Hi, welcome back to the channel. And in this video, I'm diving deep into the fascinating world of software engineering concepts. So whether you are a beginner or looking just to brush up your existing knowledge, I got you covered. I'll start by defining what software is, exploring its various types and key characteristics. So what you are going to learn about the important stakeholders involved in software development and the roles, etc. So what you can expect from this course? You can look forward to a comprehensive understanding of software principles and practical examples that will enhance your learning experience. Next, I will introduce you to the field of software engineering, covering its phases and the software development life cycle, or we call it as SDLC. I'll break down different SDLC models and key concepts in software design, including coupling, cohesion, etc. I'll discuss the principles of software design, specifically the solid principles, and debunk some common myths about software architecture. You will gain insight into the fundamental elements that make up software architecture. So finally, I will explore common architectural styles and design patterns, as well as the quality attributes that ensure software meets user needs. And I'll wrap up with an overview of the technology stack used in software development. So grab a notebook, maybe get comfortable, and let's get started on the journey into the software engineering. Let's start with the very basics. What is software? Software, we all use laptop, desktop, mobile application, right? Mobile. So it means we already use software. Software refers to a collection of instructions, data, and programs that tell a computer how to perform specific tasks. Now those tasks, maybe you're reading something from your machine, you are opening a Word document, doing some stuff, you're creating a presentation, or maybe you are on www, you are on internet, just navigating through a web application. Everything is software. It is a critical component of computer system, enabling hardware to operate effectively and allowing users to execute a wide range of functions. So what is happening whenever we are using software, and we have types of softwares available, system softwares, application softwares, right? What is happening? This interaction is happening from your logic, what you have written, with the hardware on top of that this software is running. So like I said, there are types of software. Mainly there are application softwares and the system software. System software is nothing but this includes the operating system, like for example Windows, Mac OS, etc. utility programs that help manage hardware and provide a platform for running applications. Whereas the application software, these are programs designed for end users to perform specific tasks such as word processing, web browsing, gaming. Examples include Microsoft Word, Google Chrome, Adobe Photoshop. Those all are application software. And software is made of code written in programming language, like for example Python, Java, C++, etc. This code instructs the computer on what to do, whether it is displaying a web page, processing data, playing a video, playing a game, etc. So everything, whatever instructions, right? So in essence, software is what makes computer functional, user friendly, allowing us to basically accomplish a wide range of tasks efficiently. So that is what is software. Here I will mention few type of softwares. For example, development softwares. For example, we want to create some application, whether it's application or a system related software. So we need some development tools for that. Those are development softwares. Front-end softwares, for example, I want to create a web application. So I need to create a front end for it. Maybe HTML, React, JS, etc. Those are front-end softwares. And mobile softwares, game softwares. There are backend softwares are nothing but where we need to write some logic for backend application, whether it's Java or maybe some database. Those are backend software. And finally, web-based softwares. Let's see the characteristics of software. Intangible. So unlike hardware, Software cannot be touched or physically manipulated. It exists in the form of code and data. So likewise, when I was in school, my teacher used to tell me how we can explain software that you cannot touch it but you can feel it. Right? Easily updated. Software can be modified and updated relatively easily. Now this can be a contradictory statement, but compared to hardware, so for example, if I want to change the hardware, I need to go to a retail shop, I need to purchase a new one, need to see if there is any exchange offer is going on, etc., and what to do with the previous one. Maybe it's already downgraded the previous hardware, right? So easily upgrade is possible within software, allowing for improvements, bug fixing and new features. And of course, software is dependent on hardware. So software requires hardware to run as it needs physical resources, CPU, memory, storage to execute tasks. And sometimes we see also that, for example, few softwares are available only for iOS device, and they do not support maybe other platforms, right? So softwares are dependent on hardware. So this is all about what is software. Now let's go to the next section. Now, if we really want to have deep understanding of software engineering key concepts, we really need to understand the very basics, and one of them is the key term stakeholder. So what is stakeholder? A stakeholder is any individual or group that has an interest in or is affected by a project. So we get a project, and of course there is an organization behind it, whether it's an individual, just one person, or maybe the whole enterprise, right? So all people impacted by that project in any way are stakeholders. Organization so it is affected by a project, organization or decision. Stakeholders can influence the outcome of a project and may be directly or indirectly involved. They can be classified into various categories based on their level of involvement and interest. So to be true, there are multiple type of stakeholders. There are different categories. So we have, for example, end users, right? End users would be, for example, they are the people who will be ultimately using your software. For example, you are building a e-commerce website, so end users will be the people who are going to use that website. So those people are also stakeholders, and their requirement and experience are essential for ensuring the software meets, and of course its intended purpose. That's why it's key. They can be considered as key stakeholder, right? Then we have, for example, project sponsors, right? Often responsible for funding the project. These stakeholders have of course, they will have best interest, right, in its success because they have put money, right? They may also set the project's vision and goals because they are the key people, right? Then of course the development team, so developers who are putting their best interest to develop that website or that portal. The technical team is responsible for designing, coding, testing the software, etc. So they are also stakeholder. And then the testing team, or we call it as quality assurance team, right? These individuals, they put their best to ensure that the website or the portal or the system, right, what we have developed is working fine, meeting the expectation, client expectation. Then we have other type of stakeholders as well, right? For example, product managers, they act as a bridge between the stakeholders, like the development team, and then the other stakeholders, the regulatory bodies, the technical support team, etc. So these all are the various type of stakeholders we have. So primarily we can divide into these types, like for example, primary stakeholders, they are directly affected by the project, and this include customers, employees, investors. Secondary stakeholders indirectly affected, such as suppliers, community members, government agencies. And key stakeholders have significant influence over the project, such as executives, project sponsors, or major clients. So that's it. Let's continue. We'll see you in the next section. So now we know what is software. Now let's understand what is software engineering. Software engineering is a systematic and disciplined approach to the design, development, testing, and maintenance of software systems. It combines principles from computer science, engineering, and project management to produce high quality software that meets user needs and is delivered on time and within budget. So we get the requirement in terms of project. I mean, we might need to create a software, whether it's a web portal, website, etc. And then we execute few phases. We start with getting the requirements. We understand who all are the stakeholders, and then once we get the requirement, we know what we want to develop and which technologies we are going to use to build this web portal, for example. We start implementation, and then we do all the step. Finally, we create that product and we make it live so that end users can use it. Now throughout this phase, whatever we have done, everything comes under software engineering. So that's why it is a systematic and disciplined approach to design till it goes live. Design, development, testing, whatever phases are going to come, that we will see in the next few slides. But yeah, this is the idea, that the whole process steps, whatever we are executing to develop that software and then finally making it available to the end users, the whole process is called software engineering. Now for software engineering, we have few phases that we need to execute to complete that project. So we start with the requirement gathering phase, where we understand what is the requirement. We talk to stakeholders, we talk to client, basically the people who are having this requirement. We understand that requirement, we do the designing phase, right? We do the design of the software, how it is going to look like, design in terms of like, we create the documentation, we do the implementation, and then it goes for testing, then deployment, then we do the maintenance. So all these steps we execute, and sometimes what happens, one step we execute multiple times, so there are different models, we have different patterns we have, which we follow, that we will cover. So first phase is requirement gathering and analysis phase, and like it says, right, requirement gathering, we need to understand what is the requirement. Requirement gathering is the process of collecting and defining the needs and expectations of stakeholders for a software project. This phase is crucial. It's not crucial, it's very, very crucial, because if we do not understand the requirement correctly, it's like a client is looking for an apple tree, and we understand that the client is looking for maybe a banana tree, and then we eventually make something else which is not even needed, right? So that's why this phase is the most crucial phase in software engineering, as it establishes a clear understanding of what the software must achieve, and there are multiple brainstorming sessions we do to achieve it, and we need highly qualified people who can understand the language of non-technical business people as well. So let's see the steps of this phase, requirement gathering steps. So what first we do, basically in this whole journey we will have multiple type of role, multiple type of people, right? So for example, we will have business analysts, project managers, developers, the SMEs, subject matter experts, right? And then on the other side we have business, client, stakeholders, who are having the power to impact the whole project. So they have the requirement. Now first we need, and business people, right, the stakeholders, they might not be technical people, so they will give the requirement maybe in layman language. Now we need that transition, that when they are speaking something, we need to understand that and then put it on paper, so that development team can take that as input, and then can use the technology and create those components, so that finally that whole solution works, right? So first thing is stakeholder identification. We need to understand what are kind of stakeholders we have and what is the impact they are having on the whole enterprise. So identifying all parties involved, including users, clients, and project sponsors. Then interviews and workshops. What does that mean? Conducting one-on-one or group discussions to elicit detailed information about requirement. This is a very crucial step, because there are multiple brainstorming sessions in which we try to understand what is the requirement from business. Okay, we ask questions again and again, so there are steps. And then surveys and questionnaires, distributing structured form to gather quantitative and qualitative data from a larger audience. Document analysis, review existing documentation such as business plans or user manuals to understand current processes and needs. So for example, there is an enterprise which is looking for some solution related to their maybe existing or maybe a new pillar, right? And they are looking for this new website portal where they can maybe create a career related website, right? So what we need to do is, if there is they are already using maybe some web portal, maybe for some other pillar, some other requirement, right? So we try to understand as an enterprise perspective, what kind of technology they are looking, what kind of technology they are interested into. So we sometimes we check the existing documentation as well, so that we come up with more questions, and with those questions we do the brainstorming. Then prototyping, developing preliminary version of the software to gather feedback and refine requirements. This is sometimes called POCs also, proof of concepts. What we do if we do not understand the requirement completely, sometimes we create a smaller POC, and then we arrange the show and tell session. We show it to the client, see this is what you are looking for. So this way we get more, first thing is more confidence of the client. The client is also the okay, they are working for the same requirement what we have. And also if there is any gap in the understanding, maybe what we have understood is not completely aligned, so that gap also will be minimized, because they will tell okay, no, this is not we are looking for, we are looking for something else, right? So that gap will be filled. Prioritization, assessing and ranking requirements based on their importance and feasibility. So for example, this project is a big project which might take maybe a couple of months to complete. So and of course the client is also looking for that we need to deliver this project as soon as possible, right? So sometimes what we do, we prioritize different requirements. So for example, there is a requirement of login functionality, there is a requirement of some marketing campaign, right? And so we discuss and we decide, we brainstorm, we ask this question, which feature is more priority, which feature is having more priority, which we can deliver first, and then the next phase we can deliver the remaining one. So we do the prioritization, so that first thing is we can have phase wise delivery. Second thing is the more required features will be delivered first. Then validation, ensuring that gathered requirements align with business goals and user needs. This is kind of quality assurance. Now let's understand what is the importance of requirement gathering phase. This is the most crucial phase of the whole software development life cycle. Clarity, so provides a clear understanding of what the software should accomplish. So we will have that information within this phase. So it serves as the foundation for the design and development phase, because the development team is going to take this as source of input and then start a development. Risk reduction, it helps identify potential issues early, reducing risks and rework later in the project. So like I said, sometimes we create proof of concept, we show it to client, and then we gather feedback. If there is any gap, fill that gap. It's better if we get to know whatever is the correct requirement in this phase itself. Stakeholder alignment, it ensures all stakeholders have a shared understanding and agreement on project goals. So basically, after all those brainstorming sessions, we create the documentation, we get this approval sign off from client, okay, yeah, this is what they are looking for, with proper assumptions, everything, like we document and we get the sign off. And like I said, effective requirement gathering is essential for the success of any software project, leading to projects that meet user needs and business objectives. This is the most crucial phase of the SDLC, like I said. The next phase is system design phase. System design is the process of defining the architecture, components, modules, interfaces, and data for a system to satisfy specified requirements. We are going to learn about it, what is architecture, what is the component, what are the modules, etc. It is a crucial phase in software engineering that transform high-level requirements into detailed specification for building the software. So first we gather the information through this various brainstorming session, and then finally once we get these requirements, we transform them to high-level requirements. We transform those high-level requirements to detailed specifications. We create documentation, right? So this is that phase. Let's understand the key aspects of system design. So what we do in the system design phase, we do the architecture design. So we are going to learn what is this architecture, etc., and what are the different ways we can do the architecture of a given requirement. But let's understand the overall what we do in the system design phase, because I thought first we will have this very basic terminologies, and then we will move to the more advanced topics. So architecture design, it defines the overall structure of the system. What is the system, how many integrations we are going to have, how many systems we are going to talk to, right? The overall system outlines how different components will interact and work together, and it can include choices of architectures, styles, and I will discuss about them. There are different flavors we have: microservices, monolithic, event-driven. There's so many. Component design. It involves breaking down the system into smaller manageable components or modules, right? And then specifies the responsibilities and functionalities of each component. Next one is the interface design. Defines how different components will communicate with each other. So we are talking about interface, means how one is going to interact with another one. That's called interface, right? So it defines how different components will communicate with each other. It includes the designs of APIs, okay, user interfaces and communication protocols. Data design. It involves defining how data will be stored, retrieved and manipulated in any application, whether it's a static web application or dynamic web application, right? We always have some data, whether it's a static data or dynamic data, we always have a data. Now data design means where we are going to store that data, how we are going to do that those crude operations, the create, retrieve, etc., those crude operations on the data, whether it's a static data, dynamic data. So all that management, right, will come under data design. It includes database design, data models, data flow diagrams, etc. Then the user experience, UX design. User experience is nothing but how end user will see that web application. Whenever we open any website, for example Amazon.com, we see that okay, some sale is going on, so we'll see that, right? And if it is appealing, we like it, then of course then more user interaction will happen. That comes in under user experience. It focuses on how users will interact with the system, whether there is a button, there is a navigation, there is a mega menu, there is a header, footer. Once user click on the left navigation, something will happen on the screen, right? Those type of interactions. It includes the design of user interfaces, usability and accessibility considerations. Security design addresses how to protect the system. Very crucial step, very crucial design. How to protect the system against unauthorized access and data breaches. Involves designing security protocols, encryption methods and authentication mechanism. So it means your web application, if you are designing a web application, whether it's secured or not, you have some login feature. There are pages which are behind login, right? Those are authorized pages. You are still able to access those pages without login. So that's a system breach, that's a security breach, right? So all those aspects will come under security design. This is a very crucial step, and all considerations are taken within this phase related to security. Okay, and I love this one. Scalability and performance considers how the system will handle increasing loads and maintain performance. involving designing for load balancing, caching, optimizing algorithm. So for example, today I have made this website live which can handle 500 users, 500 live users, and then tomorrow the application is so much popular, thousands of users are coming. How can I scale this application so that it can handle all those additional users? That is called scalability, right? At the same time, when the most of those users are accessing your web application, still your page load time is within few seconds or nanoseconds, right? That is how performative your web application is. So that is performance, and all those things will come under this one, scalability and performance. And by the way, I just describe this term load balancing, and load balancing is nothing but whenever we have the application, right, we have different servers running, and for example, if the request is coming from different users, then the load balancer, what it does, it will just route your request to one of the server which is lesser occupied, so that if another request is coming, that will be distributed to another server. So this is how we balance the load. That is called load balancing, so that the application is always performative. So for example, there are 3 servers and multiple requests are coming, and so one request will go to server A, another request will go to server B, and so on. So this is how we balance the load. Caching is nothing but we cache the data on server or maybe on CDN or something, so that if that data is already served, we can cache it, and the next time if the request is coming for the same type of data, we can give it from the cache instead of we hit the server, so that again the performance will increase. And then optimizing algorithms, nothing but how can we optimize this whole behavior, that the application is performative, scalable, right? So all those considerations. Now let's see the importance of system design. Okay, clarity, and it was there in requirement gathering phase also. It provides a clear blueprint for developers to follow during implementation, because architects, they have designed this system, how different systems are going to interact, which type of APIs we are going to use. Everything is there in the system design, and now it is coming to the implementation team. Implementation team is aware that okay, we are going to use this technology stack to develop this web application, so this is clear. So that's why it's clarity. Quality assurance helps identify potential issues early in the development process, improving software quality. Collaboration facilitates communication among stakeholders, developers and designers by providing a shared understanding of the system. And not only collaboration, but actually a proof of agreement also. So for example, we have the documentation in place where we have specified with the diagrams, with the text, that okay, this is the system which is going to be built, and we have taken approvals also, because stakeholders are also having access to those documents. They can give some feedback, and finally if they are agreeing to it, they will say okay, yes, this is what we are looking for, right? So not only collaboration, but we also have a proof of agreement that okay, this is what we are going to build, and then customer is also aligned with that solution. And of course collaboration also, sometime team from business side also, if business is having IT department, they will also give some feedback, some improvement areas, etc. So it's a collaboration also can happen. Maintainability, a well designed system is easier to maintain and extend in the future. Of course, overall the system design plays a critical role in the success of software projects by ensuring that the final product aligns with user needs and business objectives while being efficient, scalable and maintainable. So far we have learned the requirement gathering phase, very crucial phase, system design phase, very crucial phase, but I'd still say requirement gathering phase is the most crucial phase ever. Now let's think, right? We got the requirement, we understand the requirement, we have designed some documents, right? Nice documents which will specify how the system will look like, and then it is handed over to the implementation team, the developers, the superheroes, because they are going to develop this web application or any of the software. Implementation in software engineering is the phase where the designed system is built and put into operation. It involves translating the system design into actual code as well as integrating and testing the components to ensure they function as intended. Right? So that is the whole implementation phase, starting from writing your first line of code till it is validated by QA team, testing team, and then of course then it will go for actual production go live, right? Now let's understand the key aspects of implementation. Okay, coding, of course the coding part, writing the actual code based on the specifications and design documents. And right, in this phase we are not talking about the actual programming language, because this is the generic phase, right? Any programming language can be used to write for coding, but the idea is once the system design is ready, taking that system design as input, the developers they start writing the code for the specification, the integration points, etc. Developers use programming language and frameworks suitable for that project, and that is also agreed while in the requirement gathering phase and in the system design phase, like which tool, which technology stack, which programming language is going to be used, because of course licensing etc will also come into picture, and the enterprise, right, they take the licensing etc, they purchase those software license etc, and then only the development team they start the coding or programming the whole application, right? Okay, integration, combining various components and modules of the system to create a complete application. Now this means, right, so for example we have different systems, right? We have maybe we are using CMS, so we have front-end system, then we have downstream APIs, we are interacting with AWS services, we are interacting with maybe any third-party services which is providing us some data, right? And usually in any of the enterprise level solution we have multiple integrations, whether it's a CRM related information, profile related information, campaign related information, so those integrations we do, right? So that is why it says combining various components and modules of the system to create a complete application, because complete application is where this whole integration is already done, ensuring that all parts work together smoothly. Then testing phase, conducting various types of testing, unit testing, integration testing, system testing, acceptance testing, to identify and fix bugs or issues, ensuring that the software meets the specified requirements and functions correctly. Documentation, creating technical documentation that describes the system's architecture, code and usage, and this includes user manuals, API documentation and maintenance guides. Sometimes we create documentation for business users as well. Now just imagine a scenario where we have built a system which is a CMS based. There are multiple CMS solutions available, like for example Adobe is one of the content management system which is called Adobe Experience Manager, right, where what we can do, we can create dynamic pages on the go, on the fly. Business can create HTML pages on the fly and can publish those pages, right? So what we do, we have components available, functional components, and then using those functional components business can design pages. So sometimes we need to create a guide, authoring guide also, that also comes under documentation, that how we are going to use this component, whether it's a text component, whether it's a image component, or we text image component, right? So that documentation will also come in this implementation phase. Then deployment, installing the software in a live environment where end users can access it, and this may involve configuring servers, databases and network settings. Training, providing training for users and administrators to ensure they understand how to use and manage the system effectively. Now consider, I mean, we have developed the software, it is working fine, but we know how to configure it. We have not even given training to any of the person, and now business, right, they are just not aware how do we use it. Bingo. Yeah, so this is of course a crucial phase, and most of the time all these trainings we put it again in the documentation, because sometimes people come and go, right? They change the organization. So if a new person is joining the team, they will just go to the training documentation, learn from there. Maintenance phase is after deployment. Ongoing maintenance is necessary to address any issues that arise and to implement updates or improvements. Believe me, there is no website or web portal or any digital platform which is like 100% foolproof solution, 100% working without any bug. If it is like zero bug, then of course that product, right, which we have developed is not even up to that mark. Right, pain is gain, right? So maintenance is we sometimes we get the issues, we fix them, or sometimes we enhance the existing features, so that because every day new innovations, new things are coming, right? So that will be done in the maintenance part. Let's understand this phase. What is the importance of this phase? Very crucial step. Realization of design. It turns theoretical design which we have put in the system design phase, that those were just documented in the documents, right, into functional software that users can interact with. So first time user will see, okay, yeah, this was in my mind, now I can see it is fully working this the way I was expecting it to. So through rigorous testing, implementation helps ensure that the software meets quality standard with QA, with proper testing. User satisfaction. A well implemented system can significantly enhance user experience and satisfaction. And of course, it will be the foundation for future development. A successful implementation sets the stage for future enhancements and scaling of the software. And it is said that whenever we get a new client, a new business, this is the very first time we are interacting with this client. The very first phase, the very first go live is very crucial for us, because that will create the impression. We need future work also from the client, right? So we want this solution to be 100% working, 100% innovative. Everything should work fine. Then only we can impress client, and then only we will get more work. Sometimes what happens, if this is an existing client, we have already created that reputation and we have done some mistake, it's still acceptable, because the client also understand, no, we know them, they are very good at it, but sometimes glitches happens. But if it is for the first time, we need to create that reputation, right? So that is why foundation for future development. And implementation is a critical phase in the software development life cycle that involves everything: building, testing, deploying. It is critical, because if it is not done, I mean, this is the end result which client was looking for. So if it is not done properly, then it's of no use. The whole thing, whatever we have done previously, everything is in vain. Now we have implemented development team. They are cool guys. They have done all those implementation. It goes to testing team, the quality assurance team. Quality assurance, QA, or testing. Earlier we used to call it testing, and now with more modern keywords we use quality assurance, because of course it assures that the quality of the system what we are going to deliver is 100%, even more than 100%, right? So QA, quality assurance in software engineering, is the process of evaluating and verifying that a software application meets specified requirements and works as intended. QA is crucial for ensuring that the software is reliable, functional, and user friendly. And sometimes, I mean, we put cherry on the cake, right? So QA people, they also suggest some enhancement. At okay, yeah, this button is looking good, but instead of button, if you make it maybe something else, then it will be more user friendly, because they have done previously something, they have tested something previously, maybe in some other engagement, and that is more user friendly. So sometimes they do that type of role as well. The quality assurance people they suggest new features or enhancements which can be developed maybe in the future releases. Now let's see the types of testing. So we have different flavors: unit testing, integration testing, system testing, acceptance testing. There are other type of testings also, like for example penetration testing, security testing, performance related load testing, right? All testings are also there, but these are common. So Unit testing is testing individual components or functions for correctness. So usually basically after development, a developer does that. Unit test the functionality, the functional components, whatever he or she has written. Integration testing, verifying that different modules or services work together. So integration testing is, for example, I have written a component, maybe a service in Java or any language, and then I'm connecting with maybe one of the REST service, which is another system, right? So I am able to do that, those CRUD operations. I'm able to get the data, I'm able to save the data, right? Basically interaction from one system to another system, that is called integration testing. Then system testing, testing the complete and integrated software system to validate its compliance with specified requirements. Yeah, it's like everything. After unit testing and integration testing, the complete as whole as a product. Acceptance testing, conducted to determine if the software meets the acceptance criteria and is ready for deployment, and it is often done by the end users. So from our side, we do the testing, etc. We hand it over to business people, they validate it, they see. From business also we have IT people, they validate if everything is working fine, the business users, and they give the sign off. They say okay, yes, everything is working fine. And usually what happens, once we get the sign off, then only we can push this the whole product or feature to the production environment. So that is called acceptance testing. And then we have regression testing, ensuring that new changes do not adversely affect existing functionalities. So for example, I have deployed 5 features to production environment. It is live. Now I am working on another 2 more features. So when I will deploy these 2 new features, overall now 7 features I will have in total. So before it goes to production, need to make sure that the existing 5 features are also working fine. So that comes under regression testing. So the new features as well as the existing features, and then testing, rigorous testing is done on basis of all happy path scenario, all the exception cases, etc. And then we validate if the solution is still working and there is nothing breaking because of this newly added features. Now let's see the testing techniques, various testing techniques and the tools which we can use. Usually we talk about 2 type of testing: manual testing and automated testing. Manual testing, testers execute test cases without automation, relying on human observation. So for example, let's consider there is a website, right? And this website is having features like user will be able to sign up, will be able to log in, create the profile, do some account setting, profile update information, etc., log out. Right? Manual testing is when the tester will go to the website, will open it in maybe any of the browser, for example Chrome, will do the sign up with the test data, will do the login with test data, and will perform all the functionalities available in the test data. And when tester is executing all these use cases, tester must have already created the test cases. So she will just follow those test cases and will execute those test cases one by one. That is called manual testing, because there is no tool which is doing this activity. Human is doing this activity. That is why it is manual testing. Automated testing, using automated tools and scripts to execute tests which can save time and improve accuracy. And various tools are used for testing, such as Selenium for web application, JUnit for Java application, Postman for API testing. So automated testing is nothing but consider we have an application where we have hundreds of pages and various functionalities involved, and manual testing is fine, but of course with manual testing, first thing it requires lots of time to do that manual testing again and again. Consider we are deploying 2 features now, again next week we are deploying 2, 4, 5 more features to it, so we need to do that regression testing again and again. So it is time consuming effort. And also because of human nature, we might miss something. So automated testing is nothing but we can write scripts, for example in Selenium, and we can write for all the features, right? For all the features, dynamic features or static features, whatever we have, we can write script in Selenium, and the tool will do it for us. It will just have to run the script, and then it will execute all the flow whatever we have in the test cases. For example, sign up, then log in, then create profile, etc. So, and then tool will create a nice report, and this report we can just see in this report if all test cases are passed or something is failing, right? So two flavors: manual testing and automated testing. Now what is defect tracking? So identifying, documenting and managing defects found during testing. Tools like Jira or Bugzilla are often used for this purpose. So basically, whenever a tester, right, or manual tester or automation tester finds some bug or defect within the application, these are the tools available. So for example, Jira, so that the defect or bug can be tracked, and then later on it can be discussed and can be assigned to development team. And this is also very crucial phase, right? The tracking of defects, because unless we track it, it is very difficult to see what is the status of the ticket, if that bug or defect has been fixed or not. Sometimes we need that historical data for auditing purpose also, right? And here comes the documentation part. So maintaining clear documentation of test cases, test results, defect report to ensure transparency and repeatability. Sometimes we even make sure whenever we test and we find the bug, we put proper evidence of that issue. Okay, that at this time frame we have received this type of issue, so that, I mean, if some audit happens in future, that can be used as a reference. Okay, let's see the importance of quality assurance. By the way, without reading these notes also, we can make it, right? Why we need quality assurance? Because until we do the quality assurance, how do we make sure that the features or the product what we have developed is working the way it should work or not, right? So reliability, it ensures that the software behaves as expected under various conditions. Happy path scenario, exception cases, very edge cases, all those cases, we create the test cases and then we execute them. User satisfaction, high quality software leads to better user experience and satisfaction, right? Cost effectiveness, identifying and fixing defects early in the development process is typically less costly than addressing issue post deployment. Consider a scenario, right? We found this issue before we went on production, right? Which the issue might impact maybe some user profile information, right? Consider we found this before we went live, so we can just fix it. There is no impact on the production data because we have already fixed it. Now consider we could not identify it and the application is already live, and now we are talking about lakhs of users. And now we know that these lakhs of users will have an impact. Their profile information is not correctly saved in the system. How we are going to tackle such issues? We cannot ask those lakhs users to come back again and update their profile information. Consider we were having this field, address field, right, in the profile, which we should store, but somehow this issue was there that this was not being retained in the database, right? So that's why cost effectiveness and risk reduction helps to minimize the risk associated with software failure, which can lead to financial losses, reputational damage, sometimes compliance issue, or even legal issues, right? So quality assurance is a systematic process that involves testing software to ensure its quality, reliability and performance, and it is essential for delivering a product that meets user expectations and industry standards. Okay, so now the software is tested, it is working fine. We have even received the acceptance testing sign off also. The user is also happy, business user is also saying yes, it is working fine the way it should work. The next phase is deployment phase. We want to deploy our application, right, so that end users can take benefit of it. Deployment in software engineering refers to the process of making an application or software system available for use. This phase typically follows the development, testing, and quality assurance stages and involves several critical steps to ensure that the software is ready for end users. That is the typical definition. Now let's see the types of deployment. So we have, likewise we had the manual testing and automated testing. This time also we have manual deployment and automated deployment. Like it says, manual deployment involves manually transferring files and configuration settings on the server. So someone will just install those configuration files, deploy the code, right, using some commands. That is manual deployment. Automated deployment uses tools and scripts to automate the deployment process, ensuring consistency and reducing human error. So for example, Jenkins we use for auto deployment. We know by this time, whenever is someone is creating a golden branch, then just trigger the build and the code and configuration will be automatically deployed. Let's see the deployment environments. What are those? Okay, so we have different flavors of deployment environments. First one is the development environment, then staging environment, or sometimes we call it as pre-production environment, and then the production environment. Development environment where software is initially built and tested. Usually what happens, developers, they build the functionality, they do the unit testing on their local server, local machine, and they finally push these changes to development environment, because that is basically an integrated environment for developers, so that they can validate their functionalities along with other developers, right? But kind of a mimic, not 100% mimic, but kind of replica of production environment. Production environment is of course having better CPU, better server capability, capacity, etc. But at least from integration point of view, development environment will have all the integrations available on that server, so that developers can validate it. Staging environment, a replica of the production environment where final testing occurs before going live. Usually business users, they do the final validation, they give the sign off that yes, everything is working fine. It is exact replica of production. Sometimes even the server strength, the CPU, etc. is almost same, so that we can business users or the development team, they can make sure, okay, this is how it is going to perform on actual production environment. And finally the production environment, the live environment, the actual website www.whateveryoursite.com, right, the live environment where end users interact with the application. So 3 environment, but sometimes we have more environments also based on different different aspects of your project. So for example, sometimes we might have a QA environment in between, so dev environment, QA environment, where the QA person, the quality assurance team, they do the validation, right? So or sometimes we can have multiple development environments also. Consider we have different teams working for the same project. It's a big project and we have different small development team and they are working for different functionalities, right? So sometimes we have different development environments, then QA environment, then staging environment, production environment. So it's actually based on the requirement, what kind of project we have, so we can increase the environments if needed. Let's understand deployment strategies. Okay, so we know deployment means we are installing that application on servers, like for example dev server, production server, right? Now there are different strategies we can use to deploy the application on servers. So one is blue-green deployment, then canary deployment, rolling deployment. Blue-green deployment is when we will have two identical environments. One is blue, one is green, hypothetical color code, where one is live, the other one is idle. Live means end users are using that environment. That server is being used when the request is coming. So that server is serving the request. So that is a live server. And another one is idle, means not in use, means the requests are not being served by that server, and updates are made to the idle environment, and then traffic is switched over. So once the deployment is complete on the idle environment, then the traffic will be switched to the idle one, that will become live, and the other one will become idle, and then the deployment will happen on the other one. Canary deployment is rolling out the updates to a smaller subset of users before a full rollout to monitor for issues. And rolling deployment is gradually replacing instances of the previous version with the new version without downtime. Let's see one by one. First one is blue-green deployment. So the definition says blue-green deployment is a release management strategy designed to minimize downtime and reduce risks associated with software deployments. The core idea is to have two identical environments. So code and configurations, everything is same. Core have identical environments. The blue environment, which is live production environment, and the green environment where the new version of the application will be deployed. So this live environment, users are accessing it, will not touch it at all, and this replica of this environment, right, the new environment, the deployment will happen, and once the deployment is complete, these users will be switched to the new one, it will become live, and then this deployment will happen here. So that's why it's blue green. Let's see how it works. So the setup, you maintain two environments, blue and green, that are identical in configuration and capabilities. Deployment, when a new version of the application is ready, it is deployed to the green environment while the blue environment continues to serve traffic. Then after the new version is deployed in the green environment, thorough testing can be performed to ensure everything is functioning correctly. Then switching the traffic, once testing is complete and you are confident in the new version, everything is working fine, you switch the traffic from the blue environment to the green environment. This switch can often be done instantly without any disruption or with minimal disruption. And in case of there are any issues after the switch, rolling back to the previous version is straightforward. You simply redirect traffic back to the blue environment. It's straightforward. Okay, let's see the blue-green deployment benefits. Reduced downtime. The switch between environments can happen very quickly, minimizing downtime for users. Easy rollback. If issues are detected post-deployment, reverting to the previous version is seamless. And testing in production, it allows for real-world testing of the new version without affecting users. And isolation of changes, it means each environment is isolated. Of course, it is reducing the risk of affecting the live applications. Now let's see the blue-green deployment considerations, what we should consider. Resource usage. Maintaining two identical environments and with the same configurations, right, that's why they are identical, requires additional resources which may increase costs. It means infrastructure, all the resources, for example, whether it's database or additional services, etc., it's just duplicate, right? So it will, of course, will require additional increased costs. Complexity, managing two environments can introduce complexity into deployment process and operational overhead. The overall blue-green deployment is a powerful strategy for organizations looking to improve their release processes while maintaining high availability and reliability. The next deployment type is canary deployment. Let's see what it is. Canary deployment is a release management strategy that allows you to gradually roll out a new version of an application to a subset of users. It means we have number of users coming to our application. We will divide the users, and few users will be served by this new server where we will have the deployment. Okay, new version applicant to a subset of users before making it available to the entire user base. The name canary, okay, comes from the practice of using canaries in coal mines to detect dangerous gases. If the canary was healthy, it indicated a safe environment. So this word was driven from there. So for example, we have version 1 and there are new changes for our application and the version 2 is deployed. So for few users will be served with version number 2, which is a new code change set with new deployment, right? And other users will be served with the existing environment, existing version. Now let's see in detail how it works. So initial release, the new version of the application is deployed to a small percentage of users or a specific subset. That is why it's called canary, right? Monitoring the performance and behavior of the new version are closely monitored. This includes tracking metrics like error rates, response time, user feedback, etc. Then evaluation. If the new version performs well without significant issues, the deployment can gradually expand to more users. So subset of users then will increase to more users, eventually it will be applicable for all users. I mean, that is a strategy. This can be done in stages, increasing the percentage of users who receive the update. Full rollout or rollback. If problems are detected during the canary phase, you can quickly roll back the changes for the canary group, mitigating risk. If everything looks good, the new version can be rolled out to all users. Now let's see the benefits of this deployment type. Reduced risk. By deploying to a small group first, you can identify and fix issues before a full rollout, minimizing the impact on all users. But still, because a subset of users will see the new deployment environment, and if there are issues, those users will be impacted. So there is a downside of this type of deployment. Real world testing allows for testing in a live environment with actual user interactions, providing more accurate feedback. And gradual rollout, you can incrementally increase the user base, allowing for more controlled and manageable deployment. Be cautious because this type of deployment will of course first evaluate a set of users, and like I said, if there are any issues with the deployment, those users will be impacted. So we need to be cautious if we select this type of deployment, whether our application can support that type of issue if the set of users are impacted. So then only we should go for this, otherwise we should avoid this type of deployment. Let's see what should we consider for this deployment. Complexity. Implementing canary deployments require robust monitoring and possibly additional infrastructure to manage different versions of the application. Yes. User segmentation means because we need to create subset of users, so that's why determining which users get the new version can be challenging and may require specific targeting or randomization strategies. So overall, canary deployment is a valuable approach for organizations looking to improve their deployment strategies, allowing for safer and more efficient releases. But beware that this can be an issue if the impacted user, there are no ways to fix what issues the users have faced, then we should avoid this type of deployment. Let's see the next type of deployment, that is rolling deployment. Rolling deployment is a deployment strategy where a new version of an application is gradually rolled out to servers or instances in a controlled manner. So earlier was for a subset of users. This time we have for servers. So we will gradually increase that deployment to servers. Instead of updating all instances simultaneously, so for example, there are 5 servers of the application. First we will deploy it on one server, then another one, then 2, then 3, and so on. So gradually we will increase deployment to all the servers. So instead of updating all instances simultaneously, a small subset of instances is updated at a time, allowing for continuous availability of the application during the deployment process. Let's see how it works. So incremental updates. The new version is deployed to a small number of servers or instances, while the rest continue to run the current version. Okay, so for example, if there are 5, 2 will be updated, but rest 3 will still behave with the old version, with the current version, or we can say current version. This process continues in batches until all instances are updated. Monitoring. As each batch is updated, the system is monitored for any issues such as performance degradation or errors, and this allows teams to catch problems early. Rollback capability. If any issues are detected during the rollout, the deployment can be paused or rolled back for the affected instances without impacting the entire application. So for example, since we have batches, right? For example, for my application I will have 5 batches. I have 10 servers, and then each batch is having 2 servers, right? And I see there is an issue with the newly deployed batch. I'll just roll it back. I'll just roll back that. And there is no impact on the rest of the 4 batches. Completion. Once all instances have been successfully updated and are stable, the deployment is considered complete. Let's see the benefit of this type of deployment. Minimal downtime. Since only a portion of the instances is updated at a time, the application remains available to users throughout the process, right? Because it is like batches, so still the other one which are not updated with the current one, they will serve the request. Risk mitigation. Problems can be identified and addressed early in the rollout, reducing the risk of widespread issues. Controlled rollout. The pace of deployment can be adjusted based on the performance and feedback received from the updated instance. So those are the benefits of this type of deployment. Now let's see what should we consider for this deployment. Complexity. Managing multiple versions of an application can complicate testing and monitoring. So consider, we will roll out it for batches. So first batch, then we need to validate it. Second batch, again we need to validate, right? State management. If the application has stateful components, for example, I have a login feature, so my session should be maintained and I am navigating through the application, so from one page to another page, right? My session should be maintained. So that is kind of stateful web application. So if the application has stateful components, ensuring consistent state across instances during deployment can be challenging. What does that mean? So for example, the request is going to one server. So there are 5 servers and request is going to first one server, maybe instance number 1, and then I have logged in, right? Now the second time when I'm refreshing the page or I'm going to another page, this request is going to another server number 2. Now this server should understand that I am already logged in. So with the next time I refresh the page or I go to another page, it should not ask me to log in again. That is kind of stateful application. So what it says, state management is kind of little bit challenging because we have batches of our instances, and consider we have 5 batch. One batch is updated with the latest version, other 4 batches are still with current version, and the request is being served first using the first instance which is having current version, and after that the request is going to one of the instance which is having the latest version. So how we are going to manage this state, that is a little bit challenging. Okay, user experience. Depending on how traffic is routed, some users may experience different versions of the application, which can lead to confusion if not managed properly. Consider we have just rolled out a new web page, and this web page is only available of course because it is batch wise, right? And you just refresh the page. Okay, see this new page is coming, new user experience is coming, but at the same time when the user is going back, navigating back and coming back again to the same page, it's gone because it's giving now 404 error, because now the request is being served by another server where we do not have this deployment done so far, right? So those type of user experience issues we might face. Overall, rolling deployment is an effective strategy for maintaining application availability while introducing new features or fixes, making it popular in environments where uptime is critical. Now let's see, once the deployment is complete, there are few activities which are called post-deployment activities. What are those? Monitoring, so continuously observing the application's performance and user interaction to catch any issues early. So basically see the server load, if there are no errors on the server, all the metrics is working fine. We have different tools available for that, for example New Relic, CloudWatch logs from AWS, right? So we monitor the web application, see if there are any issues related to CPU utilization, any issues related to performance, those any issues related to security. So those things comes under monitoring part. So we monitor the application because it's just deployment just happened. Then feedback collection, so gathering user feedback to identify areas for improvement, right? Then maintenance, regular updates and patches to address bugs, improve performance and add features. Sometimes we provide hypercare support also to business. So for example, right after the deployment there will be 2 weeks of hypercare, where if we get any type of issues we will fix it. There will be an SLA defined that within 1 day, within 1-2 hours, based on priority of that defect, right? The fix will be provided and will be deployed again to the server, right? So those things comes under maintenance. Now let's talk more about maintenance phase. Maintenance in software engineering refers to the ongoing process of managing and updating a software application after its initial deployment. This phase is essential for ensuring that the software continues to function correctly, remains relevant to user needs, and adapts to changing environments or technologies. Let's go through the types of maintenance. So we have corrective maintenance, fixing bugs or issues that arise after deployment. Those are called corrective maintenance. Adaptive maintenance, modifying the software to accommodate changes in the environment, such as updates to operating system, hardware, or other software dependencies. Perfective maintenance, improving the software's performance or enhancing features based on user feedback or changing requirements. And then preventing maintenance, making updates and improvements to prevent potential future issues. To be true, no need to know about like different type of maintenance activities, but it is good to have this understanding that this categorization we have. I mean, it is always good to have such type of understanding or knowledge when we work in the software industry. That will make you out of the crowd, right? That you stand out of the crowd. Let's see the importance of maintenance. Okay, user satisfaction. Regular updates and fixes help maintain a positive user experience and satisfaction. Security, and to be true, I mean, we of course we want to make client happy. So with maintenance we put more regular updates, fix whatever bugs or defects we have. We win the client trust. Security, ongoing maintenance is crucial for addressing vulnerabilities, ensuring the software remains secure against threats. There are multiple type of threats available in the IT market. Likewise, technology is emerging. Similar to that, the threats are also emerging, and that's why we need security patches, right? So that comes under maintenance. Security, applying those security patches, applying any security or vulnerability related issues. Compliance, adapting to the new regulations or standards in the industry may require updates to the software. So for example, now we know, I mean, in the European region we have GDPR regulations, etc., right? So for example, something new has been added to the compliance. According to that, we also need to update maybe privacy policy or maybe something else to our web application, right? So that it is compliant to the rules or the governance we have, right? So those things come under compliance. And then the performance, regular performance tuning and optimization help maintain efficient operation. Let's see the various maintenance activities. So we have bug fixes, identifying and resolving defects reported by users or discovered through testing. Updates and upgrades, implementing new features, enhancements or performance improvements. Documentation is very critical, keeping user manuals and technical documentation up to date to reflect changes made during maintenance. And sometimes people skip it because the idea is who is going to check the documentation, but this is not true nowadays. I mean, in terms of audit, in terms of new people are coming to your team, and then they don't know how this application is working. So documentation is a critical part of software engineering. User support, providing assistance to users to help them navigate issues or understand new features. Now let's see the challenges in maintenance. Okay, legacy system. Older systems may be more difficult and costly to maintain, especially in if documentation is lacking. Like I said, right? Previously, the team has worked no documentation at all. Now it is coming to you, and you don't know what it is, how this whole feature is being developed, etc. You need to start from zero to understand how this functionality is working, where the code is written, what service it is invoking, how many downstream APIs, etc. we have. So it is challenging when we are working for a legacy system, basically that maintenance part. Changing requirements, and it happens, right? The requirement changes because the requirement gathering phase was not done properly. That could be one reason, or sometimes the stakeholders, they could not explain the requirement properly, and because of that gap, once the product is complete, now it's live, now we understand, okay, no, this is not what we were looking for, we need to change this to something from this to that, right? So that is changing requirement. So as user needs evolve, maintaining software can become complex, requiring significant adaptation. Resource allocation, balancing maintenance work with new development project can strain resources. So maintenance is a critical phase in the software development lifecycle that ensures the longevity, reliability and relevance of the software application. And by addressing issues, implementing improvements and adapting to new requirements, maintenance helps organizations maximize their software investments and enhance user satisfaction. Next phase is evaluation and feedback. Right, we always take feedback from users, from customer, that okay, we have developed this, how it is working fine, are you happy or not, based on different scales, right? Sometimes whether it's coming through email, whether it's you have some tool for collecting feedback or evaluation, because unless you get the feedback, first thing is, of course, it will give you a morale boost if you are getting good feedback, but also a constructive feedback will help you improve what was you were lagging behind, or the team was not able to develop it efficiently because of XYZ reasons. So it is always good to get the feedback. Evaluation and feedback in software engineering refers to the process of assessing a software application's performance, usability and overall effectiveness after its development and deployment. This phase is essential for ensuring that the software meets user needs and aligns with business objectives. So it's nothing like, okay, this software is developed, give me money and tata bye bye. No, nothing like that. So let's see the evaluation methods. These are the methods. Of course, first one is the testing, user testing, engaging real users to interact with the software and observe their behavior and feedback. Sometimes what happens, there are customer representatives which after this web application is live, they will get feedback either from call, or maybe you have a survey page on your web application, or a contact us page where user will interact, will ask some question, will provide some feedback. Then surveys and questionnaires, collecting user opinion. This is applicable for customer also, client also. So we can ask customer to fill in some questionnaire or survey. There can be multiple questions which is related to the product you have developed, that they like it or not. So we can collect through that also, collecting user opinions on various aspects of the software, such as functionality, usability and satisfaction. And analytics, analyzing usage data to understand how users are interacting with the software and identify areas for improvement. And I have created another video for analytics. There is a different playlist, please check that. Analytics, like when user is interacting, having different touch points on the web application. Basically the very first time engagement on the web application, starting from there till the user makes the decision and purchases your services, right? So those touch points and how those touch points are performing, so we can collect this data using analytics from the web application, and then can analyze this data, can take some action on those insights, right? So those options are available using analytics. Basically improving the digital channel. We will get to know, okay, where the user is facing problem, on which touch point user is not feeling happy, so what we can improve on our digital platform. Now there are two types of feedback: qualitative feedback and quantitative feedback. Qualitative feedback is in-depth opinions and experiences shared by users, providing context and insights into their interactions with the software. And quantitative feedback is numerical data which can be defined, that can be analyzed statistically, such as rating, completion time, or error rates. Let's see the importance of evaluation and feedback phase. So user satisfaction: understanding user experiences helps in enhancing satisfaction and retention. Identifying issues, highlighting the bugs, usability problems, or performance bottlenecks that need addressing. And guiding improvements, informing the development team about needed enhancements or features based on user requests. Now let's see, how do we implement the feedback once we receive the feedback, right? How do we take the action on them? So actionable insights: translating feedback into specific actions such as bug fixes, feature enhancements, or usability improvements. So I mean, feedback can be either there are issues on the existing website or platform, those are also feedback, or based on analytics data, that analysis, now the client is looking for something else which will improve the user experience, that is also feedback. So according to the decision, what after brainstorming, people will decide, the team will decide whether it's a bug, it's a feature enhancement, or it's an improvement. And then iteration will happen using feedback to guide iterative development, ensuring that the software evolves in line with user needs. What does that mean? So once we receive the feedback and we know now the phase 1 is already live, and in phase 2 we are going to put more features to the application. These features will include some improvement areas, some bug fixes, some feature enhancements, right? So first iteration is over. Now this is the second iteration. After this, again the feedback will be taken, again the evaluation will happen, and then another iteration number 3, and so on, right? So this is how we develop the software, and then we get the feedback, we work on those feedback in the next iteration. And for this we do regular reviews with the customer, with the stakeholders, conducting periodic evaluations to ensure ongoing alignment with user expectations and business goals. And we have different methodologies available. One of them is Agile, of course, incorporating feedback into Agile development. And I'm going to discuss about various type of development models available. Agile is one of them, so allowing for rapid adjustments and enhancements. Okay, the summary is evaluation and feedback are vital components of the software development lifecycle that facilitate the continuous improvement of applications by systematically gathering and analyzing user input. Organizations can enhance software performance, usability, and overall user satisfaction, ultimately leading to a more successful product. The next phase is documentation phase. And to be true, documentation phase is the phase which will which will actually start from the very first phase, requirement gathering phase, and will continue for all phases. So documentation is very critical, and it is like a continue phase it is applicable for all phases. Okay, documentation in software engineering refers to the comprehensive collection of written materials that describe the design, functionality, architecture, and operation of software systems. It serves multiple purposes, including guiding development, facilitating communication among stakeholders, and providing support for users. Let's see the types of documentation. So we have technical documentation, user documentation, system documentation, process documentation, and there could be so many types of documentation, but these are just common which we use for most of the projects. Technical documentations are it details the software architecture, code structure, APIs, algorithm used, and it's aimed at developers and technical teams, architectures. So basically the technical team architectures, they create these documentation. For example, TSD, technical specification documentation, is one of the technical document. Right, the user documentation, authoring guides and users on how to use the software, including tutorials, manuals, FAQs, etc. Those are user documentation. System documentation covers system design, specifications, requirements, and often used during development and maintenance. Then we have process documentation, describes the workflows, methodologies, standard followed in the software development life cycles, etc. Let's see what is the purpose behind all this documentation. The very first thing is knowledge transfer. It ensures that knowledge is captured and can be transferred among team members, facilitating onboarding and collaboration. So very common example. So for example, today one person is working on one of the requirement, okay, and tomorrow the person changes the role, or maybe leaves the organization, another person is joining the organization. Consider there is no documentation around. The new joinee will struggle a lot to understand what it is the product, what is this whole project, how this integration is happening. So first thing is knowledge transfer. Communication, it provides a common understanding among stakeholders, including developers, testers, users, about the software and its intended use, and its proof of agreement also, because the documentation is there and people agreed on that documentation. It's a proof of agreement. Maintenance and support assists in troubleshooting and updating the software, serving as a reference for future development and enhancements. And not only for these points, documentation is a critical phase, because we are talking about historical data. Maybe we need it for auditing purpose, right? Today we have developed something and we have not done any documentation. Consider after 3 years we need some improvement, or there is a legal implication, we need to prove something, and there is no documentation around. How we are going to prove that, why we have developed this system like that, and we have what were the considerations that time. So everything we should document, so that the solution what we have developed is foolproof solution, right? And it is as per compliance, it is as per guidelines, it is as per best practices. Those things were taken into considerations, and the proof is the documentation. Okay, let's see the best practices while we do the documentation. Clarity and conciseness. Documentation should be clear, concise, easily understandable to its intended audience. So that's why what happens when we do the documentation, we have review phase. So one person will create the documentation, another SME review or peer review will happen, because sometimes we think, okay, I have created this document and it should be good, but another person is not even understanding what is written. So that review helps in shaping the document in right manner. Consistency, use consistent terminology, formatting and structure throughout the documentation, right? A standard formatting, right, for all the documentation, so that it is easy to understand when a new join person is coming, or when maybe one person is just reviewing another person's document, because the format is unique, format is same, so it is easy to understand. Updates and versioning. Regularly update documentation to reflect changes in the software and maintain version control. uh, okay, so we have like version control means wherever we are updating this document from one version number 1 to version number 2, right, we keep the history of this update, why this document was updated, who was the person who was updated the document, right, the who was the reviewer of this document, right, we do that. And there are multiple tools available for this type of versioning. So for example, use Confluence, Word document, right, Google document, Google Docs, etc. So that versioning can be maintained. Accessibility. Ensure that documentation is easily accessible to all stakeholders using formats and tools that suit their needs. Let's see the tools for documentation. We create wikis, collaborative platforms for creating and sharing documentation among teams. Markdown editors are also there. So for example, when we use Git, which is very popular, Git also provides a markdown editor. Simple text editors that allow for formatted documentation without complex tools. Documentation generators, tools that automatically generate documentation from code comments. For example, Java docs, right? One example, we just write the whole functionality, and we just right click and create the Java doc for that particular class, right? And then project management tools, platform that integrate documentation with project workflows. For example, Confluence is one of the popular tool available in market. Notion is another one. So these tools are available, quite intuitive tools, and what we can do, we can use these tools to create the documentation for the purpose, and we can share among our team, we can share among stakeholders, get the review, get the sign off, get notified and notify others. Now overall, the summary is effective documentation is essential for the success of software projects. It supports development, enhances user experience, and ensures that knowledge is preserved for future use. By following best practices and utilizing appropriate tools, teams can create and maintain comprehensive documentation that adds value throughout the software lifecycle. This phase is the project management phase, and likewise documentation phase. This phase is also an ongoing phase. It will be in parallel to other phases. Project management is the discipline of planning, executing, and overseeing projects to achieve specific goals within a defined timeline and budget. It involves coordinating resources, managing risks, and ensuring stakeholder satisfaction while delivering a product or service that meets predefined requirements. So in short, project manager will be responsible for the project delivery, whether it's starting from the planning phase, execution phase, and if the project is on track, or if it is lagging behind, what can be done to to make it again on the track. So all those things will come under project management, along with the governance, with the resource alignment, resource management, right? People are coming, leaving, onboarding the project, outboarding from the project, right? All these things, right? Basically the whole project management phase. Let's see the key components of project management. Okay, project initiation, that is kind of sometimes it is called kickoff of the project also. Defining the project scope, objectives and feasibility, identifying stakeholders, and obtaining project approvals. Then project planning. After the initiation, project planning, developing a detailed project plan outlining tasks, timelines, resources and budgets, establishing a communication plan to keep stakeholders informed. And for this planning also we have various tools available. So for example, Jira is also one of the tool. We can create user stories, tasks, epics in the Jira, and then we can assign it to different team members. We can track the status of those user stories. You can see where we are. It will create a nice dashboard, nice chart to see if we are on the right track of the project timelines, etc. So that all those things come under project planning. Project execution, implementing the project plan by coordinating people and resources, managing teams, assigning tasks, and ensuring quality deliverables. Project monitoring and control, tracking project progress against the plan. So we have different ways for it, different type of project models. For example, whether it's a Scrum, Kanban, like which comes under Agile methodologies. Maybe we are having daily Scrum, daily stand-up calls where all the team members, right, the development team, the testing team, the BA, etc., they join the call. They discuss what they have done yesterday, what they are planning for today, where we are we on track or not, if we have any issues, if we have any blocker, etc., which we discuss in that call, and then how can we mitigate, how can we fix those blockers, right? So those will come under this. Measuring performance and making adjustments to address any deviations, managing risks and issues that arise during the project life cycle. And project closure, finalizing all project activities, ensuring deliverables meet requirements, conducting post-project evaluations, and capturing lessons learned. Sometimes it is called retrospective also. Retrospective sessions are where the team again join the call, understand what we have done correctly, what we have done wrong, where we can improve for the next phase, right? Or we want to recognize people, send some appreciations to etc., get some feedback from the clients, etc., right? Releasing project resources and closing out documentation. Project management is crucial for delivering successful projects across various industries. By applying effective project management practices, organizations can enhance productivity, ensure quality, and achieve their strategic objective. This phase is retirement phase, and the retirement phase refers to the stage when a software product or system is no longer actively maintained or supported. This phase typically follows the software's life cycle, including development, deployment, and maintenance. Let's see the key aspects of this phase. And okay, end of life. The product reaches its end of life when the vendor decides to discontinue support, update, and patches. This may be due to the software being outdated, replaced by new technologies, etc., no longer in use, right? Decommissioning, in this phase the software is gradually phased out. This may involve disabling certain features, informing users, and preparing them for transitioning to a new system. So for example, this application is built on one CMS. Just think of it, maybe it's built on SharePoint or Sitecore, right? One CMS, and now business is thinking that there is another popular CMS, maybe Adobe Experience Manager, they should utilize that. So they will migrate their system current website to the new CMS, and once this new website is ready, they will decommission the existing website. That is called decommissioning. So this transition will happen from the existing website to the new website. User will be informed, user will get a new user experience, right? Data migration. So for the same example, data migration will happen, right? Data, maybe earlier it was using any of the existing database. Maybe it was a SQL server where the user data was there. Now we are using a new database, maybe it's DynamoDB or something else. I'm just giving you an example. So that data migration is also happening. Users may need to transfer data to a new system. This includes planning for data integrity, security, compatibility with a new platform. User support. During this retirement phase, Organizations typically provide limited support to help users transition. Documentations may be updated to assist with this process. Resource allocation, resource both financial and human may be reallocated to a new project or system, making it essential to evaluate the cost and benefit of retiring the software. And of course the documentation, this is like essential part. Documentation is always essential. Maintaining documentation about the software's functionality, usage and any data migration is crucial for future reference and compliance. So the summary is retirement is nothing but okay, it is shutting down one platform, because now we have new technologies, and then migrating this whole system to a new platform, right? So this older version is getting retired. Now let's learn a new concept called software development lifecycle, or sometimes we call it as SDLC. Basically these are the same steps which we have already covered, but now we are going to learn more deeper insights about these topics, and then we will cover different models available which is applicable for software development life cycle. Okay, so the process of creating software typically follows a structured methodology known as the software development life cycle. Starting, for example, we have done the requirement gathering, analysis, then we did system design, then the implementation, then quality assurance, deployments, etc., right? So there is a way of those process, those steps to be executed, and those comes under SDLC. SDLC includes phases like we covered earlier: requirement analysis, system design, implementation, testing, deployment and maintenance, and we have already learned about them. Now there are various models available for SDLC. What I have done, because there are various, I have categorized them into 3 parts. Let's see one by one which model is applicable for which use case, what are the features of these models are having, which is better than other, right? So software development lifecycle models are frameworks that outline the various stages involved, and we know the stages: the requirement gathering, testing, development, implementation, all those are stages. So SDLC models are frameworks that outline the various stages involved in software development. Each model provides a structured approach to planning, creating, testing, deploying, maintenance, etc., everything of the software. And there are various models available: Agile, Scrum, Waterfall model, which is a very legacy one, DevOps model, Kanban, Spiral. So there are lots of models available, right? So we will learn about those models in the upcoming slides, right? So like I said, I have categorized all those models into 3 categories: traditional models, and agile models, and modern and hybrid models. Traditional models are the legacy ones which are used since the inception of software engineering. Agile models are still popular, right? And then modern and hybrid models, which are like a combination or combined flavor of traditional as well as agile. Sometimes what we do a tailored model, which is a combination of multiple models as per business requirement. So first one is traditional models, and we are going to cover 3 models. One is the waterfall model, V model and incremental model. Let's first understand waterfall model. Waterfall model is a traditional software development methodology that follows a linear and sequential approach. It is one of the easiest model used in software engineering, and it is structured into distinct phases where each phase must be completed before the next one begins, right? That's why it's linear. So one is dependent on the previous one. Until first is complete, we cannot move on to the second one. That is why it is called a waterfall or linear or sequential model. So this diagram depicts why it is called waterfall, because we have already gone through the various stages of the software development lifecycle: requirement gathering, system design, implementation, quality assurance, deployment, and finally maintenance. And these are different phases, right? Once the requirement and gathering is complete, Then we will move on to the next phase, system design. Once this system design is complete, we will move on to the next phase, that is implementation, then testing, then deployment, and then maintenance. We cannot move to the system design until the requirement gathering is complete. We cannot move on to implementation phase until the system design is complete. We can move into the testing, deployment, and maintenance phase until the previous phase is complete. And that's why it is called waterfall, because just imagine it as a waterfall. The water is flowing from upside to downside, right? So until it will complete this step, it won't reach to this step. That's why it is tricky in a way, because sometimes we understand, while this, for example, while system design, we understand, okay, there is one requirement which is not yet clear. We should go back to the previous phase and confirm, have some more brainstorming sessions with client, customers, stakeholders to gather more understanding. But since waterfall system doesn't allow that, right? So it's like a breach where when we want to discuss some more understanding, we want to take some more understanding for the requirement. So that is one of the disadvantage of using waterfall model, that since it's sequential, we cannot go back to previous phase and do some refinement. Let's see the key phases of the waterfall model. Like we have covered earlier, requirement gathering, understanding and documenting what the software needs to achieve. Stakeholders provide input to define project goals and requirements. We do brainstorming session, we do interviews, etc., documentation, etc. We see the existing architecture, we see the existing documentation, right? We gather whatever requirements we can get from the client or different stakeholders, and we document them. A very critical phase, like I said earlier. Then the system design phase. This is translating the requirement which we have received earlier into a blueprint for the software. Detailing architecture, we create diagrams, we create documentation, again basically converting those layman language, the non-technical language, to the technical specific documentation, etc. We create user interfaces and system interaction diagrams. There are multiple type of diagrams we have, so we create those diagrams, whether it's system context diagram, logical flow architecture, etc., etc. So we create those diagrams and documentation those come in the system design. Then we have the implementation phase. The system design goes to implementation team as input, and they do the actual coding of the software based on the design specification. Developers write the necessary code to build the software. Then it goes to quality assurance team. The testing happens, systematic verification and validation of the software to ensure it meets the specified requirements. This phase involves identifying and fixing bugs, right? Then after the testing is complete, then it will go for deployment. So like we learned earlier, there are multiple deployment environments, whether it's development environment, quality assurance or QA environment, staging environment, or pre-production environment, or finally the production environment, right? So releasing the completed software to users and integrating it into the operational environment, that is called deployment. Then comes the maintenance phase, where ongoing support and updates to the software post deployment, some more features, additional features, some enhancements, or maybe some bugs which are being reported after this is live on production. So those activities go to maintenance phase, and this includes fixing any issues that arise and making enhancements based on user feedback. Now let's understand the advantages of the waterfall model. So one is simplicity. It is easy to understand and manage due to its linear structure, right? Clear documentation. Each phase produces documentation providing a clear project record, defined milestones. Progress is easily tracked with clear deliverables at each stage. So it's easily understandable why it is, what is the advantage of this model, because it is easy to understand. So it is sometimes not easy to manage, or the execution is not that much fruitful, but yeah, it is easy to understand. And let's see the disadvantages of the waterfall model. So first one is inflexibility. It is difficult to accommodate changes once a phase is completed. If requirement changes, it can be costly and time consuming to revisit earlier stages, right? So for example, if there is any requirement changing, then we again need to start from the very first phase. Again, we need to follow all those steps, the requirement gathering, the system design, the implementation, right? And of course, in linear fashion only. Lead testing, bugs may go undetected until the testing phase, leading to potential issues being discovered late in the process, because the testing will be done post the implementation is fully complete. So if there are any bugs, I mean, we are not validating small chunks of the functionality. For example, we have been given this 100% of some work. We will not validate this like that 10% of work is tested, validated, it's working fine, then another test. No, it is like you complete the 100% of work and then validate it. So it is kind of late testing and late discovery of the defects or bugs. And assumes requirements are clear. Works best when requirements are well understood upfront, which is not always the case. 99% or even 100% is the case. The requirements are never crystal clear. They change frequently. So that's why the waterfall model usually doesn't work, right? Because the requirement changes, and if the requirement or changes are changing, then the phase, this linear approach will fail. Okay, let's see the conclusion. The waterfall model is suitable for projects with well-defined requirements and where changes are minimal. However, its rigidity can be a limitation in more dynamic and iterative environments where methodologies like Agile may be preferred. Right? So if the project is well-defined, it's a small project, minimal changes are required, then we can consider waterfall model. But if it is a big project, more iterations are required, there are multiple requirements we need to execute, right? Multiple functionalities, it is a big enterprise solution, then we should think of some other model. Maybe Agile is one of them, right? Waterfall model may not be suitable for that type of project or requirement. So within the traditional model, after waterfall model, let's cover the V model, or we also call it as validation and verification model. The V model, also known as the validation and verification model, is a software development process that emphasizes the relationship between development stages and testing activities. It is an extension of the waterfall model where each development phase has a corresponding testing phase, visually represented in a V shape. So this is the key here, each development phase as a corresponding testing phase. Now we have seen that waterfall model has one disadvantage, that 100% test development is complete, then only the testing will start, right? So let's see how V model will help here. Let's see the key features of the V model. Verification and validation. The model distinguishes between verification, building the product right, and validation, building the right product, ensuring that each aspect of the software is checked and confirmed. Early testing. Testing activities are planned alongside development, allowing for early detection of defects and ensuring that each phase meets its requirement before moving to the next. Clear structure. The model provides a structured approach with clear defined phases, making it easier to manage and track progress. Now let's understand with this pictorial format. So what it says, and that's why it's called V model, because if we see, for every phase of the development there is corresponding a testing phase. So for example, requirement design, we have the acceptance test. For system design, we have the system test. For architecture design, we have integration test, and so on, right? So that's why, because it looks like we can imagine it as a V, that's why it is called V model. Let's see the phases of V model. So likewise, we have waterfall model. It is just extended version of waterfall model. We have the same phases. Likewise, we have the requirement analysis, system design, architecture design, the module design, etc. I mean, whatever we have covered, it gives some extra stress on the validation, on the testing phase. So for each development phase, there is a corresponding testing phase. So requirement analysis, it defines user needs and system requirements, right? And the validation would be to ensure requirements are complete and clear. System design will outline the high level architecture of the system, and validation will check design alignment with the requirements. Architectural design details the system's structure and component interaction, and in the verification it will confirm that the architecture can support requirements. Then the module design will break down the architecture into individual components, and then the verification phase will ensure that the designs for each modules are correct and feasible. Then goes to implementation phase, actual development of the code, and then the validation phase will start from here, right? It involves unit testing, implementation phase, corresponding unit testing for individual modules. Then we have integration testing. So test interaction between integrated modules. If there are multiple systems we are integrating with, so validation of those integrations, if they are working together or not. Then we have system testing. It validates the complete system against requirements, and validation will check if the system meets user needs and business objectives. Then we have the acceptance testing, final validation by business users and users before deployment, and the validation phase will confirm that the user is ready, the system is ready for production or not. Now let's understand when to use the V model, when should we use, which use cases are appropriate for V model. Okay, well-defined requirements. The V model works best when the project has clear, stable, and well-documented requirements from the outset. So if requirements are likely to change frequently, a more flexible model like Agile may be preferable. Right? So if the requirements are fixed, very well defined, then V model can be considered. Regulatory and compliance projects. Projects that must adhere to strict regulatory standards. For example, healthcare industry, finance industry, aviation industry, right? Because there we need that every phase has done the correct job. We need revalidation of each phase, right? So that is a good example where we should use it. And it benefits from the V model structured approach to validation and verification. The documentation and traceability aspects are crucial in these scenarios. I mean, the healthcare industry, finance industry, or aviation industry, or legal, something related to legal. Smaller to medium-sized projects. The V model is often more effective for smaller to medium-sized projects, where the complexity and scope are manageable. In larger projects, a more iterative approach might be required to handle evolving requirements. Consider we have a small project, so it is easy to even foresee what will be the requirement. The requirements can be freezed, requirements can be understood, well understood, right? But if we are building the solution for enterprise, where it's a huge enterprise, the solution is huge, there are lots of requirements, it is very difficult to have well documented requirements in the start of the project. Next would be stable technology and environment. If the technology stack and project environments are stable, the V model can be very effective. In rapidly changing environments, more adaptive methodologies may be necessary, again Agile. Projects with well-defined testing strategies. The V model is ideal when there is a clear strategy for testing at every phase of development. Teams should be prepared to develop comprehensive test plans and have the resources to execute them. And the last one would be clear project timelines and milestones. The V model is suitable for projects with defined timelines and milestones where deliverables are clearly outlined. This model helps keep the project on track by emphasizing the completion of each phase before moving on. So these are the use cases where we can consider V model as the SDLC model. Now let's see the advantages of V model. First one is clarity and structure. The model's structured approach allows for easy tracking of progress and understanding of relationship between development and testing. Early defect detection, like I said, because for every development phase we have a corresponding testing phase, so early defect detection will help. testing is integrated into each development phase, enabling early identification and resolution of defects. Improved quality, of course, because for each phase we will have corresponding testing phase, so the quality will eventually improve. With the rigorous validation and verification processes, the model enhances the overall quality of the software. Let's understand the disadvantages of V model now. So first one is it's rigid in nature. Likewise, in waterfall model we cannot go back. The first phase is complete, then only we will move forward. In this phase also, the development phases are having corresponding testing phase, but we cannot go back to fix anything, right? The V model is less flexible than agile methodologies, making it difficult to accommodate changes once development begins. Assumes requirement stability. The model assumes that requirements are well defined and stable from the outset, which may not always be the case. 99% case requirement changes. So it is very difficult to have static fixed requirements and then on top of that we start working. So that's why this is one of the disadvantage of this model. High upfront planning. Significant time and effort are required for planning and design phases, which may delay the start of actual development. So let's conclude in this. The V model is an effective approach for projects where requirements are clear and stable. This is the key term. So if requirements are clear, not changeable, not changing, it's stable, then it can be considered. Its emphasis on validation and verification at each stage ensures high quality software, making it suitable for safety critical systems where thorough testing is essential. And the examples I had given is life science related project, healthcare related project, aviation related projects, right? So we are discussing traditional models, SDLC models, and this one is the incremental model. The incremental model is a software development approach that builds the system in small, manageable segments or increments. Each increment represents a functional piece of the software, allowing for gradual enhancement of the product through multiple iterations. So we got a big requirement where we have, for example, multiple features to be included in a digital platform. What we will do, we will first prioritize those requirements, and maybe we will have like this whole project will go in 3 phases. Phase 1 will have the most prioritized item, phase 2 will have the lesser one, phase 3 will have the least priority items, and then this go live, the deployment will happen in incremental fashion. Means first will go the highest priority items will go in the first release and so on, right? So that is called incremental model. And each increment, each release will be a full functional capability. It's not like that we are delivering something and it's not functioning properly. So it will be a fully functional module which we are delivering. Let's see the key features of incremental model. So first one is for sure, because we are seeing incremental model, so we will have phased development, phased delivery. The software is developed and delivered in increments, iteration 1, iteration 2, iteration 3 and so on, with each increment adding new features or improvements based on user feedback. Early delivery. Initial increments can be delivered to users early, providing value and allowing for real world testing and feedback. Flexibility. The model allows for changes and adjustments based on user feedback and evolving requirements, making it adaptable to changing needs. Let's see an example. See, so for example, we have received one website which has both static pages and dynamic pages, right? We started development of this website, and as per incremental model, what we had been aligned with the business that first we will release the static pages, and once in the second phase we will deliver the dynamic pages, dynamic functionality. For example, registration is there, login feature is there, any dynamic feature is there where we are integrating with downstream systems, etc., right? So static website, to make a static website, it is easy to develop because all we are playing with the text, images, etc. Correct? Now, since we are delivering those static website in phase 1 as early as possible, we will have good impression, we will in front of client, in front of customer, because it will add value to the client, and also that that in the next phase client is going to receive the second dynamic functionalities, right? And both these phases, iteration 1 and iteration 2, in which we are delivering static website and then the dynamic functionalities, they both are separate, they both are individual and working modules. Those are not dependent on each other, that unless the dynamic functionalities are complete, we cannot access the static pages. Now let's see the phases of the incremental model. And since we have already discussed the SDLC, these phases will come again and again, because all these models have modified these phases only, right, in a way or other. So first one is requirement gathering. We'll get the initial requirements, collect them, prioritize them, because now we are talking about the phased delivery. So we need to collect not only the functional requirements, but also to understand which functionalities are having more priority than others, so that those can be planned in first iteration, and so on. Not all requirements need to be defined at once. Only those for the first increment are necessary, because anyway eventually we are going to get feedback also from the client after first iteration, and those can be combined with the second iteration or third iteration. Design and development. The system is designed and developed incrementally. Each increment includes a specific set of functionalities, right? Testing phase. Each increment is tested for functionality, usability, and performance, ensuring that new features integrate seamlessly with existing ones. Deployment. The increment is delivered to users for feedback, and the product can be further refined based on their input. And repeat. This process will repeat. The process is repeated for subsequent increments with ongoing requirements gathering, design, development, testing, any user feedback, whether it's an enhancement, bug fix, etc. Right? So these whole phases will repeat. Again, requirement gathering, design, development, testing, deployment, again repeat. So it's like that. That's why it's called iterative deployment, iterative model. So let's see the advantage of this incremental model. Early realization of value. Users can interact with early versions of the software, providing feedback that can be incorporated into future increments. Reduced risk. Issues can be identified and addressed in early increments, reducing the risk of major failure later in development. So something that we have built the whole product at once, and now it is now the client see this and they go, oh no, this is not we are even looking for. So the whole time, investment, money, etc., right, everything is just went in vain, right? So it is reducing risk, because first we are because it's incremental delivery, so first we are phasing out the major requirements, and then we are delivering it, getting the feedback. So again the risk is reduced. Flexibility. The model allows for adjustments to requirements and design as the project progresses, accommodating changing business needs. So it's flexible in nature, of course. Improved quality. Continuous testing and feedback lead to higher quality software, as defects can be identified and fixed incrementally. Okay, let's see the disadvantages of the incremental model. Of course, it is better than the previous ones, but let's see what are the disadvantages. It requires good planning, and to be true this point, any project, whether we are using any of the model, SDLC model, it always requires good planning. Effective management and planning are essential to ensure each increment aligns with the overall project goal. Integration challenges. As more increments are added, integrating them into a cohesive whole can become complex. And I'm going to discuss about what is this cohesive coupling, etc., and how can we cope up with all these while we will do this architectural design. We have so many architecture styles and design patterns. We'll see which one we should use, so that at least we can remove this type of challenges. One of them is integration challenge. Potential for scope creep. Flexibility in requirements may lead to additional features being requested, potentially impacting timelines and budgets. So let's conclude the incremental model. The incremental model is particularly effective for projects where requirements are expected to evolve. So that is actually the case for 99% of projects. The requirements are always evolving, or where user feedback is crucial. So that is also like for almost all projects. So it means this incremental model is applicable for almost 99% of projects. By allowing for gradual development and continuous improvement, this model helps ensure that the final product is well aligned with user needs and expectations. So overall, this model is better than the previous two ones, which is the waterfall model and the V model, because it gives more flexibility. Of course, V model is one of the model which is crucial for few of the applications that I discussed earlier. For example, aviation industry, healthcare industry, etc. Right? But all these models have significance for particular use case, for particular business requirement, and then we decide which model is best for this use case. Now, after traditional models, we covered 3 traditional models. Now we are going to learn agile models. So let's cover. We have agile model, DevOps model, and RAD model or RAD model. First one is the agile model. So okay, this term agile model is an iterative and incremental approach to software development that emphasizes flexibility, collaboration, and customer feedback. Unlike traditional methodologies like the waterfall model, agile promotes adaptive planning and encourages rapid delivery of small functional software increments. So small. So there is a big requirement. First we will create small chunks of those requirements, and we will have incremental delivery. So that is what we are going to do in the agile model. Let's see the key principles of agile model. First one is iterative development. Software is developed in small manageable units called iterations or sprints, typically lasting from 1 to 4 weeks. And ideally, in ideal scenario, sprint is usually of 1 or 2 weeks, preferably. If it is 4 weeks sprint, then it might not give you that agile flavor. Each iteration results in a potentially shippable product increment. And this is actually a term in the agile that is called PSP, potentially shippable product. PSP, it means whatever we are developing, it's a very small product, but shippable means it can be live, it can go to production, and it works as a standalone unit, right? Customer collaboration, frequent communication with stakeholders and users is prioritized to ensure that the product meets their needs. Feedback is gathered regularly to guide future development. It's flexible in nature. Agile embraces changes, allowing team to adapt to evolving requirements even late in the development process, right? So for example, this sprint is of 1 week, right? And I got a new requirement in the next sprint, which is going to start the next week, right? We can put in those requirements, whether those are enhancements or some bugs, right? So flexible in nature. Self-organizing teams. Agile promotes empowered teams that can organize their work and make decisions collectively, fostering creative and ownership, right? So small teams and agile teams. So each team will have, for example, one backend developer, front-end developer, BA, right? They collectively they get the work, they collectively work on those, we have regular stand-ups, etc. And then finally they make the collective decision. So that is like the more increased collaboration among the team members, right? Continuous improvement. Teams regularly reflect on their processes and outcomes, seeking ways to enhance their performances and product quality. Let's see the common agile frameworks we have. These are the popular ones: Scrum, Kanban, and XP, right? Scrum and these are popular, at least Scrum and Kanban, they both are very popular. A popular framework that divides work into sprints. So and sometimes we use these terms if you work for a project: Scrum ceremonies, daily stand-up, retrospective, etc. Right? Into sprints with the defined roles. So we will have Scrum Master, Product Owner, Development Team, etc. Right? Scrum Master, who will be responsible for running the show, will work as a facilitator, getting the requirement, providing this information to the development team, etc. Product owner, who is going to own that product, the whole digital platform, right, from where the requirements are coming, will decide which requirement will should be taken first, and so on. And finally the development team, right, the front end developer, the back end developer, the integration developer, etc. And ceremonies like daily stand-up and sprint reviews, etc. Right? The next type is Kanban, and it focuses on visualizing the workflow and limiting work in progress, enabling teams to manage tasks more efficiently. And then we have Extreme Programming, XP. It emphasizes technical practices like pair programming, test-driven development, and continuous integration to improve software quality. Now let's go into detail of each one. Scrum. Scrum is an agile framework used for managing and completing complex projects, primarily in software development. It provides a structured yet flexible approach to project management and emphasizes collaboration, iterative progress, and customer feedback. And mostly I see in all of the projects, usually we use Scrum only, because of course it's the benefits of the iterative behavior. We get the requirement and then phased delivery. Sprint is of 1 or 2 weeks, right? So it is easy to adapt new requirement if there are changes coming. So we can have show and tell sessions with the client to understand the feedback of the client, etc. Right? Now let's see the key components of. So first one is roles of the team members. We have Scrum Master, Product Owner, and Development Team. These are the main roles. A Scrum Master facilitates the Scrum processes, removes obstacles, and ensures that the team adheres to Scrum practices. So for example, if development team, they get any blocker because the requirement is not clear, or there is an external dependency, maybe the external vendor is not providing the API response, etc. So what development team will do, they will reach out to Scrum Master, will tell him or her that this is the dependency we have. Now it's his responsibility to get those things resolved, right? Product owner represents stakeholders and customers, responsible for defining and prioritizing the product backlog to maximize value. So he's like the boss of that product. He is going to provide all the feedback, which requirement should go first. He will decide, he will attend the show and tell sessions, will provide his evaluation, provide the feedback, etc. And then we have the development team, cross-functional, right? Whenever we talk about this term Agile or Scrum, you will hear this term cross-functional. Cross-functional means front-end developer also knows the back-end development, vice versa. People know stuff, they are not much dependent. Even the full stack development stuff, these key terms came from here itself, right? The cross-functional means within the team we will have people who are cross-trained, means they know, they have all the skills which is required for that project, right? So for example, we need tester, we need developer, we need front-end developer, back-end developer, BA. So these all people are there in that team. that is a cross-functional group of professionals who work together to deliver the product increment. So, and there can be multiple teams. So one team, another team, and third team. Now all these groups, these teams would have all those type of those roles. I mean, for example, front-end developer, back-end developer, PA, tester, again front-end developer, back-end developer, PA, tester, right? So this type of team formation will happen as part of Scrum. Then we have artifacts. Artifacts will be product backlog, sprint backlog, and increment. Product backlog is a prioritized list of features, enhancements, and bug fixes that need to be addressed in the project. That is product backlog, a prioritized list of features and enhancements. Sprint backlog, a subset of items from the product backlog. So product backlog is a bigger chunk of items, right? Now consider few items which should go as part of sprint, because the sprint is of 1 or 2 or up to 4 weeks, right? So that subset from product backlog is sprint backlog, a subset of items from the product backlog that the team commits to completing in a specific sprint, that is sprint backlog. And increment is the sum of all completed product backlog items at the end of sprint, representing a usable version of the product, that is called increment. Now let's understand the various events within Scrum. So first one is sprint. Sprint is a time boxed iteration. Like I said, starting from 1 week to 4 week sprint we can have. A time boxed iteration typically lasting from 1 to 4 weeks, during which the development team works to complete the sprint backlog. Then sprint planning, a meeting at the start of each sprint where the team decides what to accomplish. So for example, now from this sprint is going to start. Before this sprint will start, we need some work, right? Now that work will be decided in the sprint plan. Daily Scrum, a short daily meeting, usually up to 15 minutes, right, for the team to discuss progress and any obstacles. So in the Scrum, right, daily we have calls, that is called a daily Scrum, where the development team, all the team members, they join the call for 15 minutes. They just update that what they have done yesterday, what they are planning for today, is there any blocker, and typically it should end within 15 minutes. And if there is any obstacle, they will inform Scrum Master, and it's Scrum Master's responsibility to get those issues or obstacles resolved. Then we have sprint review, a meeting held at the end of a sprint to demonstrate the increment and gather feedback from stakeholders, right? Sometimes we do show and tell session also with customer, with stakeholders to after the development is complete, before we make it live, we just arrange a meeting in which we show them that okay, this is what we have developed, please confirm if this is what you are expecting. Then we have sprint retrospective, a meeting after the sprint review for the team to reflect on the sprint and identify areas for improvement. So in this meeting we discuss what went well, what we could have done better, is there any blocker or something, or sometimes we give recognitions also to the people, like the people who are doing amazing job, we recognize them so that their morale will boost up, right? All these things come in the sprint retrospective. Now let's understand the benefits of Scrum. Flexibility, adaptable to change and can respond quickly to new requirements that we have seen. Collaboration, it enhances teamwork and communication among team members and stakeholders. Continuous improvement, and by the way I just used the Scrum terminology, this formatting was not correct, I just made it from white to yellow, so I just used the Scrum here. Okay, continuous improvement encourages regular reflection and adaptation, leading to better processes and product over time. Customer focus, frequent feedback loops ensure that the product aligns with customer needs and expectations. So Scrum is widely used across various industries beyond software development, including marketing, education, and product management. due to its effectiveness in promoting collaboration and delivering value efficiently. Okay, next agile framework is Kanban. Let's see what is Kanban. Kanban is a visual workflow management method used to optimize and manage work processes. It emphasizes continuous delivery, efficient and flexibility in various fields, including software development, manufacturing and service industry. So first let's understand what is Kanban board, because that way we will be able to understand what is this whole thing. A Kanban board is a visual management tool used to organize and track work in progress. It typically consists of columns that represent different stages of workflow. So the columns would be, for example, to do tasks which are not yet started. In progress, tasks means started and the team is working on those tasks. Done means the tasks are completed, and there can be other stages also. So for example, in review, if the task is development is complete and it's ready for an SME to review, etc. Right? So we can have additional columns as well. Tasks or work items are represented by cards which are moved across the board as they progress through the stages. The Kanban method helps team visualize their work, limit work in progress and improve flow. It originated in manufacturing but has been widely adopted in software development and other fields for its flexibility and effectiveness in managing tasks and improving efficiency. So let's see first how to set up a Kanban board. So to create a board, either we can use a physical board, right, or we can have some digital platforms also available. So for example, we have few digital platforms like Trello, Jira, etc. right? Or we can just simply use a whiteboard and we can just put some sticky notes also, right? So the very first thing is define your workflow, identify the stages of your process, and like I said, to do tasks, in progress tasks, in review tasks and done tasks, right? So we can have those columns. I mean, these are the different stages we will encounter within our process, and then we can of course customize these stages. Then we need to of course create the task cards. For each task, create a card that it should include a brief description, only one liner, sometimes just a headline title, any relevant details like what is the due date, who is the assignee, or any link if it is a digital dashboard, and then priority level if applicable. Mostly it is applicable that what is the priority of that task. And then we need to set work in progress limits, decides on limit for how many tasks can be in the certain stages at one time. So for example, given a time, a maximum of 3 tasks it can be in progress state, right? Because we also need to make sure that there is a progress, right, in the work item. There is a progress. And then of course we need to use the board regularly. Make it a habit to update the board regularly. We sometimes have the stand-up calls also, like for example 15 to 20 minutes call where all the team members will join that call, will explain, okay, this is the task which is in which was in to do yesterday, and now I started working on it, so that's why it moved to in progress state, something like that. And move tasks as their status changes, and hold regular meetings like daily stand-up to discuss progress and challenges. Reflect and adapt. Periodically review your workflow and make adjustments as necessary. This might involve changing stages, adjusting work in progress limits, or redefining how tasks are managed. And this is just a sample how it will look if you are using a digital platform, or even if you are using sticky notes on the whiteboard. That is fine. So what we just learned that we can have different columns. So for example, to do column, in progress column, review column, done column. There can be some customized columns as well. And consider these cards are nothing but the tasks which team is going to work on. So for example, somebody is working on some UX design, another person is working on the backend functionality work, right? These multiple tasks, right? So on this board, there will be the whole team will have those cards, and then they will change the so for example, yesterday this task D was in to do state, and the person has worked on it, so now it should be in progress state. So while in the stand-up call, or maybe previous to that, the person will change the status. If it is a physical board, the sticky note, he will just pick this sticky note from here, will paste it here, right? And if it is a digital dashboard, then we have workflows available. We just change the status from to do to in progress or any of the applicable. So this is how we manage the Kanban board using the various type of cards. Let's see few tips for effectiveness of Kanban. First thing is keep it visual, because visual means it will be interactive. Use colors or tags for priority labels. Tags are nothing but if we are using the digital dashboard, then those platforms provide tags feature. So for example, something should be available for some review, right? So we can just tag that card with the review tag, right? So we can create tags also if we are using any digital platform. For example, in Trello, etc., we have use colors or tags for priority levels, types of tasks or team members. Stay flexible, adapt the board as your team's needs evolve, right? And involve the team members. Get input from all team members to ensure the board meets everyone's needs. Now, since we know about Kanban, let's see the key principles of Kanban. First thing is, of course, visualize the workflow. Use a Kanban board, either physical or digital, to visualize the workflow. Each task is represented as a card, and the board is divided into columns that represent different stages of the process. To do in progress, set done. Limit work in progress. Set limits on the number of tasks that can be in progress or at any time. One time, this helps to reduce the bottlenecks, maintain focus, and improve overall flow. Focus on flow. Monitor the flow of tasks through the system. The goal is to ensure smooth transition between stages, minimizing delays and improving efficiency. On continuous improvement, encourage a culture of continuous improvement, often referred to as Kaizen. Regularly assess the process, identify areas for enhancement, and implement changes to optimize performance. Let's see a few benefits of Kanban. So sometimes people call it as Kanban. So either way. Okay, flexibility, easily adapt to changing priorities and workload. Provides a clear visual representation of work status, making it easy for teams to see what is being worked on and what is next. Efficiency, helps identify bottlenecks and inefficiencies, leading to improved workflow and productivity. Focus on value, emphasizes delivering value to customers through continuous improvement and responsiveness to needs. So in summary, Kanban or Kanban is widely applicable across various domains such as software development, project management, customer support, personal task management as well, right? It is particularly effective in environments where work is unpredictable and priorities can change frequently. Kanban is a powerful method for visualizing work, managing flow, and fostering a culture of continuous improvement, making it a popular choice for teams aiming to enhance productivity and collaboration. Now we have learned Scrum and Kanban. Let's see what is the difference. So this tabular format I just put in so that we can see all the differences or align what is changed between Kanban and Scrum. So framework type, it's continuous flow and it's iterative and increment flow, right? We have visualization here, and Scrum is basically organizing the work into fixed length sprints. So like 1, 2, 4 is sprints, right? In Kanban, we do not have any defined roles, whereas in Scrum we have defined roles. We have product owner, Scrum master, development team, etc. And work in progress limits, yes, of course we have the limit on work in progress, whereas there is no restriction of work in progress items limits. There is no such restriction. Planning perspective, continuous planning is needed in this Kanban, whereas in Scrum, sprint planning at the start of each sprint, that is needed. Change management, changes can be made at any time. right? Anytime. So usually that's why Kanban is also used for, so for example, if there is any production issue, there is a production issue L1, L2, L3 support fixing team. So there that is also one of the use case where we should use, or we can use Kanban, because anytime if there is a production issue coming, that ticket should be taken by the team to work upon. So that is not a good use case for Scrum team, because Scrum work is already decided before the sprint starts, right? In Scrum, changes are generally not allowed during a sprint. So yes, time frame, no fixed time frame. Tasks are completed as capacity allows, and in Scrum we have fixed time frame, which is a sprint, typically 1 to 4 weeks. Meetings, minimal required meetings, ad hoc discussions, whereas in Scrum, regular ceremonies, sprint planning, daily stand-up, sprint reviews, sprint retrospective, all those ceremonies happen. Focus, continuous delivery and flow optimization is the focus of Kanban, whereas for Scrum, delivering a potentially shippable product, and we call it as PSP, increment at the end of each sprint. And PSP is nothing but that product which we are building in 1 to 4 weeks of time. That itself is a component which can work individually, right? Adaptability, highly adaptable, easy to implement changes, and Scrum is more structured. Changes require more planning and can disrupt sprints if there is anything which is coming in between. Now let's see, since we have learned Agile, let's see what are the advantages of Agile framework. Rapid delivery. Frequent releases provide users with early access to features and improvements, right? 1 to 4 week of sprint, for example, if we talk about Scrum, right? Within a few weeks we are releasing those new features or fixes to the production environment. So it's a rapid delivery. Increased collaboration, continuous interaction with stakeholders leads to better alignment with user needs. So within Scrum, so for example, we do those show and tell session, we get the feedback before we put that feature on the production environment. We show it to client, see this is what we have built, is it working fine? We take the feedback and then sometimes we improve those things, right? So the collaboration is increasing with the stakeholders. Higher quality, regular testing and feedback help identify issues early, resulting in improved product quality. Yeah, this is self-explanatory. Let's see a few disadvantages of Agile framework. First one is less predictability. Project timelines and budgets can be harder to estimate due to the iterative nature of Agile, right? So someone says like, can you give me estimate of this project right away? So it's not predictable. Requires a discipline. Teams must be well organized and committed to regular communication and collaboration. So idle people are actually not needed in Agile framework, because I mean the lesser duration, consider we just have 1 week of a sprint. So within 1 week we need to make sure we push this change to production, right? If people are just sitting idle on the item, of course that won't be a successful release. So we need discipline. Risk of scope creep. Frequent changes and additions can lead to project scope expanding beyond original intentions. So here actually the main role of Scrum Master comes into picture, where this person should be should explain, should be a little bit stubborn as well, that we cannot introduce any item during the sprint, for example, right? So concluding, the Agile model is well suited for projects in dynamic environments where requirements may evolve. It fosters collaboration, adaptability, and continuous improvement, making it a popular choice in software development today. Yeah, this is one of the, I mean, most of the job descriptions would have this as one of the JD. The person should know Agile. The next one is DevOps model. Let's see what it is. The DevOps model is an approach to software development that emphasizes collaboration between development team or dev team and operations team, ops team, and that's why it's DevOps. It aims to shorten the software development lifecycle while ensuring high quality and continuous delivery of software. So these people, right, the development team, operations team, I mean the people who are going to deploy that code to production environment. Those are the operations team members, by the way. So they are working together in a collaborative manner. Developers are fixing it, developers are developing it, pushing it to the environment, and then operation team, they are just deploying it. Let's see key components of this model. The very first thing is, of course, collaboration. DevOps fosters a culture of collaboration between developers, operations, and other stakeholders, breaking down silos and encouraging open communication. You cannot keep hot potatoes in your hand. You have something to speak about, just speak. You need to inform team members that, okay, I'm blocked because of this issue, or maybe another party is not responding, right? There is another integration you need to do. You are not getting response from the DBA, right? So the collaboration is first thing. Automation of processes such as testing, deployment, and infrastructure management is a core principle. This helps reduce manual error and speed up delivery. I mean, nowadays, this automation, right? Whether it's testing automation or deployment automation is a must for anything. Consider a scenario where we are working in this DevOps activity, right? And we have a huge application to be tested, and every time we are releasing a new feature, and then we need to do this testing again. Manual testing. And then it will take a lots of effort. And of course, with manual effort, we might miss something. So automation is needed. Continuous integration. Developers frequently integrate their code changes into a shared repository. Automated builds and tests are run to identify issues early. Now consider a scenario. We have different teams, a common repository, and different teams are working for different features. And if we do not have automation build, whether it's automation build, automated build, or automated test, what will happen? Multiple teams are pushing their code, and end of the day, we are not sure if the code is working fine or not, if the build is successful or not, and then finally the test cases are breaking. So for this model, for DevOps model, we surely need automated builds. As soon as people check in their code to the repository, automatically the build will start. We'll see if there is any compilation level error, etc. And then automated test, those test cases should also be executed. Then only this model will work. Continuous delivery. The goal is to ensure that code changes can be automatically deployed to production at any time. This involves rigorous testing and validation processes, monitoring and feedback. Continuous monitoring of applications and infrastructure provides real-time insights into performance and user experience. Feedback loops help teams quickly identify and resolve issues. Infrastructure as a code, IAC. This practice involves managing infrastructure through code and automation, allowing for consistent and repeatable environments. Now let's see a few benefits of DevOps model. So first benefit is, of course, faster time to market. By streamlining processes and enhancing collaboration, teams can deliver new features and updates more quickly. Improved quality. Continuous testing and monitoring help catch bugs and performance issues early, leading to higher quality releases. Greater efficiency. Automation reduces manual tasks, allowing teams to focus on more strategic initiatives. So for example, there can be some improvement on your website. So we are receiving some feedback. We are putting some innovations around the solution. We can put more automation around something else. Maybe some approval process. Maybe the content which we are putting on our website needs some approval, some business approval, some legal approval. How can we automate that process, right? So think of something else which will add some value to our portal. So team can think of that. Enhanced customer satisfaction, faster delivery of features and quicker responses to issues lead to improved user experiences. So these are the benefits. Let's conclude it. The DevOps model represents a cultural shift in how software is developed and delivered. By integrating development and operations, organizations can achieve greater agility, improve collaboration, and respond more effectively to market demands. Now let's understand the another agile model, which is rapid application development model. Rapid application development, or RAD, is a software development methodology that emphasizes quick development and iteration of prototypes over a rigorous planning and testing. This approach is designed to provide fast delivery of high quality software by using a combination of pre-built components and user feedback throughout the development process. Let's see the key features of RAD model. So user involvement. RAD relies heavily on user feedback and active participation throughout the development cycle, ensuring that the final product meets user needs. So user involvement is needed. Then prototyping. Instead of waiting for the complete system to be built, RAD encourages creating prototypes or partial implementations that can be tested and refined based on user input. And actually that is a crux of agile methodology. Create small product. So for example, in terms of Scrum, we used to call it as PSP, right? The shippable product, right? And then validate them instead of like building the whole thing as once, right? Create small deliverables and then validate and then put it on production. So here also the same concept is there, but we are calling it as prototyping. The next one is iterative development. So that is also one of the feature of agile model, agile methodologies, iterative development. The development process is iterative, allowing for continuous refinement and enhancements. Each iteration can lead to a more polished product. RAD aims to reduce development time significantly, allowing organizations to deliver applications faster compared to traditional methodologies. And RAD often employs various tools and techniques such as visual programming to streamline the development process. Let's see the phases of RAD model. Okay, so these are the phases: requirements planning. Initial requirements are gathered from users and stakeholders to outline what the application needs to achieve. That is like requirement gathering and planning. User design. Users collaborate with the developers to create prototypes. This phase focuses on designing user interfaces and experiences. UX, sometimes we call them as UX design. Construction. Developers create the actual application, often using high-level programming tools and techniques. Prototypes are continuously refined based on user feedback. Cutover. The final application is deployed. This phase may include final testing, user training, and data conversion. Now let's see the advantages of RAD model. Speed. RAD allows for rapid development, which we have seen, which is ideal for projects with tight deadlines or changing requirements. Flexibility. The iterative nature of RAD enables developers to adapt to changes and feedback quickly. User-centric. By involving user throughout the development process, RAD helps ensure that the end product meets user expectations. Reduced risk. Continuous testing and prototyping help identify and address potential issues early in the development process. Now let's see what are the disadvantages of this. Limited scalability. RAD may not be suitable for very large projects due to its reliance on user involvement and rapid iteration. It requires strong collaboration. Effective communication and collaboration among users and developers are crucial for RAD to succeed. Yeah, it's not like team is just sitting on one task and thinking, okay, today I'm not in mood, maybe I will work tomorrow. Okay, potential for incomplete requirements. Rapid iterations might lead to overlooking some requirements, especially if user feedback is not adequately captured. That is also one of the important thing here. Okay, this model, that is rapid application development, is a valuable methodology for projects that require quick turnaround and high user involvement. By focusing on prototyping and iterative feedback, RAD helps deliver functional applications that align closely with user needs, making it a popular choice in dynamic environments. So far we have covered traditional models, then we covered agile models. Now we will learn the modern and hybrid models. And these models we are going to cover: spiral model, feature driven development or FDD model, lean software development model, pod model. So the first one is spiral model. The spiral model is a software development process that combines iterative development with the systematic aspect of the waterfall model. It is particularly useful for large, complex and high-risk projects. The model emphasizes risk assessment and mitigation throughout the development lifecycle. So it's a traditional, so there was a traditional approach, there is a agile, and then now this is like taking some features of waterfall model, the traditional one, and some features of agile one, right? Basically good features, not bad features. So let's see the features of spiral model. First one is iterative process. The spiral model allows for multiple iterations or spirals. So in Scrum we used to call it sprint. Here we will call it as spirals of development, enabling teams to refine and enhance the product over time. Risk management. Each phase includes a thorough risk assessment, allowing teams to identify and address potential issues early in the development process. Customer feedback. Regular customer involvement ensures that the evolving product meets user needs and expectations. Flexible and adaptive. The model accommodates changes in requirements even late in the development process, making it suitable for dynamic projects. Now let's see the phases of spiral model. Planning. Identify objectives, alternatives and constraints. Define the project scope and gather requirements. That is planning phase. Risk analysis. Evaluate risk associated with the project. This may involve creating prototypes or conducting feasibility studies to assess technical and operational risks. Engineering. Develop the software incrementally, implementing features based on the prioritized requirements. This phase includes design, coding or testing. So to be true, if we see, right, the naming conventions have changed in these models. So for example, instead of we are saying different phases of design, coding and testing, we have already seen in waterfall model, right? Now we are calling this as an engineering phase, which is a combination of those phases, right? So some terminologies have changed, and what these models are trying, they are trying to get the best of features available in existing models and trying to improve them. So that is the whole thing which is happening in these models. And why it is crucial to know all these terminologies, because when we are working for a team and the project use any of a specific model and we do not know the terminology, it will become more confusing. What is the meaning of engineering, right? Then evaluation. Review the project progress and gather feedback from stakeholders. This helps determine whether to proceed to the next spiral, make adjustments or pivot the project direction. And repeat. The process is repeat for multiple iterations, refining the product and addressing any new risk or requirements identified during evaluation. So I mean, since it's an iterative model, right? So of course there will be a repetition. Let's see the advantages of a spiral model. So the first one is effective risk management. Continuous risk assessment helps prevent major issues before they arise. So risk management is like a continuous phase. That's why it's one of the advantage. Customer satisfaction. Regular feedback loops with clients ensure that the product aligns with their needs and expectations. Flexibility. The model's iterative nature allows for adjustments based on evolving requirements. Let's see the disadvantages of this model. Complexity. The model can be more complex to manage compared to linear models, requiring careful planning and coordination. And to be true, even if it is a linear model, which is not advisable at all. So for example, waterfall model, there also we need planning. There also it will become complex if the planning is not done properly, right? So this is applicable for any of the model, the complexity, right? Cost. Yes, this can be a factor due to its iterative nature and the need for ongoing risk assessments. It may be more expensive than other models. So let's conclude the spiral model. The spiral model is particularly suited for projects where requirements are uncertain or subject to change. Its focus on risk management and customer involvement makes it an effective approach for delivering high quality software solutions in complex environments. Now this one is feature driven development model or FDD model. Feature driven development or FDD is an iterative and incremental software development methodology that emphasizes the design and building of features. It is particularly suited for larger scale projects and focuses on delivering tangible working software in short time frames. So again, to notice, this is also iterative. Okay, so means smaller increments will go, smaller functionalities will be built and will be released. Let's see the key characteristics of FDD. Feature centric approach. The core of FDD is its focus on features, which are small client valued functions that can be designed, built and tested independently. Each feature typically represents a specific piece of functionality. So for example, login functionality, registration functionality, right, any newsletter functionality. So these are the features which are small and of course that can be designed, built and tested independently. Model driven. FDD begins with building a model of the system which is then used to guide development. This model helps ensure that all stakeholders have a shared understanding of the system. Iterative and incremental. Development occurs in short iterations, usually 2 weeks, where a set of features is designed and implemented. So this allows teams to respond to changes and continuously improve the software. So kind of Scrum. Regular builds. FDD promotes frequent builds, ensuring that the software is always in a working state. This helps identify issues early and maintains a high quality of code. So kind of Scrum only. All features are like, for example, increment, delivery, iterative in nature, regular builds. Kind of DevOps model is also introduced here, right? Because of course the dev team and ops team, they need to work close. So like I said, in all these models, right, what we are doing is we are taking some good features of one model, good features of another model, renaming it as another model. That is, in a nutshell, we have done. Let's see the phases of feature driven development model. Okay, develop an overall model. The team collaborates to create a high level model of the system that outlines its structure and functionality. Build a feature list. A comprehensive list of features is created based on client requirements and the overall model. Each feature is typically a small specific piece of functionality. Like I said, maybe a login functionality or registration functionality. Plan by feature. The features are prioritized and planned for implementation in a series of iterations. So for example, my web application is having login feature, that is login feature, sign up feature, newsletter feature, right? So priority wise, which one will come first? First sign up will happen, so registration will become the first feature, then login should happen, login will become the second feature, and so on. Design by feature. For each feature, detailed design work is performed, ensuring that it meets the requirements and fits within the overall architecture. Build by feature. The development team implements the feature, conducts testing and integrates it into the existing system. Let's see the advantages of FDD. So first advantage is customer centric. By focusing on delivering features that provide value to clients, FDD aligns development closely with user needs. Predictability. The structured approach with defined phases helps in better planning and predictability of timelines. Enhanced quality. Regular builds and testing throughout the development process lead to higher quality software. Team collaboration. FDD promotes collaboration among team members, fostering a shared understanding of the project. So these are the Advantages of FDD model. So let's see the disadvantages also. Okay, the first one, requires experienced team. And to be true, this is not a disadvantage. We always need experienced people, innovative people in our team, right? Okay, FDD works best with experienced team that can handle the complexity of feature based development, right? So we need experienced team. So for example, consider there is a development of any of the project, and we are using waterfall model. This project is of 6 months, people are working on this project. It's okay, sometime if someone is not feeling good, maybe today, he can work tomorrow, right? But whereas such type of model where we need active people, experienced people all the time, because the duration of the sprint, or whether it's a sprint or any of the model we are using, just 1 or 2 weeks, we need to complete the whole functionality. We need experienced people, right? We need experienced team. Okay, less flexibility for changes. While FDD allows for changes, the structured nature can make it less adaptable compared to more agile methodologies. Initial overhead. The upfront effort to create a comprehensive model and feature list can be time consuming. So in conclusion, FDD, or feature driven development, is an effective methodology for managing complex software projects, particularly where features play a critical role in delivering value to users. Its structured approach, combined with an emphasis on iterative development and regular feedback, helps teams deliver high quality software that meets client expectations. Now, this model is lean software development model. Lean software development is an agile methodology derived from lean manufacturing principles and practices, aiming to optimize efficiency and minimize waste in the software development process. It emphasizes delivering maximum value to customers while using the least amount of resource. Let's see the key principles of lean software development. Eliminate waste. Focus on identifying and removing anything that does not add value to the customer, such as unnecessary features, documentation, and processes. Build quality. Quality should be integrated into development process from the start. This involves practices like continuous testing and validation to ensure that defects are caught early. Create knowledge. Emphasizes the importance of learning and adapting. Teams should continuously seek to improve their processes and products through experiment and feedback. Yeah, and defer commitment. Decisions should be made as late as possible, allowing teams to gather more information and reduce uncertainty before committing to a course of action. Deliver fast. Focus on delivering small incremental releases to provide value to customers quickly. This allows for faster feedback and the ability to adjust based on customer input. That's why it is using the agile methodology. Respect people. Lean development recognizes that people are the most important asset. It encourages teamwork, collaboration, and respect for all team members. I really like this one, right? People matter first, the health matter first. All these models are, I think, the second aspect. Anyways, optimize the whole instead of optimizing individual components. The entire value stream should be considered. This means looking at how different parts of the process interact and ensuring that the whole system is efficient. Let's see what are the lean practices. Value stream mapping, a technique to visualize the flow of information and materials required to bring a product to the customer, helping identify waste. Okay. Second is continuous improvement or Kaizen, culture of ongoing improvement where teams regularly evaluate their processes and make incremental changes for better efficiency. Pull systems, instead of pushing work through the system, lean practices advocate for a pull system where work is pulled based on demand, reducing overproduction. Rapid prototyping, quickly creating mock-ups or prototypes to gather feedback and iterate on design, minimizing the risk of developing unwanted features. Let's see the benefits of lean software development. So first one is increased efficiency. By eliminating waste, teams can focus on what truly matters, leading to faster delivering times. Higher quality, building quality into the process reduces defects and improve overall product quality. Greater flexibility, lean principles allow teams to adapt quickly to change requirements and customer needs. And enhanced collaboration, emphasizing teamwork and respect, foster a positive work environment and encourages knowledge sharing. Now let's see the challenges of lean software development. First one is cultural shift. Transitioning to lean practices may require a significant cultural change within an organization, which can be difficult to achieve. Initial investment, time and resources may be needed upfront to train teams and implement lean practices effectively. And then balancing speed and quality. While delivering quickly is a priority, maintaining quality standards, of course, it's essential, and finding the right balance can be challenging. And concluding, lean software development provides a framework for improving efficiency and delivering value in software projects. By focusing on waste reduction, quality, and continuous improvement, teams can enhance their processes and better meet customer needs. It's a flexible methodology that can be adapted to various types of projects, making it a valuable approach in today's fast-paced development environments. So this is pod model. Let's see what it provides. Pod model is the pod model project-oriented development is a software development approach that emphasizes organizing teams around specific projects or products rather than functional areas. Let's see the key features of this model. Team structure. Teams are composed of cross-functional members including developers, designers, testers, project managers who work collaboratively on a specific project. So for example, we have a bigger enterprise and then we are working for different projects for that enterprise. So for different projects we will have different teams, different pods. Each pod will have a developer, a designer, tester, project manager, business analyst, okay, and they will work together collaboratively on that specific project. Second is project focus. Each team is dedicated to a particular project, allowing them to concentrate on its specific requirements, goals and timelines. Flexibility and agility. The pod model encourages adaptive planning and responsiveness to change, making it suitable for dynamic project environments. Ownership. Team members take ownership of their project, leading to increased accountability and motivation. Faster delivery. By having a dedicated team, projects can progress more rapidly as team members can make decisions quickly without waiting for approval from multiple departments. So for example, there are multiple departments, right? And this team is formed for one department. Since there is no impact of this department to another department, this team can take decision among themselves and then can provide faster delivery. Enhanced communication. Close collaboration among team members facilitates better communication and reduces misunderstandings, resulting in higher quality outcomes. And sometimes in this model, even from the client side, there will be a specific SPOC, specific project manager from the client side. The pod team is going to interact with that manager or the architect. They are going to work together and they are just focused on that particular department to which they are working on. So that's why the delivery will be more faster. Now let's see the benefits of this model. First one is of course improved collaboration. Cross-functional teams foster a collaborative environment. They will work together within a team we will have all those cross-functional people, be it developer, front-end developer, back-end developer, content authors, etc., and they are working together to complete that project. And sometimes, I mean, within a model, we have combination of different models. So for example, we have pod, we are following pod method, but we are also using features of Scrum or features of Kanban. So that is also possible. I mean, we can always tailor a specific model. Faster time to market, projects can be completed more quickly due to focused efforts. Higher quality, direct involvement of all necessary skills leads to better quality assurance. Greater adaptability, teams can quickly pivot in responses to project needs or client feedbacks, right? And then of course the development team, they fix it, they work with the DevOps team, and then they push the changes to the higher environment. So what I am saying that though it's pod model, but we are also maybe using the Scrum features, but we are also using the features of Kanban model, and we are also using the features of DevOps model. So it is always tailored. It is not fixed to one model, SDLC model. We can always bring the best features of various models available, and then can create our own tailored model. Let's see the use case of pod model. Pod model is particularly beneficial in industries where projects are varied and need tailored solutions, such as software development, marketing campaigns, product launches. It allows organizations to leverage specialized teams for each project while maintaining flexibility and speed in delivery. Overall, the pod model helps organizations effectively manage complex projects by fostering teamwork, accountability, and adaptability. Okay, let's see the summary of all traditional models. So we covered waterfall model, V model, and incremental model, right? So waterfall model is a linear approach where each phase must be completed before the next begins, right? That is waterfall model. V model, an extension to the waterfall model, emphasizing verification and validation, that we have covered. So each phase of the development is having corresponding testing phase. So it is giving more stress on the testing. Incremental model develops a system in increments, allowing parts to be deployed as they are completed. So kind of agile they have brought in here. Okay, advantages of waterfall model: it's simple to understand, clear documentation. V model ensures thorough testing, clear project timelines, milestones, right? Thorough testing is more stress on testing for sure. And incremental model allows partial implementation. Feedback can be incorporated because it is delivering in increments. Waterfall model disadvantages are inflexible to changes. Late testing can lead to discovering flaws too late. All right, we cannot go back to the previous phase and do something. Okay, V model, inflexible changes can be costly late in the process, and the incremental model, integrations can be challenging. Incomplete systems may confuse stakeholders. Let's see the summary of agile models. So we covered agile model, DevOps model, and RAD model. Agile model is an iterative approach focusing on collaboration, customer feedback, and rapid releases. So it's iterative in nature, right? We covered Scrum and Kanban. We can create sprints, etc., right? DevOps model combines software development and IT operations to shorten the development lifecycle, and RAD model focuses on rapid prototyping, small features, and quick feedback from end users. Agile model advantages: it's highly adaptive, encourages customer involvement, frequent delivery. Advantages for DevOps model: faster delivery, improved collaboration between teams, increased deployment frequency. And RAD model: faster development, encourages user feedback. Disadvantages of these models are: for agile model, it requires constant collaboration. That is not actually a disadvantage, but of course, few people might think it's a disadvantage. Okay, can be challenging to manage scope and timelines. For DevOps model, it requires cultural change and collaboration between previously siloed teams. For RAD model, may compromise quality if time is too short, requires active user involvement. Now let's see the summary of modern and hybrid models. So we cover these models: spiral model, feature-driven model, feature-driven development or FDD model, lean software development model, or pod model. Spiral model combines iterative development with systematic aspects of the waterfall model, emphasizing risk. A feature-driven development model, an incremental model-driven approach focusing on delivering tangible features. Lean software development model emphasizes efficiency and waste reduction, delivering value by streamlining processes. And pod model organizes team around specific projects or products, promoting cross-functional collaboration. Advantages of spiral models are: it focuses on risk management, allows for refinement of project details. Advantages for FDD models are: it's clear focus on features, promotes regular delivery and customer satisfaction. For lean software development, the advantages are: reduce waste, encourages continuous improvement. And for pod model, advantages are: it improves collaboration, faster delivery, adaptable to project needs. Disadvantages for spiral model: it can be complex to manage, requires expertise in risk management. For FDD model, the disadvantages could be: it requires a well-defined scope, may not suit projects with rapidly changing needs. For lean software development, disadvantage could be: it can overlook essential features if too much focus is placed on efficiency. And for pod model, it can lead to resource duplication, may create silos if not managed properly. Let's understand what is coupling. This is also one of our key topic in software engineering. Coupling means pairing of items. Likewise, we say couple, right? Couple, two people they talk to each other, they like each other, they are in love, right? They are couples. Similar to that. Coupling in software architecture refers to the degree of interdependence between software modules or components, how much they are dependent on each other. I mean, for example, there are two modules, how much they are dependent on each other, that is called coupling. So for example, in layman language, husband is dependent on wife or vice versa, right? So that way, coupling. In software module, it's like those modules are dependent on each other. It describes how closely connected these modules are and how much they rely on each other to function. So for example, unless you clean the dishes, I will not prepare lunch, right? So wife says to husband, right? So they are dependent on each other, correct? I mean, that type of coupling, we can just take an example of that, right? So one module is dependent on on the other one, and they rely on each other. That is, let's see the types of coupling. So we have tight coupling, loose coupling. Tight coupling means components are highly dependent on each other. Unless you clean the dishes, I won't prepare the food at all. Tight coupling: changes in one module often requires changes in another also. So they are tightly coupled. Loose coupling means components are independent and interact through well-defined interfaces or API, but they are independent. Changes in one module are less likely to impact others. It means loose coupling. They are not dependent on each other, right? So in human life, tight coupling is good, right? We of course we are dependent on each other, right? That is how this whole work. Let's understand this concept again in fun way. What I'm talking about. Imagine two neighbors, right? Alice and Bob, and who are planning a block party together. They decide that Alice will handle the decoration while Bob will manage the food. Suppose Alice picks a specific color for decoration that directly influences the types of food Bob can prepare. For example, a color themed menu. If Alice changes her mind, Bob's entire plan might fail apart, requiring him to start from scratch. It's tight coupling. They are dependent on each other. So one, or based on one's decision or one's change in the planned activity will totally impact the other one's plan. So it's tight coupling. Let's see the importance of coupling. Maintainability. Loose coupling makes it easier to update or replace components without affecting the entire system. So we need loose coupling. That is a key thing. We need loose coupling. Loose coupling is required. Scalability. Systems with loosely coupled components can be scaled more easily, as individual components can be modified or duplicated as needed, right? Testability. Loose coupling allows for easier testing of individual components in isolation. So for example, there are different modules we have in our application, right? And something is changed in one module. We just need to validate that module because it will not impact the other module's functionality. We know that this is loosely coupled. Now another key concept is cohesion. Cohesive in nature. Coupling is one thing, another one is cohesion. What is cohesion? Let's understand. Cohesion in software engineering refers to the degree to which the elements within a module or components belong together. It measures how closely related and focused the responsibilities of a single module are. High cohesion is a desirable attribute, as it indicates that a module or component performs a single well-defined task. Little bit confusing because coupling is when we have different modules, we are saying how one module is not relying on another module. That is loosely coupled. Now in cohesion, what we are saying, within a single module, we have different elements, right? How those elements are capable to complete the whole requirement and can perform as a single well-defined task. That is called cohesion. So if a particular module is not dependent on another module, it means it's loosely coupled, as well as it is highly cohesive, because that module is self-sufficient to complete the whole task, right? Because the elements within this module, they are able to complete the whole task, so it's highly cohesive. So what we want eventually, loose coupling and high cohesiveness. Loose coupling and high cohesiveness. So that is what it says. High cohesion is a desirable attribute, as it indicates that a module or component performs a single well-defined task. Let's understand this also as fun way. Imagine a family unit. Parents and children all working together for a common purpose, like planning for a family vacation. A family project where a family is like a module. The whole family is a module, right? A family project where everyone is involved in preparing for a holiday. Each member has a specific task: booking tickets, packing bags, planning activities. Yet all tasks are closely related to the single goal of enjoying a vacation together. That is a single goal. We have different tasks. Those are different elements, and the module is this whole family. Okay. So module is equal to, the family is the module. Elements are the family members or the different tasks, and the final activity, the whole function would be that is a single goal is enjoying the family vacation, right? And they are able to, if they are able to achieve it within family, they don't need any other person, any neighbor's help, right, to achieve that goal. Then it's high cohesive family or high cohesive module. So there are types. Let's see the cohesion types. Coupling, we have already seen tight coupling and loose coupling. In cohesion, let's see what are the. So we have functional cohesion. It means all elements contribute to a single well-defined function or task. Functional cohesion, function or task. An example would be a function that calculates the total price of items in a shopping cart. That could be a function, right? So that is functional cohesion. Sequential cohesion, elements are connected in a sequence where the output of one part is the input to another, right? An example would be a function that reads data from a file, then processes it, and then saves the result. So it's like in sequence. We cannot process the file until we read the file. We cannot save the file unless we process the file, right? So this sequential process within module, it's happening. It's sequential cohesion. Then we have communicational cohesion. Elements operate on the same data set but perform different tasks. Example would be a module that reads a user profile and then updates it. Simple, right? Then we have procedural cohesion. Elements are grouped because they always follow a particular sequence of execution, a procedure, right? Process steps of doneness. Example, a function that performs multiple steps in a process, like a setup function, anything, right? But multiple steps of doneness. Temporal cohesion, elements are grouped by when they are executed, typically at the same time. And the example will be initialization function that run at the start of a program, right? So just to temporarily basis, but they are executed at the same time. Logical cohesion, elements are grouped logically, but they may not be related functionally. Example is a utility module that contains various unrelated functions, right? We have created a utility. What it will do, it will perform similar type of logic but totally unrelated. And then we have coincidental cohesion. Elements are grouped arbitrarily. There is a little or no relationship between them. An example is a module with a mix of unrelated functions and variables. Let's see the importance of cohesion. Maintainability. High cohesion makes it easier to understand, maintain, and update a module as its purpose is clear. So for example, a module is for a specific purpose and it's not dependent on other module, it's loosely coupled, as well as the elements within the module are capable to complete the whole task, high cohesive. So maintenance is also easy, right? If there is any change, it will just we just need to make sure that within module we test everything. So maintainability is easy. Reusability, modules with high cohesion are more likely to be reused in different contexts as they perform specific tasks. So for example, we have created a framework for utility, right? This utility or framework is kind of a module because what we want to do, we can just plug and play. We just need to install it somewhere and then it will start working. It doesn't dependent on something else, some other module, right? So we can reuse it again and again. So reusability factor will increase. Reliability, systems with highly cohesive components are often more reliable as they perform well-defined tasks with fewer unexpected behavior. I mean, we know that this module will work standalone utility, so we are less bothered that it will break. It should not break, right? Because we have already validated that earlier. Now let's see the summary of cohesion and coupling, and this is the table. So different aspects, cohesion and coupling. Definition, we know that cohesion, measure of how closely related and focused the responsibility of a single module are, that is cohesion, within the elements. Coupling is measure of the degree of interdependence between different modules, right? Cohesion within the module, coupling outside between different modules. High cohesive is desirable and low coupling is desirable. Cohesion focuses on internal relationship within a module, whereas coupling focuses on external relationship between different modules. Cohesion example that we have already seen, a module that handles all user related functionalities, registration, etc. Within those are the modules. Registration is a module, login is another module, profile management is another module, right? And coupling is a module that relies heavily on another module's internal function, is tightly coupled. Impact of change, if it is cohesive, change within the highly cohesive module have minimal impact on other module, and if it is coupling, change in one module may require changes in dependent module in a tightly coupled system. Design principles encourages modular design where components are focused on a single task, and for coupling encourages loose interactions to enhance system adaptability. An ideal scenario for cohesion is functions or classes working together towards a single purpose, and for coupling independently while interacting through well-defined interfaces. So in nutshell, the takeaway is we need high cohesive in module and we need loose coupling among modules. Let's learn this key term called solid. Solid is a set of 5 principles, SOLID 5, in object-oriented programming and design that aim to make software designs more understandable, flexible, and maintainable. The principles help developers create systems that are easier to manage and adapt over time. So these 5 principles, SOLID, and which basically the meaning of this S is single responsibility principle, or SRP. O stands for open closed principle. L stands for Liskov substitution principle, LSP. I stands for interface segregation principle, ISP. And D stands for dependency inversion principle, DIP. Let's learn about them one by one. So first one is single responsibility principle, SRP, and like it says, right, single responsibility. A class, let's take example of Java, right? A Java class should have only one reason to change, meaning it should only have one job or responsibility. This makes the class easier to understand and maintain. So for example, we have written a Java class file. That class should have only one responsibility, only one reason to change, right? There should not be more than one reason to change. That is one first principle. And let's see it is in the real time example. So consider this class. This class is user profile class, right? In this class we have these methods are there, right? Update profile method is there, send email notification method is there. So it violates SRP because it handles both user profile data, right? Here what we are doing is we are updating the user profile as well as we are sending notification. We have this send email notification. Now in what cases we need to change this this class? In what cases? If there is any change related to update profile, or if there is any change related to send email notification. What the definition says, a class should have only one reason to change, but in this case we have two reasons to change. One is the update profile, one is the sending email notification. So that's why it is breaking the SRP principle, which is single responsibility principle. Let's see how can we fix it. Now we see what we have done with SRP. We have refactored the earlier class by separating the responsibilities into two classes. So first class we have just notification service class, which will be responsible for sending email notification, whereas the other class, which is user profile class, is just responsible for update profile. So the segregation is there, and now we have just one reason to change these classes, which is like for update profile is user profile update, for notification email service email notification change. And here's the example how we might use these two separate classes. So for example, simply we have just created the object of user profile and we are using the method update profile. We are sending the information, where for notification email service we have just created an object of notification service and we are using this method, simple. Now the second principle, which is open close principle, OCP. Software entities, for example classes, modules or functions, should be open for extension but closed for modification. What does that mean? It means if we want to add some extension to it, then we should be able to add it. but that class should not be, we should not modify that should be closed. We should not modify the existing features. This means you should be able to add new functionalities without changing existing code, typically achieved through interfaces and inheritance. We will see that. Now consider this class, and I have just zoomed in this class so that it's more readable. Let's say we have a simple application that calculates the area of different shapes. So we have different shapes, circle, rectangle, etc., right? In this example, the area calculator class is not following the OCP, because if we want to add a new shape, for example triangle, so here just the implementation is there for circle and rectangle. For circle, what we are doing is whatever is the mathematics calculation of circle to calculate the area, we are added that logic here. For rectangle, another logic, right? So if in this example, if we want to add a new shape, for example triangle, then we have to modify the existing code, which is to update this area calculator class, correct? Now how can we fix it with OCP in our mind? So now let's refactor it to adhere to the open closed principle by using an interface and separate classes for each shape. So what we have done, we have created an interface which will calculate the area, okay, and now we have separate classes. Class circle will calculate the area of circle. What we have done, we have just implemented this interface shape, and we have overridden the method which is calculate area, and we are just overriding this method, passing the whatever is the mathematics calculation for circle. And similarly we have done this for rectangle, and now if you want to add it for anything, maybe if you want to add it for triangle, all we need to do is we will create a new class, implement this interface, and that's it. So no need, what we have done here, we are not updating the existing code. Existing code update is blocked, but we are adding new extension. The extension is calculation of triangle area, and we are just adding that logic. Now we can see if we want to add a new shape, right? If we want to add a new shape like a triangle, we simply create a new class. So new class means new extension we have added without modifying the existing code. We have just implemented the shape interface, and we have overridden the calculate area method. That's it. Hope it makes sense. This is the usage example. Finally, we, for example, within main class, I want to add triangle. I'll just create an object of shape and use the triangle, initialize the triangle class. That's it. Now the third principle, which is Lisco substitution principle, or LSP. Subtypes must be substitutable for their base types without affecting their correctness of the program. This ensures that derived classes extend the base class without changing its behavior. Now let's understand this with this example. So we have a class bird. Bird class is there, in which we have a fly method. Simple. Now we have two separate classes. Bird can be a sparrow, bird can be a penguin. Penguin is also a bird, right? Now if a sparrow extends bird, then it needs to override this fly method, correct? So it will happily override this method if needed, otherwise we'll just use this fly because a bird can fly. But in case of penguin cannot fly, right? So penguin cannot, if will override, then of course it needs to override, but we'll throw an exception that penguin cannot fly. So in this example, replacing a bird object with a penguin object, right, it will break the expected behavior, because which break violates the Lisco or this LSP principle, right? What it says, subtypes must be substitutable for their base type. Subtype is, in our case, is penguin, and that should be substitutable with bird without affecting the correctness of the program. So that is breaking. Now how do we fix it? So we have the bird class. So we need to refactor this code. So what we will do, we will have separate flying birds, non-flying birds. So in this example, we have one class which is a bird, and then we are using this abstract class flying bird, which is extending bird, right? And then it will have a method called fly, right? When sparrow wants to extend the, which class it needs to extend? Flying bird, because sparrow can fly, right? But when penguin wants to extend, doesn't need to extend the flying bird one, but the main class. So in this case, we can substitute the subclass with the parent class. So in this case, we can substitute penguin class with the bird class, right? We can substitute sparrow class with the flying bird class. Let's see how do we use it. So for example, I want to use sparrow, so I can just substitute flying sparrow with flying bird, right? The parent one. Whereas for penguin, I can use the parent one, which is bird, right? So now we are not violating LSP rule. The third principle is interface segregation principle, ISP. Clients should not be forced to depend on interfaces they do not use. This principle advocates for creating smaller specific interfaces rather than a large general purpose interface. And let's understand this principle using this example. So consider a single large interface for a machine learning that includes methods for various operations. Now in this example, simple printer is forced to implement methods which does not support, violating the interface segregation principle. So for example, this is the interface, right? Now this interface machine is having these methods: print document, scan document, fax document, and these are not methods needs to be overridden any class which is going to implement this interface, right? So for example, this one, multifunction printer, right? It is implementing this interface machine. Now this class, for this class which is a multifunction printer, it is only interested in this method, which is print document, right? Multifunction printer. So print document. No, sorry, actually this multifunction printer, right? It is utilizing all the methods. So it is happily overriding all the methods: print document, scan document, fax document, because it is multifunction printer. But whereas this class, simple printer, what it does, it just simply print the document, right? So but other methods, like for example scanning is not provided by this one. Fax documents is not provided by this one because it's a simple printer. So what is wrong here? This interface is having so many methods that those are forced to be implemented by the subclass which is implementing this interface. So that's why it's violating the ISP rule. Now let's see with the ISP. So to adhere to ISP, we can create smaller, more specific interfaces. Now we have created 3 interfaces. One interface, print document, simple printer, then scanner, then fax, simple. Wherever we want to use it, we just need to implement it. So for example, for multifunction printer, since we need all those methods, print document, scan document, fax document, we will implement all the interfaces, printer, scanner and fax. Whereas in simple printer case, we just need printer because we just want to use this method, print document. We can just implement this interface. And now finally, while using each class will just only implement the interface relevant to its functionality. So for example, I'm using printer, right, just for print documents, whereas if I want to use any of the specific one, scanning, or I can just use the multifunction printer object. So next principle is dependency inversion principle, DIP. High level modules should not depend on low level modules. Both should depend on abstraction. Means for example interfaces, right? Additionally, abstraction should not depend on details. Details should depend on abstractions. This principle helps reduce the coupling between different parts of system. Let's understand it. Consider this scenario, right? So what we have is an email service class and we have notification service class. This scenario where notification service, this service, right, is tightly coupled to email service, because we see this method is written send email, correct? So if you want to use the object of this class email service, and we use trigger this send email, it is tightly coupled, right? So if you want to change the notification method, then for example right now it's email, we want to change it to SMS, we need to modify the notification service class, right? Let's see how can we fix it. I mean, this is without DIP. Let's see how we should fix it. So to fix it, what we can do, we should introduce an abstraction, or we should say it as interface, that both the notification service as well as, and I mean any notification method can depend on. So for example, we can create email service, we can create SMS service, they both can implement this interface notification, and then this notification service, it will just invoke an abstract which is a generic method send, right? So this can be invoked whether it's email service, then it will have an implementation of email service. If it is SMS service, then it will just override this send method of this send of interface notification interface, right? So let's go back to the definition again. Let's understand what it says, and this time I think it should make more sense. High level modules should not depend on low level modules, right? Both should depend on abstraction. So in that case, abstraction, that interface we have, this one, the interface we have, the notification interface, right? Abstraction should not depend on details, means where this interface is not dependent on the implementation classes. Instead, implementation classes are actually dependent on the abstraction, right? So that is the principle, and that is how we can implement it. Now within this main method, what I am doing, if I want email service, I will just create object of notification will of type email service, and then I will just use this, right? If I want to use SMS service, then I will create object of type SMS service, and then I can use it. Same method I'm using with same interface but different implementation classes. Let's see the benefits of solid principles. Improved code quality, enhances readability and reduces complexity. Easier maintenance, simplifies the process of updating and modifying code. Better testability, makes it easier to test individual component of the system. Increased flexibility, allows developers to adapt and extend systems more easily without introducing bugs. Now we understood the solid principles, and this term comes software architecture. Let's see what is the relationship between these two. First thing is design foundations. Solid principles provide foundational guidelines for designing classes and modules within a software architecture, promoting a clean and manageable code base. Modularity, by encouraging single responsibilities and well-defined interfaces, Solid helps create modular systems. This modularity is crucial in architectural design, allowing for easier maintenance and scalability. Flexibility and extensibility. The open-closed principle and dependency inversion principle specifically foster an architecture that is flexible and can be extended without major rewrite. We just saw that, right? If you want to use SMS service, all we need to do is write a new implementation class, invoke the interface method, and then that's it. No need to change the existing interface or class. This is vital for adapting to new requirements or technologies. Reduction of coupling. Solid principles, specifically the dependency inversion principle, help reduce coupling between components. This is important in architecture as it promotes the independence of modules, making the system more robust and easier to change. And we have seen like these are the features through which using those principles we can achieve easily. Enhanced maintainability. Applying solid principles leads to designs that are easier to maintain and modify, which is a key consideration in software architecture, ensuring long-term sustainability of the system. Improved collaboration. By adhering to solid principles, teams can work more effectively on different components of an architecture as the clear structure and responsibilities reduce confusion and overlap. Now let's see the summary of solid principles. So while solid principles primarily address the design of individual classes and components, like the very low level we are going, they significantly influence the overall software architecture by promoting best practices that lead to clean, maintainable and scalable systems. Thus, understanding and applying solid principle is essential for creating effective software architecture. That is the key takeaway. What is software architecture? The IT people, right, they hear this term again and again, the architecture is good or not. What is this software architecture? We are going to learn software architecture principles, styles, etc. everything. Software architecture is like the blueprint of a building, but instead of bricks and beams, it focuses on how software systems are structured and how different parts work together. Believe me, I was talking to one of my friend, and then he said, you are an architect, and then he was relating my work that, okay, I know the architects, they build the design of the building, but what you really do you design that kind of architecture for software? But how it is even possible? So people still have, at least the non-IT people, they have this understanding that what is this architecture all about? And sometimes even in being in the IT, people have this issue to understand what is this architecture, what we do usually while we are pursuing any role related to architecture, etc. Right? Whether it is specific to particular domain or business or any type of application, but usually what we do, let's understand. So just as an architect designs the layout of a house, a software architect plans how an application will be built, right? We want to build a digital platform, whether it's a web application or an internal maybe just a system based application, right? This includes deciding what features it will have and how users will interact with it. Think of software as made up of different parts of components, like rooms in a house, right? Each room, or in software those are components, serves as a specific purpose, such as storing data, displaying information, processing tasks. Like in the house we have like kitchen, right? We have kitchen, we have bedroom, we have washroom, etc. The same way we have different components. One is for storing purpose, one is for displaying some information, processing some tasks, utility, etc. Just like rooms need doors and hallways to connect, software components need ways to communicate, right, with each other. The architecture outlines these connections, ensuring everything works smoothly together. They can talk to each other, they can communicate with each other. Software architecture provides guidelines for developers, telling them how to build each part so that they fit together correctly. It helps prevent problems later on, like having two rooms that are too small to fit in a piece of furniture, right? Similar to that. So basically, first design the whole blueprint of that software which is going to be built, and then the same information will be passed to the implementation team, and using that blueprint as a reference, they will start the implementation. Good architecture allows for changes. If you decide to add an extra room to your house, the design should accommodate that. Similarly, a well-structured software system can adapt to new features or changes in technology without needing a complete overhaul. I mean, it should not happen that, okay, oh, we need to have a new room. Let's demolish the whole building and now start with scratch, because there is no way we can build a new room. What we have architect so far. Now, software architecture refers to the high-level structure of a software system, encompassing the overall design and organization of its components and their interactions. It serves as a blueprint for both the system and the project developing it. Now, first let's understand few myths about software architecture, because most of the time I hear people are talking something about architecture, so there are some misconceptions. So let's clear what are those misconceptions. Okay, I have tried documenting all most of them. Of course, the count will be, I think, countless, right? Only for first myth, architecture is applicable only for large projects. That is a myth, of course. Even for a small project, we should do proper architecture, proper planning, etc. Documents should be created. Everything should be done. Second myth is architecture is just a documentation. I don't know. I mean, few people still think that architecture is all about just documentation. One size fits all. No. So there are different architecture styles. There are different framework, different patterns, and actually depends on what kind of requirement we have. On basis of requirement, the team decide, the architecture team, right? They decide which pattern, which style, which framework they should select. Sometimes it's business driven framework, maybe the existing enterprise we already using some framework which we should reutilize, or even the pattern, right? And sometimes if it is a project from the scratch, then it is on basis of experience and understanding what should be adapted for this type of requirement. Architecture is static. No, architecture is not static. It's dynamic and it changes as the phase goes on, whether it's implementation phase or maintenance phase. Any phase is going on, we come back, we change the architecture, we add more data to it. So we keep on adding improvements, enhanced. So we keep on enhancing the architecture. That is an ongoing practice. Good architecture eliminates bugs. That is not correct understanding, though up to some extent good architecture provides guidance to the implementation team so that we have a constant type of structure throughout, but it does not eliminate the bugs. To eliminate the bug, we need proper understanding of the requirement, then to write efficient code. I mean efficient in terms of optimized code, performative code. Then the quality assurance team, they should also make sure they properly validate the whole developed system, right? So all those things actually are responsible that we will have less amount of bugs. Non-technical stakeholders don't need to understand architecture. No, this is not true. All stakeholders are to be there to understand the architecture. They join the calls where the architect's responsibility to make them understand what is the architecture, what kind of architecture is going to be for this project, and we take sign off as well, right? Okay, this solution is going to be built, and these are the considerations we have taken. This is the everything. I mean everything is documented, right? And then proper approval and sign offs are taken from all the stakeholders. This one is funny. More complex means better architecture. No, this is not true. Sometimes even if it is a straightforward architecture and it is well suited for the problem we are solving, we are good, right? And why to make it complex? We always need an architecture which anyone can understand, right? So it's not true. Architecture is only about technology, and to be true, architecture is not dependent on technology at all, because at the time of architecture is the technology is not considered most of the time, right? Because architecture is not about technology. So for example, we are building a project and it's just maybe it can be developed in .NET or maybe it can be developed in Java. So it's not about technology. Good architecture guarantees success. No, not true. So the whole phases are responsible. Whole team is responsible for the success of the project. Architecture is all about tools. No, architects are just coders. No, this is not true. Architects are not coders. We have different teams for the implementation, right? Architects sometimes they provide some solution to the implementation team, some guidelines, but they altogether they are different roles. Implementation team, developers, technical leads, they are different roles. Architects, it's totally different role. Architecture is a one-time task. No, that is not true. It's an ongoing phase. If we are adapting any of the iterative models, so for example Agile, and then we know that we are going to accept more feedback, more evaluation will happen, more enhancements or bug fixes will come. Sometimes we go back to the architecture, we decide okay, this change we need in the architecture, right? And we do that change. So it's not one time task, it changes. This one is totally not correct. Architecture can be done at the end. No, not true. Architects know everything. Okay, this one is very funny. Okay, architects, it's not true. Actually, no one knows everything. That's why we have the cross-functional team, right? So that nothing can be worked in silos, right? We have different people for different expertise, and then we work together to complete the whole task. Architecture is only about high level design. No, we sometimes most of the time architecture is all about low level designing as well, different classes, components, etc. We just saw that. More documentation equals better architecture. Not true. Architecture is just about code quality. Absolutely not. Architecture is only relevant during initial development. Like I said earlier, no, it's not true. If we are getting enhancements, maybe it's an iterative model. So that time also we relook the architecture if something needs to be changed, and after we need to take a sign off from the IT team, etc. So those things we take care. And few more we have. You only need one architect. No, we have different flavors of the architecture. We have different roles within architecture. We have enterprise architect, we have data architect, business architect, application architect. We have so many architects. Sometimes we need for one type of role only. For example, in data, we need maybe more than one architect, data architects, because we know this application is going to be extensive for data related technologies, and we need peer reviews as well. So sometimes we need more domain architects. Architecture is the same as design. No, you can't change architecture once set. Of course not. It's like an ongoing phase. Like I said, architecture is just for developers. No, all architectural decisions are technical. All architects have the same skill set. No, architects work alone in silos. That's completely wrong statement. And I hope these myths you have found interesting. Made you maybe laugh as well, like I am doing right now. Okay, let's move on. Let's see the key elements of a software architecture, and these are the key elements. There are many, but these are the key elements. Structure of the architecture, and then we have architecture styles and design patterns. We have quality attributes. We will see technology stack. We will see the behavior, and we will also see the stakeholder needs within architecture. Then we do the architecture of a given problem. Then what kind of role stakeholders are going to provide. We will see all of them. So let's first understand structure. What is structure? Software architecture structure refers to the organization and arrangement of software components and their relationship within a system. I mean, what is the structure of that whole architecture? It defines how different parts of the software interact and work together to meet overall requirements. It defines the system's components, for example, modules, service layers, etc., and how they are organized. Outlines relationship and dependencies between components. So it is structure. So now let's see the key elements of structure. So first key element is components. What is component? And individual units of functionality within the system. So such as modules, services, or classes. Those are components. So example is if it is a web application, components might include user authentication, database access, user interface elements. Those are components. And we are discussing key elements structure. Okay. So first one is components. Second is layers. A way to organize components into distinct levels, each with specific role or responsibility. Layer. What layers we have? Presentation layer, business logic layer, database access layer. Presentation layer manages user interaction and displays data, UI components. So for example, presentation layer, when you access any of the web application, right? What we do? We open the browser, for example Chrome, we type in the URL, and then we access the website. That is the presentation layer which user can interact with. So all those UI components, the form component, the button, etc., everything is there. That is presentation layer. Business logic layer contains the core functionality and business rules. where the actual code is written. What will happen once the user clicking on the sign up button? What will happen once the user is filling up the form and clicking on login button? So there is a code written for that, which is interacting with the different services. Some integrations must be happening behind, some calculations must be happening behind. So everything that, all those aspects of business logic comes under business logic layer. And then we have data access layer. It handles interaction with data sources such as databases, external APIs. So whatever data we maintain, right, and how this access, etc., how we are storing that information to data, right, that comes in data access layer. The next element in the structure is interfaces. Interfaces are points of interaction between components, defining how they communicate with each other. So for example, we are developing a website which is going to interact with one external API, external system, and how we are interacting with that external system through REST-based APIs. So the external system has exposed some REST-based APIs. We just need to consume those APIs, and whatever data we get as part of response, maybe it's a JSON response, we just need to use that, right? So this interaction, right, interaction between components means one component is our application, another component is this external system. This interaction is happening, we call this handshaking, this interaction, as interface. Example, like I said, REST APIs, function calls, messages queues, etc., that facilitate data exchange. So those are interfaces. That is another key element that comes in structure. Then we have connectors, mechanisms that enable communication between components or layers. And types would be direct calls, messaging system, event driven system. So different connectors are available, right? For example, I want to fetch some information based on some event. I am clicking on some button, something is happening on my website, whether it's a webhook or something, right? And then some data should be persisted or should be fetched from external system, right? How we are connecting to that system through some connectors. So those connectors can be used, right? This is that connector. So that is also one of the key element that comes in structure. Then data flow, the movement of data between components from one system to another system, illustrating how information is processed and transformed. For example, data input from users goes through the presentation layer, meaning when I have a form on my HTML page, on my web page, and for example I am registering for this website. First I will fill the form and I click on submit button. So the data is going from presentation layer through business logic, and then where it is stored? Through data layer, data access layer. It is stored somewhere in the database, whether it's AWS Cognito or anything, any external system, but it is stored somewhere, right? So this data is flowing from presentation layer through business logic to the data access layer. That is data flow, and that is one of the key element as part of structure. Then we have deployment view, that represents how the architecture is deployed on hardware or cloud infrastructure, including server arrangements and network configurations, right? Diagrams showing how services are distributed across different servers or cloud instances. For example, we are using AWS services, right? This is hosted on AWS, and then it is interacting with any other system which is outside AWS. So how that interaction is happening. This deployment we will take care of how those hardware, or if it is on-premise solution, then the hardware will come to the business scope. If it is cloud, then it will go to the, or public cloud, then it will go to that respective cloud provider scope, etc., right? Everything is done through this view, the deployment view. Then we have another structure element, which is configuration and environment, setting and parameters that define how components operate in different environments. For example, development environment, testing environment, production environment. An example would be configuration files specifying database connections or API keys. So for example, then we have this type of configuration where we are interacting with another system, and we have different instances. For example, dev stage or production environment. For all those external systems also we have different environments. So for example, corresponding dev environment, corresponding stage environment, because before we make it live we also need to validate the application, right? So we need to create test data for that. Now when we are writing some code and we are committing these files, the configuration files, how these configurations are different for different environments, right? So those configuration respected environment, that comes under this element, configuration and environment. Then security mechanisms, structures in place to protect the data and ensure secure interactions between components, like if there is an authentication or authorization system, encryption protocols, access control, proper authentication is happening or not, tokens are being generated or not, only secured authenticated person is able to access the secure pages, right? After some time, if the session is getting timed out or not, all those secure mechanisms, right, comes under this element. Now question is, why to understand structure? Though we know the answer, right? Without knowing all these elements, we cannot build a robust or secure application. But let's see them. Understanding the structure of software architecture is crucial for designing systems that are scalable, maintainable, and efficient. By clearly defining components, layers, interfaces, and data flow, architects can create a robust foundation for their application. Now we will start learning architecture styles and design patterns. We have different flavors. We will learn each of them one by one. So what is architectural style? Architectural styles provide a framework for organizing a software system. Architectural styles define the overall structure and organization of a software system. They represent high-level solution to recurring design problems and dictate how components interact within a system. Okay, and what is the design pattern? Design pattern utilizes established architectural styles. We have different flavors. We are going to learn about them: microservices architecture, monolithic architecture, event-driven architecture, to solve common design problems. So design patterns going to utilize the architecture styles, right? It helps in standardizing solution and improving code reusability. Design patterns are general reusable solutions to specific problems that arise during software design. They provide templates for solving common design issues and can be applied at various levels, from individual components to entire system. Common design patterns we are going to see. Before we go to the design pattern, let's first understand the architectural styles, because design patterns are going to utilize the architectural styles. So it makes more sense first we understand what are the architectural styles we have. So these are the common architectural styles we are going to cover: microservices architecture, layer architecture, monolithic architecture, service-oriented architecture, event-driven architecture, cloud-native architecture, serverless architecture, component-based architecture, domain-driven design architecture, hybrid architecture, right? And sometimes what we do, we just don't take only one architecture. Sometimes we take like it is hybrid architecture, but we take we actually create a tailored architecture, like a combination of different flavors, and then as per our need we just tailor the architecture. That is also sometime we do as an architect, right? So let's see one by one each of them. So first one is, which is very old, which is monolithic architecture. Let's understand what it is. Okay, let's understand. Picture a house with all rooms: kitchen, living room, bedroom, bathroom, built as one cohesive unit. We have already covered what is cohesiveness, right? With one cohesive unit, basically cohesive is within a module how elements are relying on each other, how they are only with one module within a module, how elements are working with each other. That is cohesiveness, and we need high cohesiveness. There are no separate entrances or sections. Everything is interconnected, right? Single structure, right? Now when the builders construct the house, they put up walls, install plumbing, set up electrical systems at once, and it is straightforward project because everything is part of one plan. So it is easy to build initially, right? Now, if the homeowner decides that they want to add a new room or change the layout, it can be a big hassle, big task. They might have to tear down walls, reroute plumbing, redo electrical work. This requires a lot of time, effort, expense. It means hard to modify, right? Easy to build initially, but hard to modify. Just to remind, we are discussing monolithic architecture right now. All utilities, water, heating and electricity are part of the same system. If there is any problem, if there is a problem with the plumbing, it can affect the whole house, just like a bug in a software component can impact the entire application. Now what we learned? Simple to start. Building a single structure is often easier, faster than constructing multiple separate buildings, right? The challenge with the change. Simple to start, but with challenges with the change. As the homeowner's needs grow, like adding a family member, making changes can be complicated and disruptive. Now let's come to the definition of monolithic architecture. But we understood, right? Monolithic architecture is a traditional software design pattern where a single unified application is built as a single indivisible unit. This means that all the components of the application, including the user interface, business logic, and the data access layer, are packaged together and run as a single executable or deployment unit. They are tightly coupled with each other. That is the whole takeaway here from here. Now let's understand the key characteristics of monolithic architecture. Single code base. All features and functions are developed and maintained in one code base, which simplifies development but can lead to complexity as the application grows. Tight coupling. We already know what is coupling. Coupling is for different modules of the application is if they are relying on each other, they have dependency. That is called tight coupling. And we don't need tight coupling. The recommendation is to have loose coupling. So with the monolithic architecture, we have tight coupling. Components within a monolithic application are often tightly integrated, making them dependent on each other. Changes to one part of the system may require redeploying the entire application. Shared resources. All parts of the application share the same resources, such as database and server infrastructure, which can simplify resource management but may lead to bottlenecks. Simplicity. For smaller applications, a monolithic architecture can be easier to design, develop, and deploy, allowing teams to focus on building features without the overhead of managing multiple services. Now let's see the advantages of monolithic architecture. It is not like that it is always not good to use the monolithic architecture. There are use cases where the monolithic architecture is in favor. Let's see. So the advantages are easier development and testing. With everything in one place, developers can work on the same code base, making it simpler to test and debug. Simplicity in deployment. The entire application can be deployed as a single unit, which simplifies the deployment process. Performance. Monolithic applications can offer better performance due to the direct communication between components without the overhead of inter-service communication. Lower initial overhead. For small teams and projects, a monolithic architecture requires less setup and fewer resources compared to microservices or distributed architecture. Now let's understand the disadvantages of monolithic architecture. So we already have that in our mind. What can be the issues with the monolithic architecture? First is scalability challenge. Scaling a monolithic application can be difficult. If one part of application needs more resources, the entire application must be scaled, leading to an inefficient resource usage. We have already seen in the example of building house, right? Inflexibility. As the application grows, it can become more challenging to manage and make changes. A small change can require significant testing and deployment effort, because we are talking about there is just one code, one unit, and even if we are changing one small area of that code, we need to test the whole application, because there might be an impact on the other areas too. Risk of technical debt. Over time, adding features and making changes can lead to a tangled code base, increasing the likelihood of bugs and making the system harder to maintain. Right? We are changing the same code base again and again. Deployment bottlenecks. Deploying a monolithic application can become cumbersome, especially if it contains multiple features. Any change, no matter how small it is, necessitates a full deployment. So for example, there are because we are talking about just one single deployment for the whole project. If there is a small change, then also we need to deploy the whole package. Whole project will be deployed again. So of course the deployment will take time, right? Even if it is a small change. Now let's understand the use cases, various use cases for monolithic architecture where it can be utilized. So monolithic architecture is suitable for small to medium sized applications where simplicity and rapid developments are priorities. Startups where quick iterations and minimal resources are essential. Less complex domains, applications that do not require extensive scaling or complex interactions. So let's see the summary. While monolithic architecture has its advantages, particularly for smaller projects or teams, it may pose significant challenge as applications grow and evolve. That is one challenge for sure. Understanding its strengths and limitations is crucial for making informed architectural decisions, especially when considering future scalability and maintainability. Now let's go through the second one, which is service-oriented architecture. Okay, let's see one example. This time it's multi-station restaurant. Imagine a restaurant where different stations handle specific tasks. Okay, where one for appetizers, one for main course, one for dessert, another for drinks. Each station is like a service, specializing in its own area. So restaurant, we have restaurant, multi-story restaurant, and we have different stalls, right, with different stalls, and those stalls we need to just consider those are different services. And we are talking about service oriented architecture, or SOA. Now let's see order fulfillment, how it will be done. When a customer places an order, the server relays it to the appropriate station or counter, right? If a customer orders a burger and a slice of cake, the appetizer station prepares the starter, the main course station cooks the burger, and the dessert station makes the cake, right? So those three services will be invoked. Each station can operate independently. Service oriented architecture. Three services, they are working independently. If the dessert station is busy making cakes, it doesn't affect the main course station, yeah, which makes sense, which can continue preparing burgers. This separation allows for flexibility and efficiency. Easy changes. If the restaurant decides to introduce a new type of drink or a special dessert, they can simply add a new station without having to overhaul the entire restaurant. Each service can be updated or replaced independently. So what we learned with this example, modular services. Each part of the restaurant operates independently but communicates with others as needed, because there are different services, right? Different counters, different services. Efficient workflow. Orders can be fulfilled quickly because each station specializes in specific type of food or drink, right? Flexibility. Changes can be made to one part of the restaurant, like adding a new dessert, without disrupting the entire operation. So now let's see what is service oriented architecture all about. SOA. SOA is an architectural pattern style that allows different services to communicate with each other over a network, typically using standard protocols. It promotes the development of software applications as a collection of loosely coupled interoperable services that can be independently developed, deployed and maintained, and loosely coupled. Okay, this is the keyword. Loosely coupled means these different modules, different services, they are not dependent on each other. That's why loosely coupled, right? And they are independent in nature, independently can be developed, deployed and maintained, right? And that is the whole key of service oriented architecture. That's why it's service oriented, because different services and it's oriented around those services. That's why it's service oriented architecture. Let's see the key characteristics of SOA. Okay, first one is loose coupling. Services are designed to be independent of one another. Changes to one service do not significantly affect another, allowing for easier maintenance and updates. Interoperability. SOA enables different services potentially built on different platforms or technologies to work together seamlessly. This is achieved through standardized communication protocol, HTTP, so REST-based. So what does that mean? So for example, we have different services, and it is not even necessary that those services are built on same platform. So for example, one service is available maybe on AWS API endpoint. Another service is totally is available on some different external API system, but is exposed using different flavors. We have the different protocols. For example, REST-based APIs are available, right? Different services. Platform is also different. Doesn't matter at all. Reusability. Services are designed to be reusable across different applications and projects. This reduces redundancy and accelerates development. So for example, the same service we are using for our application, maybe we have different applications available, right? And the same service we are using for another application for the same customer, right? Discoverability. Services can be easily discovered and accessed through service registries, allowing developers to find existing service for reuse. Abstraction. The internal workings for a service are hidden from the user. Users interact with the service through well-defined interfaces, which abstracts the underlying complexity. So this means, we'll just the user, the consumer will just be able to see the abstract layer, means what is the request contract, what we need to pass in the header, for example, if it is REST-based API, right? Not the implementation, how they are going to utilize those request parameters, attributes, and what is the business logic written. That of course is hidden. Only the required contract is visible to the consumer. Now let's see the components of SOA. So we have services, the fundamental building block of service oriented architecture. Each service represents a specific business function and exposes its capabilities through an interface. Service registry, a centralized directory where services are listed and can be discovered by other services or application. It provides metadata about each service, including its functionality and endpoint. Service consumer, any application or components that consumes service provided by the service oriented architecture. This could be a web application, mobile app, or another services. If you guys have seen the Swagger APIs, right, the Swagger documentation is kind of service registry where we have for a particular provider application, right, we can see what are the services available, what kind of request contract we have, what we need to pass in the header, what we pass in the request body, etc., right? And we can just use which API we need, right? So those type of service registry, and then different services are there, and then finally we can consume those services. We have service contract, a formal agreement that defines the interface and behavior of a service. This contract ensures that the service consumer and provider have a mutual understanding of how the service should function. So for example, one of the contract could be that if it is a REST-based service, that which request parameter or attributes it's going to accept. So for example, consider if it is a login function, right? So it will require a username, a password, maybe it requires a reCAPTCHA token, etc., right? All those things. So that is kind of a contract, what we need to pass in the header, right? What is the endpoint? All those are service contracts. Communication protocols. So relies on various protocols for service communication, such as simple object access protocol or REST and others. So of course, these are the communication protocols. Let's see the advantages of service oriented architecture. Scalability. Services can be scaled independently based on demand, allowing organization to optimize resource usage. Flexibility. Organizations can adapt to changing business needs by modifying or replacing specific services without overhauling the entire system. Easier integration. SOA facilitates integration with existing systems and third-party services, promoting a more cohesive IT ecosystem. Reduced time to market. Reusable services enable faster development of new application and features. Let's see the disadvantages of service-oriented architecture. Okay, complexity. Managing a large number of services can lead to increased architectural complexity, requiring robust governance and management practices. Performance overhead. Communication between services over a network can introduce latency, impacting performance. And some time to check those performance, we have another type of testing, which is performance load testing, using various tools. So for example, JMeter is one of them. We have load testing, for example, for 100 users or those concurrent users for a specific window time. We run the load test, we see what is the performance of those APIs, the 90th percentile, the 95th percentiles, all those configurations and key aspects we have. We see within how many seconds we are getting the response from the provider, API provider, right? So all those things we validate. So performance overhead can be an issue because everything that the handshaking, etc., everything that is happening over network, right? So there might be some latency related issues. Initial development cost. Designing and implementing and SOA can be more costly upfront compared to simpler architectures. Let's see the use cases for service oriented architecture. Okay, in these scenarios we can use the service oriented architecture. One is enterprise applications. Large organizations often use SOA to integrate disparate systems and applications, providing a unified approach to business processes. So it is very popular architecture style to do. Service oriented architecture is very popular. Cloud services. Many cloud native applications are built on service oriented architecture principles, leveraging microservices that can be independently deployed and scaled. So we just saw that it's a kind of hybrid. We are talking about hybrid architecture solution here. So within SOA and for a particular provider, the provider is leveraging the microservices architecture. So like I said, we can always tailor the architecture style or pattern to as per the need of the business. Legacy system integration. SOA facilitates the integration of older systems with modern applications, enabling businesses to leverage existing investments. Finally, the summary. Service-oriented architecture SOA offers a powerful framework for building flexible, scalable, and maintainable software systems by promoting loose coupling and interoperability. SOA allows organizations to respond more effectively to changing business requirements and technological advancements. However, it also requires careful planning and governance to manage its inherent complexity effectively. Let's learn event-driven architecture or EDA. Event-driven architecture EDA is a software architectural pattern that focuses on the production, detection, consumption, and reaction to events. Okay. In an EDA, components of the system communicate primarily through the events they generate, enabling a decoupled and responsive architecture. This approach is particularly suited for applications that require high scalability, real-time processing, and dynamic interactions. Let's see the key characteristics of event-driven architecture. Event-centric. EDA revolves around the concept of events, changes in state or significant occurrence within a system that trigger reactions from various components. So it means some event will happen, some event will happen, and then only something else will happen. That's why it's event driven architecture, right? Decoupling the producer of the event and consumer of the event are loosely coupled, means they are not relying on each other, right? This means that the components generating events do not need to know about the components that consume them, right? Allowing for greater flexibility and easier maintenance. Asynchronous communication. EDA typically employs asynchronous communication. Asynchronous means which is not happening just right instantly, right? Asynchronous means it will not wait for that call to complete, that response to complete, that the client will not wait for that. It will just trigger the API, and then that will happen as a background job. Allowing components to operate independently. This can improve system responsiveness and performance, as events can be processed without blocking the sender. Okay, so consider a scenario. What is happening when we have a functionality of maybe a registration functionality. So user will fill the registration form of the application, will click on sign up, and then when user is signing up, the profile is also being created on various other external systems, maybe a CRM system, maybe a profile system, etc. Right? So we will not wait until the profile creation on to all those systems are being completed fully, and then we will notify the user that it is completed. We will not wait for that, otherwise it might take some time and then user might face a performance issue. What we can do, we can just hit the profile creation call asynchronously, and it is kind of a backend job which is going on in parallel, and based on the response we are getting from this backend job, this asynchronous call, whether it's successful or some technical issue had happened, we can take some action accordingly, right? But this can be made as a asynchronous call. Now, next one is scalability. The decoupled nature of EDA makes it easier to scale individual components based on demand, improving overall system performance. Real-time processing. EDA is well suited for real-time application where immediate response to events are crucial. Now let's see the components of event-driven architecture. So we will have event producer, event consumer, event channel, and event store. So what will happen? Event producer, these are components or services that generate events based on specific action or changes in state. For example, a user submitted a form might trigger an event. So for example, I just said that user is filling a registration form, that is an event, right? Event channel. This serves as the medium through which events are transmitted from producers to consumer. Common implementation include message broker or event stream platform. For example, Apache Kafka, or maybe in AWS also we have queues available, SQS, etc. Right? The simple queue service. What will happen? Anytime, so for example, this registration is happening, this event will be put in the SQS, in the queue. Okay, this event is produced by the front end. Now, whatever is the API, I mean through API, that queue will be picked by the consumer, right? For example, this queue we are putting it for profile creation in another system, right? From the queue, consumer will pick this, right? And then will take action, I mean the profile creation in another system, right? So what had happened in this whole scenario? Producer is not waiting for the consumer, right? Consumer is not waiting for the producer, right? It is just like they are just working independently, so loose coupling. Okay, event consumers, these components listen for and response to events. They can perform action based on the events received, such as updating a database, sending notification, or triggering further process. Sometimes it is also called subscription based model, because what is happening, the components, right, they have subscribed to that event, right, and when that event occurs, they take the action. So sometimes it is called subscription based model also, right? Event store, a storage mechanism for persisting events which can be useful for audit trails, debugging or rebuilding system state. Let's see the advantages of event-driven architecture. First one is of course the loose coupling. Components can be developed, deployed and scaled independently, allowing for greater flexibility and maintainability. Enhanced responsiveness. EDA can provide quicker responses to changes as events can trigger immediate actions, right? Scalability. Systems can easily scale by adding more consumers or producers without affecting other parts of the architecture. Then improved fault tolerance. The decoupling of components can lead to increased resilience. If one component fails, other can continue to function, right? Now let's see the disadvantages of event-driven architecture. First one is complexity. The architecture can become complex, particularly in managing event flows, data consistency, and error handling. Because one example is of course subscription based model, right? So of course we need to have those store that if what happens if there is any technical issue while the event has occurred, but the provider, right, the provider has not picked that event from the queue, right? So we need to have that type of store. Event ordering. Ensuring the correct order of events can be challenging, especially in distributed systems. So one example is, like I said, we can use the AWS SQS, the simple queue service, and then there are multiple notifications events in the queue. We need to ensure that those events are picked in correct order, otherwise it's a mess, right? The profile creation event for one user and then it is picked for another user, and then of course it will create issues. Debugging challenges. Tracing issues can be difficult due to the asynchronous nature of communication and the decoupled components, right? It can be an issue. So like proper logging is required, proper logging framework should be written properly, so then only even when using that trace ID etc we can see okay at what time it has failed. Though we have different options available to be true. For example, in AWS we have that X-ray option available, right? We can at least try debugging where in that flow this has failed, but yeah, it is not simple, it is a challenging task to debug. Now let's see the event-driven architecture use cases. So these are the use cases: real-time analytics, systems that require immediate insights from data streams such as financial transactions, social media interactions, that is a good fit. IoT applications, devices generating data events where quick processing and response are essential. Microservices, in microservices architecture, EDA facilitates communication between services while maintaining loose coupling. So again it is kind of a hybrid solution. We are mixing, leveraging benefits of other architecture framework styles. User interfaces, applications where user interactions generates events, for example this registration event, login event, right, that need to be processed quickly for updates or notifications. So event driven architecture provides a powerful framework for building responsive, scalable and loosely coupled systems. By centering the design around events, organizations can create applications that adapt easily to changing requirements and handle high volumes of interactions in real time. However, it is essential to manage the inherent complexity and challenges of EDA to maximize the benefit effectively. Let's learn the layered architecture. What is layered architecture? Layered architecture is a software design pattern that organizes a system into distinct layers, each with specific responsibilities and roles. This architectural style promotes separation of concerns, making it easier to develop, maintain and scale applications. Each layer communicates only with adjacent layer, which helps to isolate changes and simplifies debugging and testing. So we have different layers. Layer can communicate with the adjacent layer. Let's see the key characteristics of this architecture. Okay, separation of concerns. Each layer addresses a specific aspect of the application, allowing developers to focus on one area at a time without affecting others. Defined responsibilities. Layers are designed with clear responsibilities, each which helps streamline development and enhance code readability. Encapsulation. Each layer encapsulates its functionality and exposes a well-defined interface for interaction with other layers. Interlayer communication. Layers typically communicate with one another through functions calls or service requests, promoting a structured flow of data and control. Now let's see those layers in the layered architecture. I mean, what are those layers? Okay, now it will make more sense. So those layers are presentation layer. And the responsibility of presentation layer is this layer handles user interactions and presents data to the user. It typically includes user interface elements and input validation. And the technologies used for this layer are HTML, CSS, JavaScript framework like React, Angular or Vue.js. So whenever we open any website in any of the browser, the very first thing what we see, it's an HTML page where we have all the user experience, whether it's some CTA button, interaction web pages, form submission, form container, etc. Everything is presentation layer through which user interacts with the system. Then we have business logic layer, or we call it as domain layer. Responsibilities are it contains the core functionality of the application, implementing business rules and logic. It processes inputs from the presentation layer and interacts with the data layer. Technologies would be any programming language, popular languages, for example, Java, C#, Python, etc. We have so many, right? And frameworks would be, and there are multiple frameworks, whether it's a CMS1, Spring framework, .NET. So there are many frameworks available. So once the user is submitting any form, for example, and then some business logic is being executed, whether we are saving this data to any database system, or we are sending this data to any third-party system, or maybe we are doing some validation against this data, we are pulling some data from any downstream APIs, right? Everything, whatever logic is written in backend, that logic comes in business logic layer, right? Only the logic, not the how we are persisting, where we are persisting this data, because that will go to another layer, right? So these layers are actually interrelated, they interact with each other, right? Next to one, the adjacent layer. So for example, presentation layer, adjacent layer is business logic layer. So presentation layer will talk to business logic layer. It will not directly communicate to third layer, which is data access layer. So presentation layer will not communicate with data access layer directly, but will communicate via business logic layer, right? Now comes the third layer, which is data access layer. And the responsibility of this layer is it manages database interactions, including CRUD operation. CRUD operation is creation of something, reading some data, updating some data, delete. So it's just like first letters we have taken CRUD, CRUD operations. This layer abstracts data storage and retrieval from the business logic. So this layer abstracts data storage, right? So data that it's not a low level, just high level. So it's hide that information. Technologies used, all those database related key terms, SQL database, whether it's MySQL, PostgreSQL, ORM related tools, Hibernate, etc. Right? Then we have database layer. So with this layer, database access layer, we are accessing the database, right? With database itself is a layer here. So responsibility will include that the physical storage layer where the data is stored and managed. This layer is usually managed by a database management system, DBMS, and technologies will include, of course, the MySQL, Oracle, MongoDB, any database, right? So we have presentation layer. The user will interact with this layer. Then once this any event is happening, the business logic will take care of that logic. Will interact with the third layer, which is data access layer. What is the logic behind this? How we are going to interact with that data, how we are going to access that data. And then the database layer, where we actually put the data, will store that data, right? So that is database layer. So let's see the advantages of layered architecture. Okay, maintainability. Changes in one layer typically do not affect others, making it easier to manage and update the system. What does that mean? So for example, we have those four layers: presentation layer, we have business logic layer, we have data access layer, we have database layer. So these four layers, right? Consider we need a change that we want to change some user experience. Maybe we have those buttons which are in blue in color, we want to change them to light blue, or maybe something else, maybe red in color, right? What we will do, we will change the CSS, we will change the style, we will change the theme, and this will impact only the presentation layer. We will maybe change the HTML, whatever changes we are going to do, it will just impact the presentation layer. We will not change the business logic, we will not change the database operation, database access, we will not change that. So maintainability is easy because we are just changing, we are just updating, we are just concentrating on one layer, right? Reusability. Layers can often be reused across different applications, particularly the data access layer and business logic layer. And let's understand this also. So for example, we have business logic layer, and this business logic is pulling some user profile information, right? So we have data access layer and database. So business logic layer is actually hitting the data access layer and pulling some user profile information. And we have a presentation layer. Presentation layer is just using this data. Now consider we have another application for the same enterprise solution, but this time the presentation layer is changed, but we want to pull in the same profile information. Do we need another business logic layer? Do we need another data access layer? Do we need another database layer? No, we don't, because we want the same type of profile information, but just the UI is changed. So what we will do, we'll create a new presentation layer and we will reuse the existing data access layer, existing business logic layer, existing database layer. So that's why the reusability factor is increased here. Scalability factor. Each layer can be scaled independently. For example, if the presentation layer experiences high traffic, it can be scaled without impacting the other layers, and that makes sense also, and it is applicable for database layer, data access layer as well. Consider a scenario where we need more replica of the database. We can create multiple replicas of the database system and then we can scale it, right? So scalability is also a factor. Testability. Individual layers can be tested separately, simplifying unit testing and integration testing. Now there might be a question, without the database access layer or data access layer or business logic layer, how can we test, for example, front end? We cannot validate. So partially true, partially not true, because consider a scenario where we have the presentation layer, right? Within the presentation layer we have static pages, we have dynamic pages, right? So we can validate the static pages, you look and feel. We can still test even the dynamic pages, look and feel we can validate if the user experience is good or not, right? For example, we want to validate if once the user is clicking on any of the form container and as per user experience, user should land on a thank you page screen, right? We can still validate it because we have that page available on our front end. So testability is easy. We can test individual layers without any issue. Now let's see the disadvantages of this architecture. Performance overhead. The separation into layers can introduce performance bottlenecks due to the additional processing required for inter-layer communication. What does that mean? So because we have different layers, so for example, presentation layer is one, business logic is maybe on another platform altogether, right? Maybe we have a middleware in between where we have put all the business logic at middleware. It's totally different technology altogether, and through APIs we are connecting to middleware, right? Now because we are on the network, these calls are happening on over network, there will be of course a latency. That is what it is about, performance overhead, because we have separated these layers, and then the interaction, the interface will happen over network. There will always be a performance latency. Complexity. While layers help manage complexity, they can also introduce it, especially if the number of layers becomes excessive or if there are many dependencies between them. rigidity. Strict layering can lead to inflexibility in certain cases, where cross-layer interaction becomes cumbersome and necessary complex solution. So, I mean, this might become a complex solution if we have different systems also. So, consider a scenario where, like I said, business logic is written on maybe a middleware solution we have written, right? And then we have multiple systems through this middleware. We need to interact with these multiple systems, right? So, as many systems we are integrating with our application, there will be more complexity because of course these are different distributed systems, right? So that way these are the, not I would say disadvantages, but the architecture of the system will become more complex. Now let's see the use cases of layered architecture. So it can be used in web applications where the presentation layer needs to interact with business logic and data layer. That is one use case. Enterprise applications, large scale systems that require clear separation of functionality and maintainability. Mobile applications to manage different aspects like UI, business logic and data handling separately. And to be true, most of the enterprise solutions right now are built on this architecture, layered architecture, and I have mentioned it earlier also. It is not fixed that we always use one architecture principle. We always use tailored one, the combination of different flavors, the good features of different architectures. So for example, we might have a layered architecture, and then within layered architecture we can also have microservices architecture or event driven architecture, or a combination of layered plus event driven plus microservice. So that is possible. So based on business needs, based on how can we make it more performative, what kind of solution we are building, we decide that which architecture's capability we should pull in and to make it as a tailored architecture. So that is always done like that only. So let's conclude layered architecture. Layered architecture provides a structured approach to software design, facilitating separation of concerns and promoting maintainability and scalability. By organizing an application into distinct layers, developers can focus on specific functionalities and manage complex more effectively. For example, front-end developers, they will only concentrate on the front-end layer. They will work on HTML, CSS, theme, design, whereas the back-end developer will only concentrate on the business logic layer. Whereas a database developer will only concentrate on the database access layer, right? However, careful consideration is required to balance the benefit of layering with potential performance impact with architectural rigidity. Like I said, because layers are separated and interaction or interface will have over network, so of course there will be a performance impact that we need to compensate. I mean, we'll see how can we reduce that performance impact, how can we reduce that latency, how can we scale this backend, these backend APIs performance, that we need to consider while we will design the architecture of such solution. Now let's discuss the next architecture, which is microservices architecture. It is a very popular architecture nowadays. Lots of enterprise solutions, they are looking for such type of solution, microservices architecture. A very good discussion point while in interviews also, basically mainly in architect kind of interviews. So let's explore. Microservices architecture is an architectural style that structures an application as a collection of small independent services. This is the key point: small independent services that communicate over well-defined APIs. Okay, so there will be multiple small independent services and they will communicate over APIs. Okay, well-defined APIs. Each microservice focuses on a specific business capability and can be developed, deployed and scaled independently. Consider there are multiple services, they are not relying on each other, kind of they are loosely coupled, focused on a specific business capability, right? And if they want to communicate with each other, there are well-defined APIs. That is in nutshell this whole microservices architecture is. This approach promotes flexibility, scalability and resilience in software development. Of course, right? So for example, we have a requirement that we have multiple microservices and we need some change, some enhancement in one of the microservice. Just make that change in that microservice. That's it. No need to change rest of the hundreds of microservices. No. And the deployment is also easy, right? A teeny tiny application needs a new deployment, and then it's a few seconds to few minutes task and done, right? So those are the advantages. Now let's see the key characteristics of microservices architecture. First one is independence. Each microservice operates independently, allowing teams to develop, deploy, and scale services without impacting others. Just remember this thing. Microservices means there are multiple small tiny services. They are independent in nature. That is the key. That is the key takeaway. If someone asks you in the interview what is microservice, micro means very tiny, right? The micro, etc. They used to there. And then services, there are multiple services. They are independent in nature. They are loosely coupled, means they are not dependent on each other at all. Single responsibility. Microservices are designed to perform a specific business function or capability, adhering to the principle of single responsibility. So we still remember single responsibility principle that comes from solid, right? The very first letter S, right? Each function should have one responsibility, and there should be only one aspect of changing that function, only one reason to change that function. That is single responsibility, right? Decentralized data management. Each microservice manages its own database and data, promoting data ownership and reducing coupling between services, right? So they consider, I mean, those microservices are different people. They mind their own business. They will complete their task. They are not dependent on each other at all. Inter-service communication. Microservices communicate with each other over the network using lightweight protocol such as HTTP, REST. There are other protocols as well. Messaging queues are also very popular. Technology agnosticism. Teams can choose the best technologies and programming language for each microservice, enabling a diverse technology. This is one of the key takeaway, right? So for example, there are multiple microservices. So it is not necessary that, for example, all the microservices will be developed using one technology. So for example, this microservice is built over OSGI framework or over using AWS API endpoint or some other technology. No. So those different microservices can use different technologies, different programming languages, right? Because they are not related to each other. And if they want to communicate to each other, then we have some lightweight protocols already available, right? And those protocols are not dependent on technology. REST principle, HTTP, those are protocols are there through which we can just interact with any type of service, no technology intervention in between, right? So that's why there is no issue with the technology. Same technology is not required. Let's see the advantages of microservices architecture. Scalability. Services can be scaled independently based on demand, optimizing resource utilization and performance. Yes, right? Those are independent services, so they can be scaled independently. Flexibility. Teams can adopt new technologies and frameworks for a specific service without affecting the entire application. This is one of the best advantage of microservices. Multiple services, and each service needs some change. That change will be deployed to that service, and it will not impact other services. Other services are still functioning. Right? Consider a scenario where on your web application you are using multiple web microservices, and maybe one of the microservices is not functioning because of some technical issue, right? Only that functionality will be impacted. Other functionalities will still work on your web page, right? So there will be no downtime on the user experience. Just maybe one service will not work on that function, on that digital platform. Then resilience. If one microservices fails, it does not necessarily bring down the entire application. Like I said earlier, other services can continue to function, enhancing overall system stability. Faster time to market. Independent development and deployment cycle enables team to deliver features and updates more quickly. Yes, that is also true. Easier maintenance, smaller code base are easier to manage, test and understand, leading to improved maintainability. Yeah, so those different microservices, different teams are working on those microservices. Something is changed, they will just change it, they will just validate it, and life is good, right? Now let's see the disadvantages of microservices architecture. Okay, this one, complexity. Managing multiple services increase architectural complexity, requiring robust orchestration and monitoring solution. To be true, so people say that this is one of the disadvantage, but I am not aligned with this. It's not disadvantage, it is actually an advantage, because even in architectural while we do the architecture of such a type of solution where we have different microservices, it is easy to document it, because we know that okay, this microservice is responsible for this functionality, and this microservice will be doing this activity, right? So it is easy to manage, it is easy to document, it is easy to even show those all those diagrams that okay, this section will be done by this platform or service. So likewise, it can be considered as advantage too. Network latency. Inter-service communication over the network can introduce latency, which may affect performance, and this issue will arise for any of the modern architecture, network latency, because most of the time the communication between different systems will happen over network, and when there is a network, of course there will be latency, right? We can always think of some solution to reduce this latency. So for example, this is solution, the way who is exposing those APIs can be scaled up, can be put on the infra can be scaled up, like more CPU, etc., memory. With that, I mean, it can provide a better solution with lower latency. Then data consistency. Achieving data consistency across services can be challenging, especially in distributed system. Yes, that can be a challenging task, because most of the time we rely on asynchronous calls. Asynchronous calls means we just call it, and sometimes we use that subscription type of architecture, that we just put that event driven call to a queue, and then the subscribe network will get this, will execute that event, right, process it. So user will not wait for that call to complete, right, because we want to improve the performance of our front end. So few things can be executed in backend, so we introduce more asynchronous calls, right? So sometime when we have those asynchronous calls, the other system is also running in parallel, will take time to complete that job, and during this time, until that process is complete, and then it will give back the response, and then with the response we update our system also to make it consistent that the job is complete or not. During this time, data can be inconsistent, and let me give you one example. So for example, we have the requirement that we are creating profile, so user just have a sign up registration flow on the system. So user hit on the sign up button, and at the time of sign up we are creating this profile on multiple systems. So for example, we are creating profile on AWS, maybe AWS using AWS Cognito. We are also creating profile in CRM system, right? Now while this profile creation is happening in CRM system, that is a synchronous call. We call this system, we get the response from CRM system. If it is successful, we update back Cognito that the operation is successful, right? Now there might always be a latency, that once we will get the response, maybe it's there is a time difference, right? During that time, it's always an inconsistent data, because that profile is not yet created on CRM system, but it is already created in Cognito, and we still don't know that the profile is successfully created or not. So that way, achieving data consistency across services can be a challenging task, because we are talking about distributed systems. Then deployment overhead. Deploying nebulous microservices can require more sophisticated CI/CD pipeline and deployment strategies, and proper planning, of course, right, of the DevOps team working together, making sure that the latest services are deployed or not. Now let's see the use cases of microservices architecture. And to be true, I would say most of the time, most of the enterprises look for such type of solution right now. So Microsoft, these are the use cases: large scale applications, systems that require high scalability and frequent updates, such as e-commerce platform, social networking platforms, streaming services, etc. Agile development, organizations that prioritize rapid iteration and delivery of features can benefit from the independent development cycles of microservices, right? Cloud native applications. Microservices are a natural fit for cloud environments where services can be deployed and scaled dynamically. Classic example of where microservices are used. There are multiple cloud native applications which are using microservices architecture along with event driven architecture, that we will talk about it. And one more architecture we will use, this event driven architecture, just give me a second, and a layered architecture. So combination of these architecture, and then finally we create a tailored architecture. So let's conclude microservices architecture. It offers a modern approach to building software applications, enabling organizations to achieve greater agility, scalability, and resilience. By structuring applications as a collection of independent services, teams can innovate more rapidly and respond to changing business needs effectively. However, careful consideration is required to manage the inherent complexities and challenges associated with distributed systems. Yeah, so that is of course there is always a consideration we need to make, that because we are working in the distributed environment for such use case, we always need to make sure about the latency, about the deployment, right, the interaction, the interface is happening properly or not, right? So all those considerations we need to make while we adapt this microservices architecture. Now this is very popular, cloud native architecture. Let's see what is this architecture is all about. Cloud native architecture is a design approach that leverages cloud computing to build and run scalable application in dynamic environment. Cloud computing, I have created a separate playlist for it. What is cloud computing? Nothing but we already have so many cloud providers, AWS, GCP, Azure, etc. And they provide so many services, multiple services, whether it's infrastructure as a service, software as a service, platform as a service. Those solutions are provided by those providers. Now this architecture evolved around those services, whether it's in IaaS, whether it's infrastructure as a service, platform as a service, and all. This architecture is focused on flexibility, scalability, and resilience. These key terms are coming from cloud only. This scalability, flexibility, these are cloud terms. Scalability is like you add more servers, how can you scale the application, right? So these are all cloud terms, and this architecture allowing organizations to take full advantage of the cloud's capabilities. These all are cloud capabilities. So this architecture will also evolve around cloud capabilities only. Let's see the key characteristics of cloud native architecture. Okay, first one, microservices. Like I said earlier, microservices architecture is also very popular for one of the use case, which is cloud native architecture, right? So the very first characteristics of cloud native architecture is of course microservices. Applications are built as a collection of small independent services that communicate through APIs. Each service can be deployed, developed, and scaled independently. So the very first characteristic of cloud native architecture is we can build multiple microservices, and those microservices are independent in nature. They work for one specific task. They are not relying on each other, very loosely coupled. They interact with each other over protocol, like for example REST based protocol, etc. Right? So they can be even on different platform or different technologies altogether, right? Containerization services are packaged in containers, which provide a lightweight and consistent environment for development, testing, and deployment. This ensures that applications run the same way regardless of where they are deployed. Then dynamic orchestration. Tools like Kubernetes are used to manage containerized applications, automating deployment, scaling, and management of containers based on demand. Right now we are talking about cloud. So all the functionalities, all the capabilities of clouds are being discussed right now. One of the cloud feature which is very unique, which is of course orchestration, right? So we will create the container, and using those containers, those packages, we have tools like Kubernetes available. We can just have manage, can deploy those containers, right? We can have automatic deployment, we can scale, we can put in scaling, etc. of those containers, right? So that those options are there. DevOps practices emphasizes collaboration between development and operations team, enabling continuous integration and continuous delivery, or sometimes we CI/CD, continuous integration, continuous delivery practices for faster and more reliable software releases. Then elasticity and scalability, very popular topic of capability of cloud computing, right? Applications can automatically scale up or down based on demand, allowing efficient resource utilization and cost management. What is this? So for example, you have made this web application live, and you are expecting that 100 users will access your application at a time, right? But your website is so amazing that you see that on this coming Diwali, thousands of users are coming to access your web application. But the problem is your infrastructure, what you have created, will just cater only 100 users at a time. So how, consider you have not even used this cloud capability, right? What will you do? You will go to the market, will buy more resources, more CPU, etc., right? And it's an overhead because you need to change the whole infrastructure. Now if we use this cloud native architecture, what will happen? Because you are on cloud, and with cloud we have this feature available, pay as you go subscription. It will automatically scale your server, right? It will automatically increase the VM size, etc. Just a second. And I thought I should explain this also. What I am trying to do is I'm just trying to explain scaling very quickly. So yeah, let me explain. I mean, it will take just a few minutes. Okay, so we have two type of scaling. I have already described that in one of the video, but I thought I should explain it. Oh sorry, not this one. This is, just a second. So this is up and this is okay, scaling, right? So we are talking about scalability, scaling. So we have two type of scaling, vertical scaling and horizontal scaling. Now consider there is a scenario, right? This is the family, right? And two people are living right here happily, no problem at all. Now they have a kid also. Now kid is growing, got adult, right? And he got married. So what they need one more house for it, either some way to accommodate another person, right? The newly added person here, his wife, right? So there are two ways. One way would be in the same house they will add one more room up there, multi-story building. That is one. Or they will, within the same premise, they will build another house, right? So when they are adding one floor to it, so what they are doing, they are adding some more capacity to the existing house. This is called vertical scaling. When they are all together making a new house, this is called horizontal scaling, right? This way we are increasing. So similar way in cloud native architecture, what will happen, we will have in cloud, this is nothing but the VM, right? The VM, CPU, storage, consider this is server, right? This is server. So in this case the server size is increased, and in this case more servers are added to handle the load, right? So within cloud, and this is in few seconds, this is automatically can be done automatically scale up or scale down. So that is the benefit of having cloud native architecture. Next one is resilience and fault tolerance. Designed to withstand failures, cloud native applications often include built-in redundancy and failover mechanism to ensure high availability. So for example, when we run our application on cloud, right, and they have concept of multiple availability zones, multiple reasons, right? So for example, this is one reason, right? This is one reason, this is another reason, right? And because of some natural disaster or some issue, one reason failed, we still have data that application is running through another reason or maybe some another availability zone, right? So that is called fault tolerance, right? So designed to withstand failures, cloud applications often include built-in redundancy. So their data redundancy means your data will be copied over to multiple regions or multiple availability zones, so that in case of some disaster, using failover mechanism is still application is still available. That is called high availability. Now APIs and event-driven communication. Services communicate through well-defined APIs or events. That is the characteristics of microservices architecture, promoting loose coupling and flexibility in integrating with other services. So that is a feature with microservices architecture. They communicate with each other over well-defined APIs or event. If this is event, then this is event-driven architecture also. And like I have mentioned a couple of times, when we design any of the architecture, this is always a combination of different architectures. So for example, this right now we are talking about cloud native architecture, microservices architecture, event-driven architecture, and layered architecture. So we have taken four architectures features. Promoting loose coupling and flexibility integrating with other services. Okay, then infrastructure as code. Infrastructure is managed through code and automation tools, enabling version control, consistency, and rapid provisioning of resources. That is also possible. We can put infrastructure as code. We can create those templates, and whenever we want to deploy another infrastructure altogether, using those templates we can just deploy the whole infrastructure. Your infrastructure will be ready within few minutes, right? So those capabilities are there in cloud native architecture. Now let's see the benefits of cloud native architecture. First is faster time to market. It enables rapid development and deployment cycles. Cost efficiency, reduces infrastructure cost through on-demand resource usage, and this is one of the beautiful advantage. Actually, pay-as-you-go subscription, no need to buy all the servers. When starting, if you think that we need more servers, we will just buy those servers on the go until we need them, and then again decommission them. So it will, of course, this subscription will of course will save money, right? Improved resilience. Applications can recover quickly from failures, right? We have this failover mechanism concept. Enhanced developer productivity, focus on writing code rather than managing infrastructure, because your infrastructure is managed by amazing cloud providers, whether it is AWS, GCP, Azure, etc. And the advantages are not only till here. We have multiple advantages: scalability, performance, security. There are so many advantages. Whatever advantages we have with cloud capability, all advantages will be inherited by this architecture. Now let's see the use cases of cloud native architecture. So it is ideal for developing applications that require frequent updates, such as web applications, mobile backends, and APIs. Cloud native architectures empowers organization to innovate rapidly while maintaining the flexibility and efficiency offered by cloud environments. Now let's learn this architecture. Serverless architecture, very popular. Let's learn what it offers. Serverless architecture is a cloud computing execution model where the cloud provider dynamically manages the allocation and provisioning of servers. In this model, developers can build and run applications without worrying about the underlying infrastructure. So one thing to notice here, that is, this is also cloud computing, means cloud native architecture only, but serverless means this will be managed by the cloud provider. The servers will be managed by the cloud providers. All we need to worry about that how can we build the application. That's it. Let's understand the key characteristics of this architecture. Event driven. Serverless applications are typically triggered by events. It means event driven architecture is also involved, such as HTTP requests, file upload, database changes, or scheduled tasks. Managed services. Functions or services are managed by the cloud provider. which handles the server setup, server maintenance, and server scaling automatically. So nothing to worry about the infrastructure at all. And then microservices based. So it means event driven architecture, microservices architecture, cloud native architecture also right now. And then it is serverless architecture. So again, I'm saying whenever we decide the architecture, it is always 99% tailored architecture, combination of different flavors of different architecture. Applications are often structured as small single purpose functions that perform specific tasks, promoting modular design. So it means there will be many microservices which are not relying on each other. They are independent in nature. They are there for their different purpose, different functions they are performing, loosely coupled. And if they want to communicate to each other, the interface would be for example, REST-based protocols, etc., right? The HTTP protocol, that is how they communicate with each other. If one of the services is down, one of the microservices is down, still your web application will perform for other services with other services. So there will be no downtime at all, but yeah, lesser impact on the website because other microservices are still working. Those microservices are technology independent, platform independent. That means different microservices can be deployed, can be built using different technologies, different platforms, right? Then we have stateless functions. Each function execution is stateless, meaning it does not retain any data between executions. Any required state must be stored in external database or services. Auto scaling, serverless functions automatically scale in response to demand, allowing applications to handle varying workload efficiently. One of the example is AWS Lambda functions. Those are also serverless, and they scale automatically as in response of demands. For example, multiple requests are coming, so we will have multiple functions being executed, Lambda functions being executed. So auto scaling is there. Auto scaling means up and down. Based on need, the functions will increase or will go down. The resources will increase up or down. Pay-as-you-go pricing. Users are billed based on actual usage. It means the number of functions invocation, making it cost effective, especially for applications with variable load. So for example, today I am using for 500 concurrent users, tomorrow I am using for 1000 concurrent users. Maybe after the sale ends, I am using it for only 100 users. So how many functions are being executed, on basis of that only I will be billed, I need to pay. Let's see the benefits of serverless architecture. Reduced operational overhead. Developers can focus on writing code rather than managing infrastructure because it is managed by the cloud provider. Faster development. Accelerates the development lifecycle, enabling rapid iteration and deployment. Cost efficiency. Pay only for what you use, reducing cost for low traffic applications. Scalability. Automatically scales with traffic, handling large spikes in demand without manual intervention. And not only this, whatever capability we have for cloud native architecture, we will get everything for serverless architecture as well, because that serverless architecture is also on cloud. Let's see the challenges of serverless architecture. Okay, first challenge is cold start latency. What does that mean? Initial request to a serverless function may experience latency due to the time taken to spin up the environment, warm up. So few requests might take some time, right? Limited execution time. Functions often have a maximum execution time, which can be restrictive for long running tasks. And complexity in monitoring. Debugging and monitoring can be more complex due to the distributed nature of serverless application. And this one, the complexity in monitoring, right? This is always a case wherever we work for a distributed environment, whether it is cloud native architecture or microservices architecture or layered architecture. We need to have proper logging framework enabled, proper monitoring that is always required, and how can we debug those issues, right? Now let's see the use cases of serverless architecture. Web application, ideal for APIs, microservices and backend. Yes, that is a good use case. Data processing, useful for real-time data processing. ETL type of tasks, extraction, transformation and loading, and analytics, because of course it's a service based on demand. We need to increase the function, right? So good for IoT, good for data processing as well. IoT applications handles events generated by IoT devices efficiently. Scheduled tasks, perfect for cron job and automated tasks that run at specific intervals, something coming on real time. That is also a good use case. We are getting some data from any of the IoT device, and then we need to perform some action based on that data retrieval, right? As many requests are coming, we need to increase the functions. So server will be managed by the cloud provider, and as many requests are coming, those functions will be created, will be executed in parallel. So of course it's a good use case for this type of architecture. Now let's learn this architecture, which is component based architecture. Component based architecture, or we call it as a CBA, is a design approach that emphasizes the separation of functionalities into reusable components. Each component encapsulates a specific piece of functionality or a set of related functions, enabling developers to build complex systems by assembling these components. And one more simple definition: component based architecture is a software design paradigm that focuses on building application from discrete reusable component. Consider we already have a component available. Someone will give you that component, you will reuse that component and will make the application, right? So something is already developed and we can reuse it. Those components are reusable components, right? Let's learn more. And I thought I should give examples first so that we have more understanding what we are discussing right now. So let's understand the examples. First example of web application. If we are from the front end development background, we already know React framework, Angular framework, Vue.js framework. What are those frameworks? For example, React, a JavaScript library. This is already a library written by some organization, right? For building user interfaces using reusable components. Each component can manage its own state and lifecycle. So we are given the React library, and using React library, we are building our front end. So that is a reusable component. Similar to Angular.js is another component, Vue.js is another component, another framework. So these are component based design, allowing developers to create a encapsulated components that can be reused throughout the application, right? Microservices architecture, for example, Docker is a very popular one. While not a component itself, Docker containers can encapsulate microservices, making them modular and easily deployable, right? Spring Boot is another. In a microservices environment, each service can be treated as a component that handles a specific business function, allowing for independent deployment and scaling. So those microservices we are creating, those are nothing but the components, because we can reuse the same service again and again. So those are again components. Then we have, for example, game development use case, and I'll take the example of Unity. Unity is a very popular game building tool, right? Software, a game engine that uses a component based design pattern where game objects can have multiple components, for example, physics, rendering, scripting, attached to them to different behaviors. So we can create that component once and then we can reuse it again and again. For mobile applications also, we for example, this Flutter, a UI toolkit that uses widgets as components, allowing developers to build interactive mobile applications. And Swift UI is another building tool, right? Provided content management system. This is very popular. WordPress, Drupal, Adobe Experience Manager, right? What we can do, it's built on a modular architecture where themes and plugins act as components, enabling users to extend functionality without altering the core system. Drupal, similar to WordPress, it allows for building websites using reusable modules for added features and functionalities. And if you want to know more about Adobe Experience Manager, which is also a CMS, and in Adobe Experience Manager, or sometimes we call it as AEM, there also we can create functional components. Those functional components are reusable components. For example, text component, text image component, dynamic functionalities also. We can create components, and those components can be reused multiple times on different pages. So that is also one of the example of component based architecture. Then we have cloud native application, serverless architecture, for example AWS Lambda functions. Similar service allow developers to build applications using modular functions that can be deployed independently, right? So these are all components. Consider those components like functionalities and or services, and those services or functionalities can be plugged and played wherever, whenever, wherever we want. Let's see the key characteristics of component based architecture. So modularity. Applications are composed of distinct modules or components, each representing a specific functionality or feature. These separations allow for easier management and understanding of the application. This is the same feature of microservices architecture also, that those different microservices, here we have different components, right? And then they can be reused, right, independent of each other. Reusability. Components can be reused across different parts of the application or even in different projects. This reduces development time and effort. Encapsulation. Each component hides the internal implementation details, exposing only a defined interface for interaction. This promotes better abstraction and reduces the complexity of the overall system. Interoperability. Components can often be designed to work across different platforms and technologies, facilitating integration and collaboration. And loose coupling. Components are designed to be as independent as possible, allowing changes in one component without significantly affecting others. This leads to greater flexibility and easier updates. So takeaway is, whatever functionality we have in the microservices architecture, it is kind of same. Components can be reused, those components can be plugged and played, and one component change will not significantly impact the other component, right? This is the main takeaway. Let's see the benefits of component based architecture. But is of course faster development. You think that components are already built, now we just need to plug them and play them, right? So reusable components can significantly speed up the development process, as teams can focus on integrating existing components rather than building everything from scratch. Now consider a scenario. We have developed a component which will save some data to a external system, whether consider it's a profile data, and we are using this component on the system. Now we are building another application, and this time also we need to save this data to an external system. What we can do, we can just use the same reusable component, right? So development will become faster. Maintainability. Since components are modular, updating or replacing them is easier without affecting the entire system. Scalability. Applications can be scaled by adding or removing components as needed, providing a flexible architecture that can grow with user demands. And enhanced collaboration. Teams can work on different components simultaneously, improving productivity and reducing time to market. So consider we have, that we need to develop 6 to 10 functional components of different features, right? We can divide among those team members. They can work independently, and once they are ready, we can just plug them and then can build the website or any digital platform. So this way we are enhancing the collaboration, enhancing the faster development. We are having scalability. All those aspects are covered if we do that. Let's see the use cases of component based architecture. So for example, one is web application. Many modern web applications utilize component based architecture through frameworks like React, AngularJS, Vue.js, CMS, Adobe Experience Manager, WordPress, right? These all are the examples of component based architecture. Enterprise applications. Large scale enterprise systems often adopt CBA to manage complexity and enhance maintainability across various business functions. So it is a powerful approach, right, for building scalable, maintainable and flexible applications by leveraging reusable components, ultimately leading to more efficient software development processes. Now let's learn domain driven design architecture, DDD. Domain driven design is an approach to software development that emphasizes collaboration between technical and domain expert to create a shared understanding of the business domain. The goal is to model the software based on the domain's complexities, ensuring that the architecture aligns closely with the business needs. Now let's see the key concepts of this architecture TDD. Okay, first key concept is domain. So let's see the definition again. What it says, it's domain driven design. Okay, and what it says, it is an approach to software development that emphasizes collaboration between technical team and then the domain expert. Okay, so now let's go back to the domain. The domain is the specific area of knowledge. So for example, if it is an e-commerce website, domain is e-commerce. If it is life science healthcare website, domain is the healthcare. If it is aviation related website, or it is aerospace related website, if it is finance related website, insurance related website or digital platform, these are domains. Domain is the specific area of knowledge or activity around which the application is centered. It encompasses all the rules, processes and business needs that the software aims to address. Example is, in an e-commerce platform, the domain includes elements like product management, order processing, customer interactions and payment processing. Understanding this domain is crucial for developing features that meet user needs effectively. So now we know what is domain. Second key concept is ubiquitous language. This is a shared vocabulary that both technical team and non-technical stakeholders use to describe the domain. The goal is to ensure that everyone understands the term in the same way, reducing the ambiguity and misunderstandings. Let's see the example. In the e-commerce context, terms like product, order, user, shopping cart, payments are consistently used across discussions, documentation and code, right? For instance, when a developer refers to user, both the business analyst and the developer, they understand it to mean a registered customer of the e-commerce platform. So that is the language. Next key concept is bounded context. A bounded context defines the boundaries within which a particular model applies. It helps isolate different models and prevents ambiguity, ensuring that terms used in one context do not conflict with those in another. Let's see the example. In our e-commerce system, we might have several bounded contexts. One, product management is one context. Order management is another context. User management is another context. Product management is responsible for handling product details, inventory and pricing, whereas order management focused on order creation, order status, payment processing, and user management deals with the user registration, authentication, profile management, etc. Each context has its own distinct model and may interact with one another through well-defined interfaces, APIs, but there is a well-defined boundary also, right? So that is bounded context. Next key concept is entities. Entities are objects that have a distinct identity and life cycle. They are defined not just by their attribute, but also by the continuity and the ability to change over time. Let's see the example. Product. Each product in the e-commerce system has a unique identifier, for example SKU or product ID, right? And can have various attributes like name of the product, description of the product, price. For instance, product A is identified by product ID 12345 or any SKU ID, right? User is another entity. So product is one entity, user is another entity. Each customer has a unique identifier, user ID, profile ID, cognito ID, right? Attributes such as name, email and password. The identity persists even if the user updates their profile information, correct? Now third entity example is order. Each order has a unique order ID tracking its status like pending status, shipping, it's already shipped, etc. Next key concept is value objects. Value objects are immutable objects that are defined solely by their attributes rather than a unique identity. They often represent descriptive aspects of the domain. Let's see the example. Money is one value object. A value object representing an amount and currency, for example, $20, right? It does not have a distinct identity. Instead, it is defined by its properties, like what is the amount, what is the currency, right? Address is another value object. Represents a shipping or billing address with attributes like street, city, and zip code. An address does not have an identity. It is identified by its attributes. Aggregates, another key concept. An aggregate is a cluster of related objects, entities, and value objects that are treated as a single unit of data changes. Each aggregate has a root entity which is responsible for enforcing business rules and maintaining the integrity of the aggregate. Let's see the example. For example, order aggregate, right? We already seen order is an entity, right? The order entity is the root, right? Order, that entity. It may include associated value objects such as payment details of the payment method, shipping address. When an order is placed, changes are made through the order aggregate to ensure consistency. So we see this, right? Aggregate is like a combination of the entity and the value object, how they are associated with each other. That is order aggregate, right? Similar to that, cart aggregate. The cart is the aggregate root managing a collection of cart item value objects. It ensures that all operations like adding or removing items are performed in a consistent manner. So these are aggregates. Then another key concept is repositories. Repositories are abstractions that provide methods for accessing and storing aggregates. Order aggregate, order repository. Product aggregate, product repository. They serve as a bridge between the domain model and data source such as databases. An example is order repository. This repository provides methods like save order or save the order and find the order by ID to persist and retrieve orders from the database. Similar to that, product repository, it offers methods like find by SKU to retrieve product details, encapsulating the data access logic. So now we know we have the repositories, right? Repository we just saw. We have the methods available, but how do we access those repositories? We need services. So domain services encapsulates business logic that does not naturally fit within the entities or value objects. They often perform operations that involve multiple entities or aggregates, right? And we access repositories. Example is order service, payment service. So for example, order service, right? This service contains methods for creating and processing orders. We'll just create the order, we'll just fetch the order. Similar to that, payment service will manage the logic of processing payments, complete the payment, etc. So using services, we will access the repositories and aggregates. Now let's understand domain driven design benefits. Alignment with business goals. This architecture ensures that the software solution closely reflects the real world business processes and rules, facilitating better outcomes. Improved collaboration by using ubiquitous language which technical and non-technical stakeholders, they both can understand. They can collaborate also more effectively. Scalability point of view, it promotes a modular approach, making it easier to scale and adapt the applications as business needs evolve. Enhanced maintainability, the clear separation of concerns, helping in organizing code, making it easier to maintain and evolve over time. Let's see the use cases. This architecture is particularly useful in industries with complex business logic, such as finance industry, healthcare industry, e-commerce industry, where understanding domain knowledge is critical. Domain-driven design is a powerful methodology that focuses on creating a deep understanding of the business domain, enabling developers to build software that effectively meets business needs while maintaining a flexible and maintainable architecture. Hybrid architecture is very famous, a combination of multiple architectures and of course different flavors of architecture. The benefits of different architecture comes into play. Let's understand this architecture. Hybrid architecture is a design approach that combines multiple architectural styles, patterns, or technologies to leverage the strengths of each while addressing the unique requirements of a system. This architecture often integrates on-premises infrastructure with cloud services, allowing for flexibility, scalability, and cost efficiency. And this is the key term, on-premise infrastructure along with cloud services. That's why it is called hybrid architecture. And not only this, we have different type of architectures, right? So getting those flavors also, and then that is also a terminology used for hybrid architecture. Let's see the key characteristics of hybrid architecture. Combination of environments. Hybrid architectures typically integrate both on-premises and cloud-based resources. This allows organizations to maintain critical systems in-house while utilizing cloud services for scalability and flexibility. What is in-house setup? So we know that we have different flavors of infrastructure, like on-premise solution or cloud solution. Cloud is where we have this various cloud providers, namely AWS, GCP, Azure, and they provide different flavor of services, whether it's infrastructure as a service, software as a service, platform as a service, container as a service, right, etc., etc. In-house setup is when organization or enterprise solutions, they build their own in-house setup because of some constraints. For example, they cannot put the sensitive data on public cloud, so that's why they have this in-house setup, right? Hybrid infrastructure cloud architecture is nothing but bringing both together, on-premise solution as well as cloud-based resources, because of some limitation or some compliance related stuff, we cannot bring we cannot put our stuff to cloud, not all, so we will put it on premise or using in-house setup, but we also want to utilize the benefit of cloud-based resources, cloud-based capabilities. So that's why sometimes organizations, they opt for hybrid and type of architecture, right? Flexibility deployment models. Applications can be deployed across various environments, allowing organizations to choose the best hosting options based on specific workload and requirements. Interoperability. Components within a hybrid architecture can interact seamlessly, whether they reside in the cloud or on-premise. This requires well-defined APIs and communication protocols. So of course, I mean, how we are going to achieve this? So for example, whitelisting of APIs, etc., that connection is happening or not, the inbound entries, outbound entries, all those technical terms will happen, but the main concept is this hosting of the whole application, the solution, whether it's a distributed solution where we have different external systems which we want to integrate with, right? So some services will be hosted on premise, some services will be hosted on cloud, and that is the whole takeaway from hybrid architecture. Data management. Hybrid architecture can manage data across different environments, enabling organizations to leverage cloud storage for backup and recovery while keeping sensitive data on premises. Applications like, for example, legal related applications, government related applications, defense related applications, where the data is so sensitive they cannot put it on cloud, they put it on premise, and then they just have some data which they can put on cloud for recovery purpose. Scalability and resilience. By utilizing cloud resources, organizations can scale applications quickly to handle increased demand while maintaining the resilience of critical systems in a controlled environment. Now let's see the benefits of this architecture. Cost efficiency. Organizations can optimize cost by utilizing cloud resources for variable workloads while keeping essential systems in-house, right? And we know that cloud solution is always cost effective because we have so many options available. For example, pay-as-you-go subscription, auto scaling feature. If we don't need more servers, we can just it will automatically scale down the resources. and scale up when it is required. So we will pay whatever we use. So cost efficiency, improved agility. Hybrid architectures allow organizations to respond quickly to changing business needs by leveraging cloud capabilities for rapid deployment and scaling. Enhanced security. Sensitive data can be kept on premises. So this way we are securing, we are enhancing the security, while less critical workloads can take advantage of cloud resources, providing a balanced approach to security. Then flexibility. Organizations can choose the best environment for each component of their applications based on performance, compliance, and cost. Right. So these are the advantages. Let's see the use cases of hybrid architecture now. Enterprise applications. Many enterprises adopt hybrid architecture to manage legacy systems while integrating new cloud-based applications. Disaster recovery is one of the popular use case. Organizations can implement cloud-based backups and recovery solutions while maintaining primary operations on-premise. So they just use cloud-native technology just for the backup purpose, but the application is actually running on their on-premise solution. If they need that data just to recover something because of some disaster, they just use those cloud based technology. For example, S3 is very popular technology to keep the backup of the data. This is object storage service. Data analytics. Hybrid architecture allow organizations to process large data sets in the cloud while keeping sensitive data on premise. So hybrid architecture provides a versatile approach that combines the benefits of both cloud and on-premise solutions, enabling organizations to optimize their infrastructure for performance, cost, and compliance. Command query responsibility segregation, CQRS architectural style is also one of the popular architecture style or pattern. So CQRS is an architectural pattern that separates the handling of data modification operations, commands, from data retrieval operations, queries. This separation allows for more optimized, scalable, and maintainable applications by treating these two aspects differently. So main two key things here: data modification operation. When you want to modify something, that operation is command. Data retrieval operation, whenever we want to retrieve some data, we want to get some data, that is query. Okay, let's understand it. And this is this separation. So this separation allows for more optimized, scalable, and maintainable applications by treating these two aspects differently. Let's learn them. Now let's understand CQRS with its key components. We'll understand it with one example. Example is we have an e-commerce system. Let's understand with CQRS how it will behave. So in our e-commerce platform, users interact with two main functionalities. One is placing orders and another one is viewing products. Okay, they see the product and they finally place the order. To effectively manage these interactions, we apply the CQRS pattern, which separates the process that modify the data means commands, and then retrieve the data means queries. That is the pattern, right? So commands are operations that change the state of the application, means update the data. They represent intentions and are executed to modify data. Commands do not return data. Instead, they may return a success or failure response. So for example, creating an order. When a user places an order, they submit a command that includes details like user ID, the items they want to purchase, and payment information. This command is processed to create the order in the system. Or another example is updating a product. If a product's price or description needs to be changed, an update command is issued which contains the product ID and the new details. Second concept is command handlers. Each command is processed by a dedicated command handler. This command contains the business logic necessary to handle the command and effect the required changes. So for example, the order creation handler takes the order command, validates the information, and saves the new order to the database. Then we have queries to fetch the data, right? Queries are operations that retrieve data without modifying it. They are optimized for reading and can return data in various formats or structures tailored to specific needs. For example, retrieving an order, a query could be issued to fetch details about a specific order based on order ID, returning information such as the order status and items purchased. Another example could be listing products. Another query might be used to get a list of all available products, including the names, price, and description. Similarly, we have query handlers. So each query is handled by a specific query handler, which is responsible for retrieving the necessary data and returning it to the requester. For example, the order retrieval handler takes the order query, assesses the database to fetch the required order details and formats them for presentation. Now, concepts are separation of models. CQRS often involves using different models for commands and queries. So different models will be there for command type of for type of commands means data updation, data insertion, queries for fetching the data. The command model focuses on business logic and validation, while the query model is optimized for data retrieval. And read and write databases. In many implementations, CQRS employs separate databases for read and write operations, allowing for optimization based on the specific needs of queries and commands. Now let's see the benefits of this model. Scalability. The separation of commands and queries allows each to be scaled independently, making it easier to optimize performance for different workloads. Performance. By optimizing read and write models separately, applications can achieve better performance and responsiveness. Flexibility. Changes to the read or write side can be made independently, allowing for easier evolution of the system. Enhanced security. Permissions can be managed separately for commands and queries, improving the security. Let's see the use case of CQRS. Complex domains. CQRS is particularly useful in applications with complex business logic, where read and write operations can be significantly different in terms of performance and requirements. Microservices architecture. CQRS fits well with microservices, where individual services can manage their own commands and queries. CQRS provides a powerful approach to building applications that require clear separation between data modification and retrieval, leading to enhanced scalability, performance, and maintainability. Let's learn peer-to-peer architecture, or we call it as P2P. Peer-to-peer architecture is a decentralized model in which each participant, which is peer, in the network can act as both a client and a server. This architecture allows peers to share resources, data, and services directly with one another without relying on a central server. Now let's see the key characteristics of this architecture. First thing is decentralization. There is no central authority or server. Each peer can connect to and communicate with any other peer in the network, promoting autonomy and resilience. Equal roles. Every peer has equal capabilities. They can initiate and respond to requests, share resources, and contribute to the network's overall functionality. Direct communication. Peers communicate directly with each other, which can enhance performance and reduce latency by eliminating intermediaries. Dynamic participation. Peers can join and leave the network at any time without disrupting the overall operation, allowing for flexibility and scalability. Resource sharing. Peers can share various resources such as files, processing power, or bandwidth, contributing to the collective capability of the network. And let's understand this with a very simple example. So we all use Git, right? The GitHub. So what we do? We create repositories, right? So GitHub provides centralized hosting service. Users can still clone repositories and collaborate directly with each other. That is P2P only, right? I mean, I can clone a repository which is already created by one of my peer, I can do some commit to those changes, right? So I'm directly connecting with my peer, right? So this is a straightforward example of this peer-to-peer architecture. What is the benefit of this architecture? Scalability. P2P networks can easily scale as new peers join, distributing the load among all participants. Resilience. The absence of a central point of failure means the network can continue to operate even if some peers go offline. So in the centralized server, the issue was if that centralized server is having some issue, the whole network connectivity is lost. But here we have peer-to-peer connection. It means all those peers are individually, they can connect with other peers. So if something goes wrong with one of the peer, still the other peers are working fine. Kind of microservices architecture again, a little bit of flavor of that only. Cost efficiency reduces the need for centralized infrastructure, lowering operational costs and resilience and reliance on server maintenance. Increased privacy. P2P architecture can offer enhanced privacy for users as data can be shared directly without passing through a central server. Let's see the use cases of this architecture. File sharing. P2P networks are widely used for file sharing applications like BitTorrent, where users can download and upload files directly to and from each other. Blockchain and cryptocurrencies. Many cryptocurrencies like Bitcoin utilize P2P architecture to enable decentralized transactions and maintain the integrity of the blockchain. Communication. P2P technologies are used in applications like Skype, where users can communicate directly without routing through a central server. Peer-to-peer architecture offers a robust and flexible model for building decentralized applications, enhancing scalability, resilience, and efficiency in resource sharing. Now let's learn this architecture, which is data-centric architecture. Data-centric architecture is an architectural approach that prioritizes data management and organization as the core aspect of the system. So data is the main focus. In this architecture, the data is central to the application's design, driving the way that components interact and operate. Let's see this with some example. So, okay, Netflix is popular. How Netflix uses data-centric approach, data-centric architecture. Netflix utilizes a centralized data platform that stores vast amount of user data, including viewing habits, preferences, ratings. This data is crucial for understanding user behavior and tailoring content recommendations. Right? So we watch this movie next time. Netflix will recommend, okay, you have watched this earlier. Based on that, these are more titles that you can consider. So when a user logs into Netflix, the platform immediately uses the centralized data to provide personalized recommendations based on the viewing history, ratings, and preferences. This data-centric approach not only improves user satisfaction but also drives engagement and retentions. And by leveraging this architecture, Netflix effectively manages vast amount of data to create a personalized data and seamless streaming experience for users. Let's see the key characteristics of this architecture. Centralized data management. The architecture focuses on a central repository where data is stored, accessed, and managed. This can be a database, data warehouse, or another form of data store. Data as a first-class citizen. In data-centric architecture, data is treated as primary entity. Business logic and functionality are designed around data management, retrieval, and manipulation. Loose coupling. Components of the system are loosely coupled, means they do not rely on each other, meaning that changes to one component, for example data model, right, have minimal impact on others. This enhances maintainability and flexibility. The architecture emphasizes how data flows through the system, focusing on data processing pipelines, transformation, and storage rather than on individual components. And then abstraction layers. often includes layers of abstractions that separate data access, processing, and presentation, allowing for easier changes and upgrades to individual layers without affecting the entire system. So, in nutshell, what we have just talked about, this data-centric approach is nothing but consider there is a data repository which is centralized, and all the software, whether those are clients or functionalities, they are getting the information from this common repository. The main focus is here on the data center with the repository where the data is stored, right? So for example, in Netflix example, the data is stored, the user rating, preferences, etc., and whatever information we need. So for example, fetch ratings, this is fetching rating is one of the function, fetching user preference is another functions, but all in all that data is stored in one repository. Let's see the benefits of this architecture. Enhanced data management. Centralizing data makes it easier to enforce data governance, consistency, and integrity. Scalability. The architecture can be scaled by enhancing the data storage or processing capabilities independently of the application logic. Of course, because the data is already centralized, so if you want to scale it, we just need to add more resources to the same database. Improved performance. Optimizing data access and management can lead to improved overall application performance, because all applications are accessing the same database. So if we are increasing or optimizing it in terms of scaling or adding more resources to it, since that is the only resource, the repository which is holding all the data, so of course the performance will increase. Simplified development. Developers can focus on data related concerns, which can simplify the design and implementation process. Let's see the use case of this type of architecture. Data warehousing. Systems designed for data analysis and reporting often use data centric architecture to manage large volume of data efficiently. Business intelligence applications, or sometimes we call it BI applications, right? Applications that require extensive data manipulation and reporting leverage data-centric design to provide insights from data. So what we do first, we ingest the data into some warehouse, right? And then we have analytics tools. So for example, Power BI or any analytics tool. With that huge data, we do the analysis of that data. So that is also a good use case. Then we have CMS, content management system. CMS platforms often prioritize data storage and retrieval structure, the application around how content is managed and accessed. So we can have a repository within content within a CMS, right? There we can have centralized data. So for example, within Adobe Experience Manager is one of the CMS which uses JCR to store the data, right? That is also use case. So data-centric architecture is an effective approach for applications that require robust data management and organization, providing clear focus on data as the core element driving application functionality. Now let's understand what is thin client architecture. Thin client architecture is a client-server model where the client or the front end performs minimal processing. That's why it's thin, right? Thin, thick. So thick part is the backend server, thin is client or the front end. So the front end performs minimal processing and relies heavily on the server, which is backend, for most of its computing tasks. In this architecture, the client typically runs a lightweight application that interacts with the server to access resources and services. One of the lightweight application example is the browser. So for example, Chrome, right? Now let's understand thin client architecture with one example. So we all know how Google Workspace implements the thin architecture. Let's understand this. In a thin client setup, most of the processing occurs on the server rather than the client device. Google Workspace applications like Google Docs, Sheets or Slides run primarily in a web browser. The client, which is user's device, requires minimal local resources, since most of the functionalities are handled on Google server. So what we need is just a browser, we sign in and then we start using Google Docs, etc. It's thin on front end side because most of the calculation, all those business logic is done using Google backend server. Now the application point of view, a team of remote workers can use Google Docs to collaboratively write a report. Each member accesses the document through their web browsers, making edits in real time. The heavy lifting part, such as saving changes, version control, data processing, etc., occurs on Google server, allowing even users with low specs device to contribute effectively. Right? A browser can be opened very easily, right? And we can access Google documents. Now let's understand the key characteristics of thin client architecture. First thing is minimal client processing. The client device has limited processing power and relies on the server for executing application and managing data. Most processing occur on the server. Centralized management. Applications and data are hosted on a central server, simplifying management, updates and maintenance since changes are made at the server level rather than on individual client devices. Reduced hardware requirement. The client can be low cost devices with minimal hardware specifications since they do not need to run heavy applications locally. Network dependency. The performance of thin client is heavily dependent on the network's speed and reliability, as they require constant communication with the server. So for example, Google Docs example, we always need an internet connection for that. Until we have internet, we cannot work, right? So we need network, it is dependent on network. Increased security. Data is stored on the server rather than on client devices, reducing the risk of data loss or theft from individual clients. Now let's understand the benefits of this architecture. First thing is cost effectiveness. Thin clients are generally less expensive to purchase and maintain compared to traditional desktop computers. Easier maintenance. Since applications are centrally managed, updates and patches can be deployed quickly across all clients. Enhanced security. Centralized data storage minimizes the risk of data breaches and simplifies backup processes. Scalability. Organizations can easily scale their infrastructure by adding more thin clients without significant changes to the server setup. One use case we have already explored. Let's see more use cases of thin client architecture. Enterprise environments. Thin client architecture is commonly used in businesses where employees need access to application and data but do not require powerful individual machines. So for example, web-based applications. VDI solutions often utilize thin client architecture to provide users with access to virtual desktops hosted on a central server. Remote work. Thin client enables remote access to applications and data, allowing users to work from various locations without needing powerful local devices. So thin client architecture offers a streamlined and cost-effective approach to computing, particularly suited for environments that prioritizes centralized management, security and efficiency. Rich client architecture. Now understand what is rich client architecture. Rich client architecture refers to a client server model where the client or front end is capable of performing significant processing tasks locally, providing a rich user interface and a responsive experience. In this architecture, the client application is often a standalone software that can interact with servers to access data and services. Previously, we learned about thin client architecture, where most of the business logic is handled by the servers, but the rich client architecture is reverse, where most of the logic will be done via front end or the client as well. Right? Let's see the examples. Microsoft Outlook. So Outlook is primarily a desktop application that performs significant processing locally. It can handle complex tasks such as managing emails, calendars, contacts without relying heavily on a server for every action. And we know even if we are not connected to the network, we can still use the Outlook. At least we can draft the email, check the calendar. Though the calendar needs sync, but yeah, if the network is going on and off, we can still, if it is synced, we can work in Outlook. The application provides a rich user interface with features like drag and drop, advanced formatting, customizable view, which enhance user experience and interactivity. The use case is a person uses Microsoft Outlook to manage his emails, schedule meetings, and maintains a task list. He can draft and send emails, check his calendar, message, and manage contacts, all from the Outlook client on his desktop, even without an internet connection. He can access his emails and calendar, and any changes made will sync with the server when he reconnects with the internet. So with this example, it is a rich client architecture example. Now let's understand the key characteristics of rich client architecture. First thing is local processing. Rich clients perform most of the data processing and business logic on the client side. So it's reverse of thin client architecture, reducing the load on the server and providing a faster response time. Enhanced user experience. Rich clients typically offer a more interactive and responsive user interface, often utilizing advanced graphics and multimedia capabilities. Offline capabilities. Many rich client applications can function without a constant connection to the server, allowing users to access and manipulate data offline, syncing changes when they reconnect. And if we see, there is a web browser version also available of Microsoft 365 for Outlook that will go to thin client architecture. If it is a desktop application, then it will come to the rich client architecture. Complex functionality. Rich clients can handle complex tasks and computations locally, making them suitable for applications requiring heavy processing or extensive user interaction. Integration with local resources. These applications can access local resources such as file system, hardware, and peripheral devices, providing a seamless experience. Now let's understand the benefits of rich client architecture. Performance. Rich clients can deliver fast performance by reducing server load and minimizing latency in user interaction. User experience. The ability to provide a highly interactive and responsive UI enhances user satisfaction and engagement. Flexibility. Users can work offline and synchronize data later, making rich clients suitable for environments with intermittent connectivity. Functionality. Rich clients can support advanced features like drag and drop, animations, and real-time updates. Now let's understand the use cases of rich client architecture. The very first use case is desktop applications. Many traditional desktop applications such as word processors, graphic design tools follow a rich client architecture. Gaming. Video games often utilize rich client architecture to provide immersive and responsive experiences. Business software. Applications like customer relationship management, CRM, enterprise resource planning, ERP systems often benefit from rich client functionality. So finally, rich client architecture is popular in scenarios where high performance, interactivity, and offline capabilities are essential, making it suitable for a wide range of applications across various industries. Event sourcing architecture. Let's understand what is this architecture. Event sourcing architecture is an architectural pattern that stores the state of an application as a sequence of events. Event sourcing, so sequence of events, rather than as a current state. Each event represents a change or action that has occurred in the system, allowing for a complete historical record of all changes. Let's understand this architecture with one use case. Order management is the use case. Let's consider an order management system for an e-commerce platform where customers can place, update, and cancel their orders. Here is how the event sourcing architecture can be structured and utilized in this scenario. And we are also going to discuss in this scenario only, we are also going to cover the key components of this architecture. So first one is the command layer. where we will have the commands as well as the handlers, actions that change the state of the application. Below can be the actions: place order command, cancel order command, ship order command. And the handler would be basically what is the business logic written to handle each of those command. These can be the handlers, right? So this is one layer. Then event store. Events would be order placed, order cancelled, order shipped, right? And stored in a database designed for high write loads. Like, I mean, these are the examples. There are multiple databases. Cassandra is one of that database. For event store, we can use that. After event read model, basically projects denormalized representation of data based on events. So for example, current orders for a user or order history are typically stored in some database. It can be relational or NoSQL database. We will have event bus, and we will have user interface, whether it's a web application or mobile application. Let's understand this whole order management with the workflow. What are the steps of doneness will happen. So user action: a customer places an order by submitting a place order command after filling their card. Then command handling will happen. The handler validates inventory and payment, then creates an order placed event with order details. Storing the events: the order placed event is saved in the event store. Event publishing: the event is published via the event bus. Event handling: we will have projection service and we have notification service. So the projection service update the read model with the new order, and notification service sends an email confirmation to the customer, right? And then user queries: the user query the read model to view their orders. Handling changes: if the customer cancels, a cancel order command is issued, processed, and order cancelled event is published. Reconstruction of state: the system can replay stored events to reconstruct their order history if needed. So we see that how this architecture style is placed for this use case. Let's see the key characteristics of this architecture. So we know now event storage. Instead of storing just the current state of an object, all changes are captured as events and stored in an event store. This provides a comprehensive history of all actions taken. We have already seen that: order placed, order cancelled, right? Immutable events: once an event is stored, it is immutable, meaning it cannot be changed or deleted. This ensures a reliable audit trail of changes. So every time an event is happening, it is added to the book. We are not overriding it because it is immutable. State reconstruction: the current state of an application can be reconstructed by replaying the sequence of stored events. This allows for various representations of the state at any point in time. And separation of concerns: of course, business logic is often separated from the data storage logic, allowing for cleaner code and easier maintenance. And of course, it's event driven communication, right? Event sourcing often works well with event driven architecture, where different components communicate through events, enabling loose coupling. So I am always saying that whenever we actually work for any project or opportunity, we combine different flavors of architecture, and then it is always a tailored architecture. Let's see the benefits of this architecture. Auditability perspective: yes, the complete history of changes provides a robust audit trail, making it easy to track what happened and when. Flexibility: systems can evolve over time. New features can be added by processing existing events without altering the stored data. Debugging and testing: historical events make it easier to reproduce scenarios for debugging and testing. So for example, some issue came while the order is placed. Now we know with the audit trail that these are the events had happened earlier. We can replicate the same issue again with the same type of steps. Decoupled architecture: components can be developed and deployed independently, responding to events as they occur. Let's see the use cases of this architecture. very important, financial application, because we need to keep all those records in the book. Financial applications event sourcing is commonly used in banking and finance system when a complete history of transactions is critical. E-commerce system, in e-commerce platforms, capturing user actions as events help track orders, states and changes effectively. Collaborative applications, applications that require tracking changes made by multiple users, document editors, right, can benefit from event sourcing. Yeah, whenever we want to track those events, the sequence of those events, right, we should consider this architecture. Event sourcing architecture is a powerful approach for applications that require a detailed history of changes and enhanced flexibility in managing state, making it suitable for various domains where tracking and auditing are essential. Aspect oriented architecture, or AOA. So let's first understand this key term, cross-cutting concerns. A cross-cutting concern refers to a behavior or functionality in a software application that affects multiple parts of the application, but is not confined to a single module or layer. These concerns typically cut across various components and are not neatly encapsulated within a specific functionality. So let's see with example. So for example, logging, right? Whenever we build a functionality, we record various events, right, through logging. So that is logging. Recording information about application behavior, errors, performance metrics is needed in many places throughout the code, but it does not belong to any specific business logic. So logging is one of them. Security, authentication and authorization processes need to be enforced across various components of an application, but they are not tied to any single functionality. Error handling, managing exceptions and error reporting often needs to happen in multiple areas, yet it does not relate directly to the core functionality of those areas. Transaction management, in applications that interact with the databases, ensuring that a series of operations are completed successfully is crucial, but it spans multiple services or methods. Then performance monitoring, tracking the performance of different parts of an application can apply broadly on and needs to be implemented in various components. So these are the examples of cross-cutting concerns. Now let's come back. Aspect-oriented architecture is a programming paradigm that aims to increase modularity by allowing the separation of cross-cutting concerns. We want to keep them aside. Concerns that affect multiple parts of systems such as logging, security, error handling from the main business logic. So we want to concentrate on the main business logic. This architecture promotes the use of aspects to encapsulate these concerns. Let's see the key characteristics of AOA. Separation of concerns. AOA enables developers to separate cross-cutting concerns from the main application logic, allowing for cleaner and more maintainable code. Then we have aspects. Aspects are modules that define behavior that can be applied at certain points in the program, such as method call, object instantiations, etc. And then we have join points. These are specific points in the execution of the program where an aspect's behavior can be applied, such as before, after, around method execution. Then we have advice. Advice refers to the code that is executed at a join point. Join point we just understood, right? The before, after, around. These are different types of there are different types of advice, including before, after and around advice, each specifying when the aspect code should run. And then we have point cuts. Point cuts define the conditions under which advice should be executed, allowing developers to specify which join points to target. Let's see the benefits of this architecture. One is the improved modularity by encapsulating cross-cutting concerns. AOA promotes cleaner code and improved separation of responsibilities. Reusability. Aspects can be reused across different parts of the application or even across multiple applications, enhancing code reuse. easier maintenance, changes to cross-cutting concerns can be made to one place, reducing the risk of introducing bugs when modifying related code scattered throughout the application, and of course the enhanced readability, because the main business logic remains uncluttered, making the code base easier to read and understand. Let's see the use cases. Logging and monitoring, implementing logging across various modules without scattering logging code throughout the business logic. Security, applying security checks across multiple methods and components without duplicating code. Transaction management, managing transactions in a consistent manner across various services and operations. And error handling, centralized error handling mechanism to improve maintainability. Space-based architecture. Space-based architecture, or SBA, is a design approach that aims to address scalability and performance challenges by distributing application components across a network of nodes. It utilizes a shared memory space. This is a keyword, shared memory space, allowing multiple instances of application components to operate in a distributed environment without relying heavily on a centralized database. Let's see the key concepts of this architecture. Space as medium. In this architecture, the space refers to a shared distributed memory, like in-memory data grid, where application components can read and write data. So space is equal to like shared memory. Decoupling. By separating components from each other, SBA minimizes dependencies, allowing different parts of the application to evolve independently. So loose coupling is also there. Then we have horizontal scaling. SBA allows applications to scale out by adding more instances of components or agents that can access the shared space. We have load balancing. SBA inherently support load balancing, reducing the risk of any single point of failure. And then replication, data in the shared space can be replicated across different nodes to enhance reliability and availability. Then we have distributed computing. Components of the applications are distributed across multiple nodes, allowing for parallel processing and increased throughput. In-memory data grid, it typically uses as in-memory data grid to provide a shared memory space where data can be stored and accessed quickly, minimizing the need for disk I/O. Scalability, the architecture supports horizontal scaling, like I said earlier, enabling the addition of more nodes to handle increased load without significant architectural changes. Let's see the example of this architecture. E-commerce application. Imagine an e-commerce platform that experiences variables load during peak shopping season, right? So shared space, first is shared space. The application uses a distributed in-memory data grid. Like there are multiple, Apache Ignite is one of the popular ones, as the shared space to store session data. Another example could be Redis also. That is also a good example. Product information and shopping cart content. Decouple components, order processing service, inventory service, and user service. These are the different components, and they are accessing this shared space. So shared space is nothing but the in-memory like a temporary storage, and all these decoupled components, they are accessing this shared space. Now order processing service, this service handles order placement, payment, processing. It reads from the shared space to retrieve product detail and update the order status. Inventory service will manage the stock levels. It also interacts with the shared space to update inventory count. And user service finally will manage user profile and shopping cart data stored in the shared space. Now there were concepts like horizontal scaling, load balancing, and data replication within this architecture. So during peak time, additional instances of each service can be deployed. Each service means, for example, we have order processing service, inventory service, user service, right? These services. If the order processing services sees increased traffic, more instances can be spun up to handle incoming requests. Load balancing, requests to the order processing services are distributed across all available instances. The shared space ensures that each instance can access the latest product and order information, allowing them to work independently yet cohesively. And data replication, the shared space replicates data across nodes to ensure high availability. Nodes means we have similar type of data, but we have created multiple replicas, right? If one node fails, means one of the instance fails, we have replicas available, so other can continue processing without any data loss. And this is the feature of cloud computing, like creation of a replica of the database to multiple availability zones or multiple regions. You see the benefits of this architecture. Of course, high performance by keeping data in memory and distributing workloads. SBA can achieve low latency and high throughput. Scalability, the ability to add more nodes easily allows organizations to scale their applications to meet growing demand. It means, for example, today I know that these many users are accessing the application, and this is the database, right, which is the shared space, is working fine, but tomorrow we have more load, we can just create another replica and then we can put load balancer so that those requests will be served by another replicas. Fault tolerance, the distributed nature of the architecture can improve resilience, as the failure of one node does not impact the entire system. Flexibility, applications can be modified or extended without significant disruptions thanks to the decoupled architecture. So we have decoupled architecture as well here. Okay, let's see the use cases. Real-time analytics. Applications requiring high-speed data processing such as financial services analytics platform can benefit from this architecture. Then we have e-commerce platform. Online retailers can utilize this architecture to handle large volume of transactions and user interactions without performance degradation. IoT applications, Internet of Things systems that need to process and analyze large streams of data in real time can leverage this architecture. So in summary, this architecture is particularly effective in environment where high scalability, performance and resilience are critical, making it suitable for a variety of applications across different industries. Pipe and filter architecture. Pipe and filter architecture is a design pattern that separates the processing of data into distinct stages known as filters, which are connected by conduits called pipes. Each filter performs a specific transformation or processing task on the data it receives, and the pipes transform the data from one filter to another filter. So filters are doing some processing and pipes are just transforming that data from one filter to another filter, and filter is some processing. Let's see this with one example. Let's imagine we have an image processing pipeline. Consider a simple image processing application that applies various transformations to an image. This application can be modeled using the pipe and filter architecture. So what will happen? We want to apply various filter to the image acquisition filter. First time image will load on that application, right? Then we want to apply some gray scale filters to that image, then some blur effects, that is another filter. Then we want to do some edge detection of any blur images. Finally we want to display that image, right? So these are the filters which are like different processing. So for example, converting that image to grayscale, blurring the image, these are all filters. And the data flow would be like loading the image, converting it to grayscale filter, blur filter, etc., right? Those are pipelines. Let's see the characteristics of this architecture. Each filter encapsulates a specific functionality, allowing for clear separation between different processing stages. So, right, one function or one filter is only responsible for blurring the image. Then data flows through pipes connecting filters, creating a linear or network structure for processing stream of data. Then filters And you know these flows could also be, for example, we can have another type of subscription based architecture here. So for example, we are using AWS SQS, one event is happening, we are just putting that message to SQS, and then another subscriber is receiving that and doing some taking some action on it, right? So again we are mixing a couple of architectures, tailoring the architecture basically. Then filters transform the data they receive, producing output that can be passed to subsequent filters for further processing. Filters are loosely coupled. They can be added, removed, or modified without significantly affect other components in the system. So for example, we loaded the image, then we changed it to grayscale, then we blurred the image, but we can just remove the grayscale one. We can directly load the image and use the blur effect, right? So anytime we can filters can be removed or added. Filters can be reused across different applications or workflows, enhancing modularity and maintainability. Pipe and filter architecture benefits. Let's see the benefits. Modularity, that is the very significant benefit of this architecture. The architecture promotes modular design, making it easier to manage, understand and maintain each component. It's of course flexible. New filters can be introduced or existing ones modified without impacting the entire system. It is scalable because the architecture can be scaled by adding more filters or optimizing existing ones to handle large data volumes, and it provides parallel processing because filters can operate in parallel, improving performance and throughput when processing data streams. Let's see the use cases. So data processing pipelines, commonly used in data processing applications such as ETL type of job in data warehousing, right? First we want to do extraction, then we want to do transformation, then we want to load it to somewhere. So these are the filters, right? Then media processing, we just saw one example, used in audio and video processing applications where each filter performs a specific transformation, encoding, filtering, rendering, etc. Network protocols, applied in network systems where data packets are processed through a series of filters to transform or analyze network traffic. So all in all, this architecture is particularly effective for applications that require clear data processing workflow steps of doneness, enhancing modularity, maintainability while allowing for flexible data transformation. Grid computing architecture. Grid computing architecture is a distributed computing model that harnesses the power of multiple geographically dispersed computers to work together on complex tasks. This architecture allows for resources sharing across network, providing a unified view of the combined computing power and data resources. Let's see the example. Example is scientific research grid, a system for analyzing large data sets, like for example genomic sequencing, using interconnected computers. So there are computers distributed on distributed network. Now components, let's see the components. Resource nodes, multiple computers, for example university cluster, supercomputers providing processing power, but these are scattered, these nodes, these computers are scattered. Then grid middleware, software that manages resource allocation and job scheduling. Data storage, distributed file system for shared access. And then we have user interfaces, tools for researchers to submit jobs and monitor progress. And we have job scheduler, assign tasks to available resources based on load and availability. And let's see the data flow. What will happen? Job submission. Researcher will first submit a task. Then this job scheduler divides the task and assigns task to nodes. Nodes are basically different multiple computers. Computers process tasks concurrently. Then what will happen? Results are collected and combined. So multiple computers were working and the data, the results will be collected and combined. And finally the researcher retrieves final output. So what we have seen in this architecture, that multiple nodes are working in parallel, right? Multiple nodes are working in parallel in distributed computing model, and finally we are getting the they are sharing this, they are accessing the shared resource over network, and finally getting a unified view of the combined computing power. Okay, let's see the characteristics of this type of architecture. We know resource pooling. Grid computing enables the pooling of resources, CPU storage, etc. from multiple locations, allowing users to access and utilize them as needed. Then resources are distributed across different sites and can include various types of hardware and software, promoting flexibility and scalability. Grid architecture support interoperability among diverse systems and platforms, enabling different types of resources to work together seamlessly. Then we have dynamic resource allocation. We just have seen that resources can be allocated dynamically based on demand, allowing for efficient use of available computation power. And then we have high throughput, because of course the combined power of multiple computers. Let's see the benefits of this architecture. Scalable. It is a scalable architecture. Grid computer can scale easily by adding more resources, accommodating growing workloads without significant reconfiguration. It's cost effective. Collaboration, of course it's collaborative because multiple nodes were working in parallel. Fault tolerant. The distributed nature can provide resilience up to some mark, as the failure of one resource will of course not impact the overall system significantly, though it might impact. Consider a scenario where different nodes are working but for different calculation, and finally we are aggregating the data and one of the node fails, then this architecture might also fail in that case. So we need to consider what is the business use case. So let's see where this architecture fits. Scientific research, widely used in scientific computing for tasks such as simulations, modeling, data analysis, fields like physics, chemistry, biology, all these fields. Financial modeling, used in finance for complex risk assessments and simulations that require significant computational resources. Then for data analysis, suitable for large scale data processing tasks such as big data analytics, machine learning, and then collaborative projects, of course. So all in all, this architecture is particularly effective for applications that require significant processing power and resource sharing, making it a valuable solution for in various domains. Cloud computing architecture, and this is I think very famous architecture. Most of the people in IT, they know what is this architecture all about. Cloud computing architecture refers to the comprehensive framework that enables the delivery of cloud services such as infrastructure, platform, software over the internet. This architecture consists of various components including hardware, software and network resources that work together to provide scalable and on-demand computing resources. Let's see the key characteristics of this architecture. So first is service models. What type of service models this architecture provides? And what I have done, I have created a table because we have different offerings for this architecture. For example, we have infrastructure as a service, platform as a service, software as a service, function as a service, container as a service. These are all the service models available. And let's understand with some description and example. Infrastructure as a service, it provides virtualized computing resources over the internet, allowing users to manage operating systems and applications. Okay, and examples are AWS EC2, Google Compute Engineer. So consider if you have used VM, virtual machine, right, or remote desktop. That is one of the example of infrastructure as a service. Platform as a service offers a platform allowing developers to build, deploy and manage applications without worrying about the underlying infrastructure. And the examples are Google App Engine, Microsoft Azure App Service, etc. Right? So this cloud will provide you the platform and you will just work on on the application, whatever application you want to deploy. Then we have software as a service. It delivers software applications over the internet, accessible through web browsers, eliminating the need for local installation. Example is Gmail is very popular example. Gmail, Google Docs, Microsoft 365. Those are all our examples. We just need to use the software. Then we have function as a service, a serverless computing model that allows developers to run code in response to events without managing servers, automatically scaling as needed. So one thing to note here, we are talking about right now cloud architecture, right? But here we are also discussing serverless architecture. Like I said earlier, we always combine different flavors of architecture when we design any application. And serverless function as a service examples could be AWS Lambda, Google Cloud Functions, etc. So as many requests are coming, as many instances of Lambda functions will be created, right? So and no need to manage, it's managed by AWS. So function as a service. Okay, container as a service. It provides a container management service that enables users to deploy and manage containerized applications, another architecture type. Containerized is also an architecture type, so that is also common. So we can create package and then we can use the container to deploy those packages. Examples would be very popular is like, for example, Kubernetes, and then Amazon Elastic Kubernetes Service, EKS, etc. Those are the popular services provided by AWS, GCP, Azure. Now let's see the deployment models. So deployment models also I kept in a table format. So we have different deployment models within cloud. We have public cloud, private cloud, hybrid cloud, multi-cloud. Public cloud is services are delivered over the public internet. That's why it's public cloud and shared among multiple organizations. Not built to a specific organization, it's built for public usage. Examples are AWS, Microsoft Azure, Google Cloud, those are all public cloud. And of course the benefits are that these are cost effective, scalable, accessible, no need for physical infrastructure, pay-as-you-go subscription, whatever features we have on cloud computing, right? No need to decide right away what do you need, you can just increase auto scaling, all those features are there. Then private cloud. Private cloud is dedicated infrastructure for a single organization, providing enhanced control and security. So it is just for one organization, they have created their own cloud. No one can access that. And examples are VMware, private cloud, OpenStack. So these cloud, they provide private cloud option as well. And the benefits are of course the greater control, security, because no one can access. Even the hardware is, you are only utilizing the hardware, no one is having access at all. And tailored resource for specific needs. Then we have hybrid cloud. Basically this one and this one, combination of these two, combines public and private clouds, allowing data and applications to be shared between them. And the examples are of course AWS, Google, Azure. They all provide hybrid cloud as well. Okay, benefits would be flexibility to manage workloads, optimize resources use, etc. And finally we have the multi-cloud option, which is utilizes services from multiple cloud providers to enhance flexibility and avoid vendor lock-in. So it means using AWS services, Google Cloud services, Azure services, right? Other characteristics would be of course all the cloud features will come into play. Scalability. Cloud architecture allow for elastic scaling, auto scaling, upscaling, downscaling, meaning resources can be provisioned for or deprovisioned as needed to handle varying workloads. Today I am having 100 users, so I need maybe lesser size of VM. Tomorrow I am having thousands of users, so I just increase the size of my VM. It is just that can be configured automated way. Multi-tenancy means multiple users, organizations share the same infrastructure when maintaining data isolation and security. Optimizing resource usage. It means they have these cloud providers, they have the data centers, and it is possible that if you are using the public cloud, that more than one organization is using the same hardware, that is multi-tenancy. Virtualization technology underlies cloud computing, enabling the creation of virtual machine and efficient resource allocation. Just within a few clicks you can create a new virtual machine, new desktop of any of the type, right? So that is one of the capability. Let's see the benefits of this architecture. Cost efficiency. It reduces the need for upfront capital investment in hardware and allow organizations to pay only for what they use. Services can be accessed from anywhere with an internet connection, facilitating remote work and collaboration. Organizations can quickly scale resources up or down based on demand, ensuring agility in responding to changing business needs. And cloud providers manage update and maintenance, reducing the burden on IT staff. And these are not just the one, the list will be long using cloud, and I have created a separate list of cloud computing. Please check that if you need more details. Let's see the use cases. Different use cases, and this is very tiny distributed web hosting websites and application in cloud for improved reliability. Then we have cloud storage solution. We can use, for example, AWS S3 for storage or backup. Sometimes what people organization do, they use the private cloud, but for backup they use public cloud. So that is also doable. Application development, leveraging platform as a service for rapid development, testing and deployment of application. Then big data analytics, analyzing large data sets using cloud-based tools and services that provide the necessary computing power. So this is just a small tiny list of the benefits, but there are many benefits of using cloud services. Service mesh architecture. Service mesh architecture is an infrastructure layer that facilitates communication between microservices in a distributed application. It manages service to service interaction, providing capabilities such as traffic management, security, observability, and reliability without requiring changes to the application code. Let's see the example. E-commerce application. An e-commerce platform using microservices for product management, order processing, user authentication, and payment. So we are using microservices. Let's understand this example with key components of service mesh architecture. Microservices. So first we have so many microservices. One is for product services, one is for order service, one is for user service, and one is for payment service. Now we have service mesh. Tools like, for example, AWS App Mesh, etc. What it will do, it will manage communication between these services, and that is why it says it is called as service mesh architecture. Oh, the tongue actually twists when we say service mesh. Okay, let's see the key characteristics of this architecture. So decoupled communication. Service mesh decouples the communication between services from the application logic, allowing developers to focus on business functionality without worrying about network concerns. First thing is, whatever functionalities we have or benefits we have of microservices, those will also be inherited. Each service instance is accompanied by a sidecar proxy which intercepts all incoming and outgoing traffic, enabling features like load balancing, monitoring, and security. And service meshes provide fine-grained control over traffic routing, allowing for features like canary releases, blue-green deployment, and A/B testing. We will learn about these type. What is canary release, or what is blue-green deployment. But let me give you a quick summary. So basically there are different environments for the deployment, and traffic is going to one of the environment, and we can just reroute the traffic to one to another environment once the deployment is complete on one environment, right? So that is like a traffic management. Then service discovery. The architecture facilitates dynamic discovery of services, allowing applications to locate and communicate with the correct service instance at runtime. Service meshes often include features such as mutual TLS or MTLS for secure communication between services, authentication and authorization policies. Enhanced visibility into service interaction is provided through metrics, logging and tracing, helping to monitor performance and troubleshoot issues. Let's see the benefit of this architecture. Enhanced resilience, automatic retries, circuit breaking and failover mechanisms improve the reliability of service interactions. Simplified security management. Centralized security policies and MTLS reduce the complexity of securing services communication. Comprehensive monitoring and tracing capabilities provide insights into service performance and help diagnose issues. And operational consistency, developers can manage communication and security uniformly across all services, reducing operational overhead. Let's see the use case of this architecture. First one is microservices communication. Ideal for application built using microservices architecture where multiple services need to interact seamlessly. Multi-cloud and hybrid deployments. Supports consistent service management across different environments, making it easier to implement hybrid or multi-cloud strategies. Complex distributed system, beneficial in scenarios where service interactions are complex, requiring advanced traffic management and observability feature. So all in all, this architecture is particularly valuable in modern cloud native applications, providing a robust framework for managing services interactions while ensuring reliability, security and other aspects of microservices. So this is kind of like I said earlier, also using the features of microservices architecture. Microkernel architecture. Microkernel architecture is a software design pattern that emphasizes minimalism by separating the core functionality of system from additional services and features. In this architecture, the microkernel provides the essential services needed for the system to function, while additional components and services operate independently as plugins or modules. Let's see the key characteristics of this architecture. Core functionality. The microkernel includes only the most fundamental feature necessary for the system, such as communication, resource management, and basic scheduling. Additional functionalities are provided by separate modules that can be added or removed without altering the core system, allowing for flexibility and customization. So we have core functionality and we have extension. So core functionalities without which the system won't work. Extensions are which can be added to add more functionalities to it. So that is why it is flexible in nature. Inter-process communication. The architecture often relies on inter-process communication or IPC mechanism to facilitate communication between the microkernel and its plugins or modules. Right? The microkernel and its plugins or modules. Modules are isolated from each other, which enhances stability and security. A failure in one module does not necessarily affect the other. And it is kind of similar aspect of microservices architecture also. There it is just a service. Here it can be a module. Now within module we can have services as well. Modules can be loaded and unloaded at runtime, enabling dynamic updates and resource management. Let's see the benefits of this type of architecture. Modularity. The separation of core and additional features promote a modular design, making it easier to manage and maintain. And if you guys are familiar with content management system, let's say for example Adobe Experience Manager, which uses OSGI framework where we can deploy different bundles. Those bundles are different functionalities, different services and independent of each other, right? They can be uninstalled, installed, can be activated or deactivated at runtime. So that is also a modular application. So somehow that CMS, Adobe Experience Manager, is also using this architecture, microkernel architecture. Scalability. New features can be added as independent modules, allowing the system to grow without significant rework. Flexibility, users can customize the system by adding or removing modules according to their needs. So for example, I'll create a new jar file, I'll add new functionalities to it, I'll just deploy this, and this jar file can be plugged and played. Means if you deploy this jar file to another system, it will work. So that way it is flexible in nature, it is reusable, and it is scalable. Enhanced reliability. Isolation of components increase the overall reliability of the system, as issues in one module are less likely to impact the others. Now let's see the use cases of this type of architecture. Okay, operating systems. Microkernel architecture is often used in operating systems where the core functions are kept minimal, and additional services like file system, device drivers are run in user space. Then embedded systems, suitable for embedded systems requiring high reliability and real-time performance, where flexibility and modularity are essential. Plugin based application, ideal for applications that benefit from an extensible architecture such as web browsers or IDE, where users can add plugin for enhanced functionality. So this architecture is particularly beneficial for systems that demand high modularity, flexibility, reliability, allowing for a clean separation between core functionalities and additional features while enabling dynamic updates. Self-contained systems. Self-contained systems, or SCS, is an architectural style that emphasizes building applications as independently deployable units, each encapsulating all the necessary components to operate independently. This architecture promotes the creation of small cohesive systems that can be developed, deployed, and scaled independently. And with the name also we can understand self-contained system, a system which itself is complete, contains everything. So that way we can just correlate it. Now let's see the key characteristics of this type of architectural style. Independence. Each self-contained system operates independently with its own database, user interface, and business logic, reducing dependencies on other systems. That is one, the prime one. Autonomy. SCS are designed to be autonomous, meaning they can be deployed and run without relying on shared resources or services. Cohesion. Each system is focused on a specific business capability, promoting high cohesive and clarity of purpose. Interoperability. Self-contained systems communicate with each other via well-defined APIs, allowing for interactions while maintaining independence. And scalability. Since SCS are independent, they can be scaled individually based on demand without affecting other systems. Now let's see the benefits of this type of architecture. Modularity enhances modular design, making it easier to manage, update, and maintain each system independently, right? That is one of the advantage. Reduced complexity. So of course, because we are seeing that we will have modular bundles or functional components, right? So if there is any change required within one module, we can just change it and then it will not impact the other one because it is loosely coupled and highly cohesive within module, right? So reduced complexity. It simplifies the overall architecture by minimizing dependencies, making it easier to understand and modify. Faster development. Of course, for different modules, we can have different teams. They can just concentrate on their requirement, their business logic, etc. So in this way, teams can work on different systems concurrently, speeding up the overall development process. Improved resilience. Failure in one system, one module has failed, consider, okay, does not directly impact others because though they are loosely coupled, they are not dependent on each other, enhancing overall system reliability. Let's see the use case of this type of architecture. Microservices architecture. SCS is often employed in microservices environment where each microservices can be viewed as a self-contained system. So when we are saying microservices architecture, this is actually this architecture only, self-contained, because each microservice is self-contained system. Then large scale application. suitable for large applications that can be decomposed into distinct independently deployable units. And then we have legacy system replacement, helpful in gradually replacing monolithic legacy systems by breaking them down into self-contained components. So consider, I mean, we have a legacy monolithic application, I mean, which were using the monolithic architecture. It means we had several functions, right? But they are tightly coupled with each other. Now what we can do, we can break down them, create small microservices, and this way we are creating those microservices nothing but the self-contained systems, right? So this way we can use this architecture to upgrade that system from legacy monolithic architecture to microservices based architecture. So this architecture is particularly effective in environments that prioritize modularity, scalability, independence, allowing organizations to respond quickly to changing requirements and maintain robust, resilient applications. Multi-tenant architecture. Multi-tenant architecture is a software architecture pattern that allows a single instance of an application to serve multiple customers. Customers are tenants. Each tenant's data and configuration are isolated while sharing the same application resources and infrastructure, enabling efficient resource utilization. Let's see the key characteristics of this architecture. Single application instance. A single instance of the application serves all tenants, reducing maintenance and operational costs. Data isolation. Tenant data is logically isolated, ensuring that one tenant cannot access another tenant's data, which is crucial for security and privacy. Of course, I mean, consider all data is at one place and then someone is requesting the PIA information and we are sending someone else PIA information. So data isolation is required. Shared resources. Resources such as servers, databases and storage are shared among tenants, optimizing resources utilization and reducing costs. And can you guess one example? These cloud providers, right? For example, AWS, etc. They are built on multi-tenant architecture, right? They have shared resources. In the data center, we have that database, those hardwares, those servers are shared. The services are exposed from the same hardware, same resources, right? So that is also one of the example. Customizability. Tenants can often configure certain aspects of the application, for example, user interface setting according to their specific needs while using the same underlying code base. Scalability. The architecture supports easy scaling as new tenants can be onboarded without needing to deploy new instances of the application. See, the same thing, right? I can create a new AWS account right away. You can also create a new AWS account right away, and then you can create an EC2 instance on top of that. You can run a new VM, create new services, right? So AWS is not going to install a new server so that a new user can create an account, right? On the same shared resources only. It is scalable in nature, that if new tenants are coming, they are onboarded without needing to deploy a new instance. See the benefits of this type of architecture. Cost efficiency, of course, reduces infrastructure and operational costs by sharing resources among multiple tenants. Simplified maintenance. A single application instance is easier to maintain as updates and patches can be applied centrally. Faster onboarding. New tenants can be onboarded quickly, often through automated process. Improved resource utilization maximizes the use of available resources, allowing for a more efficient and sustainable operation. Let's see the use case of this architecture. Software as a service. Commonly used in software as a service applications where multiple organizations use the same software while maintaining data privacy and security. For example, Salesforce, Microsoft 365, Gmail, Rediff Mail. I'm not sure if people still use Rediff Mail, but yeah. Okay, cloud platforms. Cloud service providers often use multi-tenant architecture to deliver services to multiple customers efficiently. That is what I just told earlier. Then collaborative applications, applications that require shared access and collaboration among multiple users, such as project management tools or content management systems. There also it is a good use case of using this type of architecture. Reactive architecture. Reactive architecture is an architectural style that focuses on building systems that are responsive, resilient, elastic, and message driven. It emphasizes the ability to respond to changes in the environment and user demands in real time, enabling applications to handle varying workloads and conditions efficiently. Let's see the key characteristics of this type of architecture. Responsive. The system provides timely response, and that is why it is reactive. I mean, it is reacting, right? The system provides timely responses to user inputs and system events, ensuring a seamless user experience even under varying load. Then resilient, designed to withstand failure gracefully. Reactive systems can recover from errors and maintain functionality, often through techniques like replication and circuit breaker. Replication means, for example, I have some data, maybe I am using some database, and I have replicated this data to another region, another availability zone. So something happens to this region, this data center, data is already replicated to another server, so data is still available, right? Elastic. The architecture can scale up or down in response to demand, automatically adjusting resources to handle changes in workload without degrading performance. Message driven. Components communicate asynchronously through messages, decoupling producers and consumers, which enhances system flexibility and responsiveness. And event driven. Systems react to events and change in state, enabling a more dynamic interaction model that can adapt to real-time conditions. Let's see the benefits of this architecture. First is, of course, improved user experience. Fast and reliable responses enhance the overall user experience, especially for applications with high interactivity. Scalable solution. Elasticity allows systems to efficiently handle fluctuating loads, ensuring consistent performance during peak and off-peak time, and the system will be fault tolerant. Resilience ensures that the system continues to function despite failures, increasing overall reliability. And decoupling of components means message driven communication fosters loose coupling between system components, facilitating easier maintenance and updates. Let's see the use case of this architecture. Web application, ideal for applications that require high interactivity and responsiveness, such as social media platform and online gaming, right? Any post is submitted and then it should be available on all the nodes, or different players are game in a multi-player game. The interaction should be visible. The status should be updated on real time. IoT systems, useful in IoT applications where device generate and responds to events in real time. Streaming services, effective for platforms that need to process and deliver continuous streams of data like video streaming, real-time analytics, etc. So this architecture is well suited for modern applications that demand agility, scalability, and resilience, particularly in environments where user interactions and system loads can change dynamically. This architecture empowers developers to create systems that not only respond to user needs but also adapt to varying conditions effectively. Hybrid cloud architecture. Hybrid cloud architecture is a cloud computing model that combines public and private cloud resources, allowing organizations to leverage the advantages of both environments. This architecture enables data and applications to be shared between them, providing flexibility, scalability, and enhanced security. So we already know that the cloud can be of private, public, multi-cloud, etc. Right? Hybrid cloud is a combination of public and private cloud resources. Let's see the key characteristics of this architecture. combination of cloud types, integration of both public cloud services provided by third-party vendors, for example AWS, GCP, Azure, etc., and private cloud infrastructure dedicated to a single organization. Data portability facilitates the movement of data and applications between public and private cloud. It allows organizations to optimize their resources based on specific needs. So usually what organizations do, if they have sensitive information, they will put it in private cloud, but wherever they can utilize the public offering, they will utilize it using public cloud. Often includes tools and platforms that provide a cohesive management experience across both cloud environments, simplifying operations. Scalable solution. It offers the ability to scale resources up or down based on demand, utilizing public cloud resources during peak time while keeping sensitive data in the private cloud. Security and compliance related aspects. Organizations can store sensitive data in the private cloud, so it is more secure. Private cloud is always more secure, while taking advantage of the scalability of the public cloud for less critical applications. Now let's see the benefits of this architecture. First one is of course flexibility. Organization can choose where to host applications based on performance, security and compliance requirements. It is cost efficient because it reduces cost by utilizing public cloud resources for non-sensitive operations while maintaining private cloud resources for critical data only. Business continuity enhances disaster recovery options by allowing data replication and backup across multiple environments. So for example, AWS has this multiple AZ or multiple region replication capabilities. So same data will be replicated to multiple availability zones or multiple regions, so that in case if there is any disaster in one of the data center, we still have the data backup somewhere else. Optimized performance. Workloads can be distributed across public and private cloud to optimize performances and resource utilization. Let's see the use cases. One of the use cases is data backup and disaster recovery. Organizations can back up data to a public cloud while keeping primary operations in a private cloud, ensuring business continuity. So for example, AWS S3 can be used as one of the backup storage. Development and testing. Developers can use public cloud resources for development and testing while maintainability production systems in a private cloud. Regulatory compliance. Businesses in regulated industries can keep sensitive data in a private cloud while utilizing the public cloud for less sensitive applications. Client-server architecture. Client-server architecture is a computing model where tasks are distributed between service providers known as servers and service requesters known as clients. This architecture is commonly used in networked environment, allowing clients to access resources and services provided by the servers. And to be true, if you see any web application wherever we are accessing the application through client, for example Chrome, right? This is client server architecture only, because in that case client will be the Chrome, that, and then whatever requests are coming to the server is responding with the proper response. So this is also one example of client and server architecture. Benefits of client server architecture. Centralized control simplifies administration and maintenance as resources are managed from a central location. Scalable solution, easy to scale both horizontally, and we can add more servers to it, and vertically we can upgrade the existing server. We can increase the RAM, increase the CPU, etc. to accommodate growing user demands. Efficient resources. Enable efficient use of resources by allowing multiple clients to share server capabilities. And enhanced security. Servers can implement robust security measure, ensuring that sensitive data is protected. Let's see the use cases. Like I said, any web application. Most web applications operate on a client server model their web browsers acts as client and web servers deliver content. Simple example, database systems. In database applications, clients send queries to database servers. For example, SQL based queries, we have get query, fetch query, update query, all those queries, right? Which process the request and return results. Email services, email clients connect to email servers to send and receive messages, right? So example, Outlook is one of the email client. Okay, this architecture is foundational to modern computing, providing a structured approach for building scalable, maintainable and efficient system that support a wide range of application across various industries. Because before this client server architecture, it means everything including the user experience as well as the business logic, the calculation, etc. used to happen on the same system, right? And then this cloud computing concept came into picture. That's why we need this client server architecture, that even if it is a distributed system, we need this calculation, the business calculation, the whatever calculation is happening, which is happening through server, we want to distribute it, we want to segregate it from the client. And that is why it is this concept came, this architecture came, client server architecture. Distributed architecture. Distributed architecture is a software design pattern in which components of an application are located on different network computers, enabling them to work together as a single cohesive system. This architecture allows for resource sharing, scalability, and improved fault tolerance across various locations. Like it says distributed, it means the systems, the networking computers, they are distributed. Let's see the key characteristics of this architecture. First one is of course decentralization. Unlike centralized architecture, distributed systems do not rely on a single point of control. Distributing tasks and data across multiple nodes. Multiple nodes means multiple computers, multiple servers. Interconnected components. Components here are basically servers, clients, databases. Communicates over a network using standard protocol, allowing for seamless interaction. These protocols could be, for example, HTTP protocol, REST-based APIs, etc. Scalability. The architecture can be scaled horizontally by adding more nodes to the system. So we can add more server, more clients, more databases to the system, accommodating increasing loads without a significant reconfiguration. Fault tolerance. If one component fails, another can continue to operate, enhancing the system's reliability and availability. Yes. And resource sharing enables sharing of resources. Those resources could be computational resources, power, storage, etc. across different nodes, optimizing overall system performance. Client server architecture benefits. Let's see the benefits. Enhanced performance. By distributing workload, applications can achieve higher throughput and reduced latency. Of course, because the workload or tasks are distributed, so there will be less. There will be latency will be lesser. Flexibility. Components can be developed and deployed independently, allowing for more agile development practices. Improved resilience. The failure of a single component does not lead to system-wide outages, improving overall uptime. Cost efficiency. Utilizes existing infrastructure and resources, potentially lowering operational costs. What does that mean? This means, for example, right now we have client server architecture. In this architecture, we want to add more nodes, means more computational power or servers, clients, etc. Configurations are still same. All we need to do is just add that. Configuration and infrastructure is same. All we just need to do is just add that new server. That's it. Let's see the use case of this architecture. Cloud computing. Many cloud services utilize distributed architecture to provide scalable and flexible solutions. Almost everywhere not in cloud computing, but everywhere we use the distributed architecture nowadays. Microservices. In microservices architecture, individual services are deployed as independent components that communicate over a network. That is also one example of distributed architecture, because those microservices works in silos. They are not relying on each other, totally loosely coupled, cohesive in nature within those modules. They are cohesive in nature. Content delivery network, CDNs use distributed architecture to cache content across multiple locations, improving access speed for users. Now this architecture is crucial for modern applications that require scalability, resilience and efficiency. By leveraging multiple interconnected components, organizations can create robust systems capable of handling diverse workloads and dynamic user demands. Reactive microservices architecture. Reactive microservices architecture combine the principle of reactive system. So we have reactive architecture and we have microservices architecture, right? Some events are happening, so we need instant reaction. That was the whole reactive architecture, right? Microservices architecture was small modules, independent in nature, not relying on other modules, and loosely coupled with other modules and highly cohesive within itself. Those are the microservices architecture pattern. Now we are combining these two patterns. So what it will do, reactive microservices architecture combines the principle of reactive system with microservices architecture to create applications that are responsive, resilient, elastic and message driven. This approach enables organizations to build systems that can efficiently handle variable loads and user demands in real time. Let's see the key characteristics of this architecture. So it's reactive microservices. So of course it's microservices based. Applications are composed of small independent services, each focused on a specific business capability, allowing for modularity and easier management. Then asynchronous communication. Services communicate through asynchronous message passing, promoting loose coupling and enabling system to react to events without blocking. The message driven approach is being used. Event driven. The architecture is designed to respond to events, allowing services to react to changes in state or incoming data streams in real time. Resilience. Each microservice is built to handle failures gracefully, often employing patterns like circuit breaker and retries to maintain functionality. So for example, if we are using this message driven or event driven approach, let's take the example of SQS. AWS provides this SQS feature where you can create an event, put it in SQS, which is simple queue service, and then this event will be taken by the subscriber, right? So because of some technical issue, if this event failed, the subscriber could not pick this event, there are retries we can configure. So for example, 3-time retries can be, because otherwise that event might be lost, right? So those options are there. Elastic scalability. Services can automatically scale in response to demand, ensuring optimal performance under varying loads. Let's see the benefits of this architecture. Enhanced responsiveness. The architecture provides quick responses to user interactions, improving user experiences, especially for applications requiring real-time processing. Improved fault tolerance. Services can continue operating even if some components fails, enhancing overall system reliability, because we are talking about microservices architecture. Those are independent in nature. So of course, if one service fails and others are still independent in nature, so they will work. Independent deployment. Microservices can be developed, deployed and scaled independently, facilitating agile development practices and continue delivery. Resource optimization. By scaling only the necessary services, resource utilization is improved, reducing the operational cost. Let's see the use case of this architecture. Real-time data processing, because of course it's reactive, right? Reactive means real-time use cases are always applicable for this. Real-time data processing, ideal for applications that require immediate response such as financial trading system, online gaming, IoT applications effective in IoT scenarios where devices generate and response to events continuously, and streaming services, of course. So all the use cases whatever we had for the reactive one are also applicable for this architecture. So this architecture is particularly beneficial for modern applications that demand agility, responsiveness, resilience, and by leveraging the strengths of both reactive system and microservices, organizations can build robust solutions that adapt to changing conditions and user requirements effectively. Backend for frontend, BFF. Backend for frontend is a software architectural pattern that involves creating a dedicated backend service tailored to the specific needs of a front-end application. This approach allows for optimizing communication between the front-end and back-end, enhancing performance and usability. Let's see the key characteristics of this architecture. Dedicated backend services. Each front-end application, for example, we have web application, we have mobile application. Each front-end application has its own backend service. So it means there is a different service for which will provide data for web, and there is a different service which will provide data for mobile application, which can be optimized for its particular requirements and workflow. API gateway functionality. The BFF acts as an intermediary between the front-end and various backend services, aggregating data and responses to simplify front-end development. Custom data handling. The BFF can transform, filter, or aggregate data from multiple sources, delivering only the necessary information to front-end, thereby improving efficiency. So for example, when we have different backend service for different channels, for example web and mobile, we know that for web application we need data which can be still huge, but on mobile application we need data which is lesser in size, because we need more performance. On mobile application we need less data in terms of lesser in size, so that there will be less latency, right? Front-end specific logic. It allows the implementation of business logic and functionality that is specific to a particular front-end application without affecting other services, right? So for example, there is a service which will build UI on homepage, right? So that service will be different for web application and different for mobile application. Versioning and evolution. The BFF can evolve independently of the backend services, allowing teams to implement changes and improvements tailored to the front-end's need. Now let's understand with one example. Let's take the example of e-commerce platform, and this platform is having web application as well as mobile application. Now understand, we have two clients. We have web application, which is first one client, and mobile application, which is second client. So since we have two clients, it means we need two services, because that is what it says, backend for front end. How many type of front end we have? Same number of backend we should have, backend services. So we will have one BFF for web and one BFF for mobile. And consider we have these microservices: user service, product service, order service, payment service. It means we will have two flavors of each of them. Now the flow would be, client request will go either from web app or mobile app. So web app requests product data from web BFF, or mobile app requests the same data from mobile BFF. Now on BFF layer what will happen? There are two BFF. One is web BFF and one is mobile BFF. Web BFF will aggregate and format data for the web, whereas mobile BFF optimizes data for mobile devices, because sometimes we need like lesser data on mobile device. We don't need those fancy items which we show over desktop application. Microservices interaction. BFFs, both BFFs Fetch data from relevant microservices. Simple. Response BFF send tailored response back to the client. So sometimes we might have different microservices, or sometimes we use the same microservices. It's just we fetch the data from microservice and we manipulate that data according to what we would want to send to different type of clients. Now let's see the benefit of this type of architecture. Optimize performance by providing tailored data and reducing the number of API calls needed by the front end. The BFF can enhance overall application performance. Front-end developers can work more efficiently as they interact with the dedicated service designed specifically for their application. So kind of one-to-one mapping. Reduced complexity simplifies the front-end code by abstracting complex interactions with multiple backend services, leading to cleaner and more maintainable code. And of course, independent deployment, because the BFF can be deployed independently, allowing teams to iterate faster without impacting the entire backend. Let's understand what is design pattern in software engineering. So there are 20 plus design patterns, and there are emerging modern design patterns also. Let's understand one by one each of them. Design patterns are standardized solutions to common software problems. They provide a template for how to solve specific issues in software architecture and design, promoting best practices and enhancing code readability and maintainability. So these are the keys. It's just to enhance the code readability and maintainability. Even if you have not read the design pattern so far, you must already be using them unknowingly, right? So these standards are just to make optimized code to help developers how they can write different type of classes. It's kind of low level template for writing the code. So there are three types of design patterns: creational design pattern, structural design pattern, and behavioral design pattern. Let's first understand what is creational pattern. Creational patterns are a category of design patterns in software development that deal with object creation mechanisms. That's why it's creational. They aim to create objects in a way that is suitable for the situation while providing flexibility and reuse. The main goal is to abstract the instantiation process, making it easier to create objects without specifying the exact class of the object being created. So within creational design pattern, we have these flavors: singleton pattern, factory method pattern, then abstract factory, builder, and then prototype. Let's first understand what is singleton pattern. The singleton pattern ensures that a class has only one instance throughout the application and provides a global access point to that instance. This is useful when exactly one object is needed to coordinate actions across the system, like managing a configuration setting or a connection pool. Now let's understand this with this Java code example. What we have is a class, singleton class, right? And then we have this method, which is singleton get instance, which is constructor of this class, right? The type of this same class type. And this is static method, right? Now what is happening here? We also have a private constructor here. This private constructor will prevent instantiation from outside the class, right? And static method, get instance method, it will provide a way to access this, and then only a single instance will be created of singleton type, because what we are doing here is checking if the instance is null, then only create it, otherwise just return it. So there will be only one instance be created of this class, and if it is not created, then only, otherwise it will not be created again. So, and that is the definition of this. Let's read it again. Singleton pattern ensures that a class has only one instance throughout the application and provides a global access point to that instance only. Let's see the benefit of this type of pattern. So first thing is controlled access to a single instance. It ensures that a class has only one instance, providing a global point of access. This is useful for resources that should be shared, like configuration setting or connection pools. So for example, we create a database connection pool, and of course we want to use the same connection pool resource. So we do not want to create the database resource connection pool again and again. So that is a good example. The singleton can be instantiated only when it is needed, which can save resources if the instance is not always required, right? That is another use case. Since only one instance is created, it can help reduce memory usage. By providing a single point of access, the pattern can simplify client code that needs to interact with the instance, avoiding the need to pass references around. And when implemented correctly, the singleton pattern can be made thread safe, ensuring that multiple threads can access the instance without causing inconsistencies. Because there will be only one instance created, and consider there are multiple threads they want to access this instance, so there will be no issue related to that. If the resource is updated every time, only at a time only one object will be able to update the thread, and all other instances will get the same value of that resource. So that is way it will this add this benefit also, that it will be a thread safe. Let's see few example. One is logging service. So in almost in any application we will use logging feature, right? We want to log in logs that what are the features have been executed, so that we can debug later on, or for some auditing purpose also. So in many applications, especially large ones, we need a centralized way to log messages like error logs, warning logs, information message, etc. Having multiple instances of logging service can lead to inconsistent log entries or resource conflicts. So there it is a good example. We can create the logging instance at one centralized place, and then we can use the same instance. Factory method pattern. The factory method pattern defines an interface for creating an object, but allows subclasses to alter the type of object that will be created. It promotes loose coupling by eliminating the need for the client to know the specifics of the class being instantiated. Let's see this example. So first thing is, we have an interface animal, and there we have a speak method. What the definition says: the factory method pattern defines an interface for creating an object. So that is the interface. Animal interface defines a common interface for all animals with a speak method, right? And then we have concrete animal classes, dog and cat. What it does, just implement this interface and override the speak method and put more specific implementation of the speak method. Then we have factory class, this abstract factory class. What it does, this just declares the create animal method for concrete factories. So this will just exposes a method which is create animal. Now we will have more concrete factory classes, for example dog factory class, cat factory class, and of course it will override this method create animal. And what we are doing, we are just returning the dog, this type of concrete instance, like for example here we are returning dog and here we are returning cat. So what we have achieved is, it defines an interface creating an object, yes, and allows subclasses to alter the type of objects that will be created. So we have just used these classes, subclasses, to alter the type of the subclasses. To alter the type means we have altered it to dog, and we have altered this factory to return type of cat. Now for example, if you want to add another factory where we just dog and cat, instead of that we want to add any other animals factory, all we have to do is we have to add one more class, extend the animal factory, and override this method and return the object. Return the object would be any class which is going to implement the animal interface. Abstract factory pattern. What is the difference between this factory pattern and now we have this abstract factory pattern? The abstract factory pattern provides an interface for creating families of related or dependent objects. So in the factory pattern, we had what we learned, it provides an interface to create the object, but in this one we are creating families of related or dependent objects. That is the main difference with it, without specifying their concrete classes. This pattern is useful when you need to create multiple related objects that are designed to work together. Now let's understand this pattern with this example, and let's simplify it. Earlier in the factory pattern we had one interface. Consider here also we have this interface N1. Same. Now we are saying the difference between factory pattern and abstract factory pattern is abstract factory pattern is more concerned on creation of families of related dependent object families. So somehow we want to create more objects that are closely related to each other. Now in this example, that's why we have taken another interface which is habitat. So in animal interface, this is for speaking of how animals speak, and habitat, they describe the animal type, right? Now it can be considered as a family of similar type of object, habitat and animal. Okay, now what we have done, we have implemented this interface in the using the class dog. Simple, we have just overridden this method. So far we are good, and we have also written another class which is domestic habitat, and we have implemented this method describe. Let's ignore this, don't see this class at all. So far we are good. We have created one interface animal, another interface habitat, and we have just created subclasses to override the methods inside these interfaces. We are good. Now what we have a abstract factory of animal, abstract animal factory. What it is, it has two methods. First it is creating the animal, and then it is creating habitat of the animal, right? Now consider we have a class, right, which will implement this factory, and maybe it's domestic animal factory. It will override this method create animal, and it will override this method create habitat, and will just return the dog, and will just return the domestic habitat, right? So what we have done, we have created a factory of domestic type of habitat, and in that one we have created two objects of same type. Now consider we want to create another class of wide habitat factory. Okay, we want to create another factory of wide habitat factory. What we need to do, we will just write another class wide habitat factory extends abstract animal factory, right? And here inside create animal we can just maybe return dog is also sometimes considered wide, or maybe we can create another class wolf, right? And then in create habitat we will just override this one, which is describing this is a wide habitat. That's it. Let's see the benefits of this type of pattern. It creates families of related object, ensuring compatibility. It greater decoupling from concrete classes, making it easier to switch product families, and new families can be added without modifying the existing code. And it guarantees consistency across product created by the same factory. Basically, whenever we implement any of the design pattern, right, it is just because first thing is we want to have more abstraction, so that implementation, wherever we have the implementation or we are providing it as an interface, right, we want to just hide the implementation, just to have as an abstract method. Also the readability of the code, and it should look nice and clean. Let's see this pattern, which is builder pattern. The builder pattern separates the construction of a complex object from its representation, allowing the same construction process to create different representations. The builder design pattern consists of several key components that work together to facilitate the step-by-step construction of complex objects. So let's see those components first. Okay, first component is product. This is the complex object that is being built, and the definition says The builder pattern separates the construction of a complex object from its representation. So this is the complex object we have, that is product. Example is, for example, in a house building scenario, the house class represents the product. Okay, that is the product. Then we have builder interface. This defines the methods required to build different parts of the product. For example, an interface like house builder that specify methods for building walls, roofs and windows. Then we have concrete builders. These are specific implementation of the builder interface. Each concrete builder knows how to create a specific version of the product. And for example, class like wooden house builder, brick house builder, that implement the house builder interface and provide the logic for building wooden and brick houses. So the complex object was house, and then we are breaking into by step we are breaking into more concrete classes. And for example, this one, right, wooden house builder, brick house builder. So for example, product, which in the example is like the whole house, right? This is the product, and we have several methods, right? And builder interface is like, for example, house builder, right, where we have build walls, build roofs, build windows, all these methods available. Then we have director. This class is responsible for managing the building process. It uses a builder instance to construct the product in a specific order. For example, the house director class, which directs how to build a house by calling the methods of the builder. And then we have client. The client is the code that uses the director and builders to create the product. It interacts with the director to construct the object. And for example, the main program, right, from where you are invoking, from that creates instance of builders and the director orchestrating the construction process. So for example, this one, we had this house builder. Now this class is implementing the house builder, right? And this one is wooden house builder, which is implementing house builder. This one is brick house builder, which is also implementing house builder. And what they have inside, the house is same, everything is same. It's just the implementation is different. Here they are setting the walls as wooden. It's in the brick house, it is by brick, right? The implementation is different in these concrete classes. And then we have the director, house director. What it is doing is, it is finally taking the builder object and then building the using those methods. For example, building walls, building roofs, building windows. And this is the client class where we are using the director. We are making the object of builder. We are making the object of director, right? And whatever we want to use, right? So for example, using the director, and we have created an object of wooden builder, wooden house builder. We are using the wooden house builder, and then director, using director's object, we are constructing the house. If you want to create a brick house, then again we are using the subclass brick house builder, creating that object, and then using the director method we are creating the house again. Next is prototype pattern. The prototype pattern allows creating new objects by copying an existing object, which is a prototype, rather than creating new instance from scratch. I think it is simple and straightforward explanation. Let's see the key components of this pattern. So first thing is we have cloning method. The prototype interface typically includes a method like clone, right, through which that object can be cloned, which is responsible for creating and returning a new instance of the object that calls it. And of course, it enables quick duplication of objects, allowing new instance to be created without knowing their class, which is crucial for class hierarchies. Flexibility. By using the prototype interface, client code can work with various concrete prototypes without being tightly coupled to their implementations, and it allows new prototype types to be added without modifying existing code, enhancing scalability and adhering to the open closed principle that we have learned earlier. What is open closed principle? Instead of relying on a complex constructor or factory methods for object creation that we have seen earlier, The prototype pattern enables the generation of new instance through cloning. It simplifies object creation, especially for complex objects, avoiding repetitive code and promoting clearer and more maintainable structure. The prototype interface allows variation of an object to be created easily by cloning existing instances and modifying them as needed. And this is a very straightforward, simple example. It's written in Java. Here we have this class, right? And this prototype class has a clone method that creates a new instance of itself with the same value. You see this is the constructor. It has a clone method and it returns just the object. And the clone method allows you to create a duplicate of the original object. Next design pattern is structural design patterns. Structural design patterns focus on how classes and objects are composed to form larger structures. They help ensure that if one part of a system changes, the entire system doesn't need to change. Basically, the concept of modularity or microservices. And these are the patterns we have: adapter, bridge pattern, composite, decorator, facet, flyweight, proxy. Let's first understand adapter pattern. Let's understand this with one example. Adapter. We only use the charger of mobile. So we are getting 220 voltage, right? And we want to convert it to for the mobile. So we use adapter. Sometimes we say also, for example, for laptop we need adapter charger. For mobile also we need adapter charger, right? Similar to that. The adapter pattern is a structural design pattern that allows incompatible interfaces. So for example, we were getting 220 voltage from the source, but whereas we just need maybe 12 volt, right, for our mobile or for our any electronic device. So we are converting it, we are adapting it. So this pattern is a structural design pattern that allows incompatible interfaces to work together. It acts as a bridge between two interfaces, enabling communication between them without modifying their existing code. Let's see the components of this pattern. So we have a target interface. This is the interface that the client expects to work with. It defines the methods that the client will call. For example, an interface called target with a method request. Adapter. This class implements the target interface and translates the request from the client into calls to the adaptee. It acts as a wrapper around the adaptee. A class called adapter that implements the target interface and holds a reference to an adaptee instance. Then we have adaptee. This is an existing class with a different interface that needs to be adapted to the target interface. It contains the logic that the client wants to use. For example, a class called adaptee with a method specific request that the client cannot call directly. And finally, the code that interacts with the target interface using it to perform operations. So for example, a class or method that creates an instance of the target interface and calls its methods. This is very simple and straightforward explanation. What we have here we have a target interface, and this target interface is having a request method, and we have adaptee, right, which is having specific request. Now what we want is an adapter. This adapter class, what it will do? It will translate request from the target interface to the adaptee. And how it is being done? See this, what it is doing, adapter class, it is implementing the target interface, right? It means it needs to implement this request method. So within this implementation, the request method implementation, it is just returning the adaptee dot this method, right? So this is one of the example of adapter. Now we have bridge pattern. The bridge pattern is a structural design pattern that separates an abstraction from its implementation, allowing both to evolve independently. It provides a way to decouple an interface from its implementation so that you can change one without affecting the other. Let's see the components of this pattern. Abstraction component. This is the main interface that defines the high level operations. It holds a reference to the implementation interface. An abstract class called shape that contains, we will see that, how it is going to be implemented with an example. Then we have refined abstraction. This extends the abstraction and provides additional functionality or specific implementation. Then we have implementer class, the interface that defines the implementation method. It doesn't need to be tied to the abstraction. And then we have concrete class, concrete classes that implement the implementer interface, providing specific behaviors. Let's understand this with this example. Okay, so what we have is, we have one interface color. This interface defines the implementation that can be changed independently of the abstraction, and this has this method called fill, right? Then we have concrete implementation color classes, color interfaces. We have class red, we have class green. Simple. So far we are good. We have an interface, we have two concrete classes. Now we have another abstract class, right? This is for color, this is for shape, and what it is doing, it uses the color implementation. So what I have done here, I have just a color object, right? And inside this constructor of shape, I am using the color object, right? And I have another abstract method. Now what I can do, I can create specific shapes. So for example, I have created circle, I have created square, right? And I have extended this class. So it means I can implement this method, draw method, and which is specific to circle or to square. And then for this circle object, right, this constructor will be as is, like I will just use the extended one, which is shape, right? And I can create as many shapes I want with the different colors, right? So this is the example which describes this pattern. Next pattern type is composite pattern. The composite pattern is a structural design pattern that allows you to compose objects into tree-like structures to represent part-whole hierarchies. This pattern treats individual objects and compositions of objects uniformly, making it easier to work with complex structures. Let's see the key components of this pattern. We have three components: component, leaf, and composite. And component is very simple. In Java terms, it is kind of an interface or abstract class. So component is an interface or abstract class that defines the common interface for all objects in the composition, right? Leaf represents the individual object. So leaf nodes do not have children. So the least amount of object is leaf. Then composite, a class that implements the interface, okay, interface which we are calling here as component. So class which is implementing the interface and contains child component. So it is very simple. Now let's understand with this example. It looks bulky, but I will explain. It is simple. So we have this interface, file system component. Okay, interface is what? Component. Simple. Then we have file class, which is implementing this interface. According to this design pattern, if the class which is implementing the interface, what is it? Is a leaf. And then we have another class which is implementing, which is containing files and folders, right? So it is containing files and folders. So as per the description, component is an interface, understood? Leaf is the individual object, and in our case it is file, right? And composite, the implementation of the component interface. So in this case, it is both file as well as folder. They both are implementing this interface, so hence they are composite. Decorator pattern. Decorator pattern is a structural design pattern that allows behavior to be added to individual objects, either statically or dynamically, without affecting the behavior of other objects from the same class. It provides a flexible alternative to subclassing for extending functionality. So these are the components of decorator pattern. So we have a component, we have concrete component, we have decorator, and finally the concrete decorator. Component is nothing but the interface. Okay, concrete component is the class which implement the interface. So far we are good. So component is an interface or abstract class that defines the core functionality. Example is coffee is an interface which has method cost. What is the cost of that coffee? Simple. Concrete component, a class that implements the component interface that defines the base functionality. For example, simple coffee which implements coffee interface. Simple. So far we are good. Decorator. Decorator is an abstract class that implements this coffee interface and has a reference to a component object. It serves as a base or for concrete decorator. Simple. So what this decorator will do is just another abstract class which will implement this interface and has a reference to this component, okay, which is implementing the interface, right? So, to add some more functionalities to it. And finally we can have concrete decorators class, again the implementation of this abstract class. Let's understand this with this simple example, very simple example. So first I said interface component. Component is the interface which has one method. Simple. Then we have concrete component class which will implement this interface. So far we are good, right? It's just we have implemented this. Then we have a decorator class which will implement the interface, right? And then has a reference to the concrete component class, right? And to add more methods to it. So for example, here we have just added more, that this is some extra logic we have added. Next pattern is facade pattern. The facade pattern is a structural design pattern that provides a simplified interface to a complex subsystem. It acts as a facade or front-facing interface that makes it easier to interact with the underlying components without exposing the complexity of the system. This pattern is especially useful when you want to provide a higher level interface that hides the intricacies of a system, making it more user-friendly. Let's see the key components of facade pattern. First one is facade, the main class that provides a simple interface to the complex subsystem. It delegates requests to the appropriate class in the subsystem. Example is a class called home theater facade that simplifies the operation of various components in a home theater system. The next one component we have is subsystem classes. So it's a simple interface. Then we have subsystem classes. These are the classes that perform the actual work. They can be complex and may have many interdependencies. For example, classes like amplifier, DVD player, projector, that represents various components of a home theater system. And let's see this very simple and straightforward example. We have two classes, subsystem A and subsystem B. For example, we had taken this example where we have amplifier, DVD player, projector, etc. Right? Simply according to that only. Subsystem A has some operation, subsystem B has some operation. Now facade class, what it is doing? It is just simply having one operation and it is delegating these operations. For example, operation A will go to this class, operation B will go to this class. Simple illustration of how we use the facade design pattern. So what this says, the main class that provides a simple interface to the complex subsystem, it delegates requests to the appropriate classes in the system. Flyweight pattern. The flyweight pattern is a structural design pattern that aims to minimize memory usage by sharing objects. It is particularly useful when a large number of similar objects need to be created, as it allows for the reuse of existing instances rather than creating new ones. This pattern is especially effective in scenarios where the object creation overhead is significant and where many objects have shared state. Let's see the components of this pattern. So we have flyweight interface. An interface that defines the methods that can be used by the client. It usually contains method for manipulating the shared state. For example, an interface called shape with method like draw. Then we have concrete flyweight, a class that implements the flyweight interface and contains the intrinsic state, which is shared data. It may also have methods to modify the extrinsic state passed by the client. For example, a class called circle that represents a shape, which is an interface and shares common properties. Then we have flyweight factory, a factory class responsible for creating and managing flyweight objects. It ensures that flyweight instances are shared and reused when possible. For example, a factory class called shape factory that returns shared instances of circle based on specific criteria. And then we have client, that the code that interacts with flyweight object and manages their extrinsic state. For example, client code that uses the factory to create and draw shapes. Proxy pattern. The proxy pattern is a structural design pattern that provides a surrogate or placeholder for another object to control access to it. This pattern can be used for various purposes, such as lazy loading, access control, logging, implementing additional functionality without modifying the original object. Let's see the key components of this pattern. Subject, an interface or abstract class that defines the common operations that can be performed on the real object and the proxy. An example is an interface called image with a method display. Then real subject, the actual object that the proxy represents. It contains the real implementation of the operations defined in the subject interface. An example is a class called real image that implements the image interface and handles image display. Then so we have subject, which is an interface. Real subject is the class which is implementing the interface. So far we are good. Then we have proxy, a class that implements the subject interface and has a reference to the real subject. It controls access to the real object and may add additional functionality. Example is a class called proxy image that implements the image interface and manages the loading of the real image. Let's understand it with some other example. So in this example we have a subject, right? We have a subject which is an interface. We have a class real subject which is implementing this interface. And finally we have a proxy class which is implementing the interface but having a reference to the real subject, and that is how some additional logic, right, is being added. For example, access control is added right here. So this is how we can implement proxy pattern. Behavioral patterns. Behavioral design patterns focus on how objects interact and communicate with one another. These patterns are concerned with algorithms and the assignments of responsibilities between objects, promoting better communication and flexibility. And these type of behavioral patterns we have: chain of responsibility, command pattern, interpreter, iterator, mediator, memento, observer, state, strategy, template method, visitor. Chain of responsibility pattern. The chain of responsibility is a behavioral design pattern that allows an object to send a command without knowing each object will handle it. Which object will handle it? Instead of having a single handler for a request, the request is passed along a chain of potential handlers until one of them handles it. Let's see the key components of this pattern. So key components are handler interface, concrete handlers, and client. Handler interface defines a method for handling requests and a reference to the next handler in the chain. Concrete handlers implements the handler interface and defines how to process requests. Each handler can either process the request or pass it to the next handler in the chain. And the client initiates the request to the first handler in the chain. Let's understand this pattern with this example. So we have an interface. This interface is support handler and we have these methods. Now we have a concrete class which is implementing this interface, technical support. And just imagine we can have more subclasses like this which is implementing this interface. So for example, for one is for billing support, one is for general support, and one we already have which is for technical support. And here what we are doing is we are just overriding these methods, for example set next and the handle request. Now in the implementation class, what is happening here? We have just created objects of these support handlers, right? The concrete classes. And here what we are doing, we are just testing different objects, and then we are just passing these requests to different handlers. So basically the same thing, chain of responsibility. Whichever handler is applicable for that type of request will complete that, will fulfill that request. So let's understand the advantages of this type of pattern. First main advantage is of course decoupling. The sender of a request is decoupled from its receivers, allowing for more flexible and reusable code. That is one advantage. The second one is dynamic composition. The chain can be modified at runtime by changing the order of or the handlers. Let's see use cases of this pattern. For example, event handling. We have a UI system, often use this pattern to manage event propagation. Middleware in web application, each middleware can process the request or pass it to the next one. Logging framework, different loggers can handle messages of variety of severity. This pattern is command pattern. The command pattern is a behavioral design pattern that encapsulates a request as an object, thereby allowing for parameterization of clients with queues, requests, and operations. This pattern is particularly useful for implementing features like undo, redo operations, logging changes, and supporting queued requests. Let's understand the key components of this pattern. So we have a command interface, declares an interface for executing operations. We have a concrete command, implements the command interface and defines the binding between a receiver and an action. We have a receiver, the object that knows how to perform the operation associated with the command. And we have an invoker, the object that holds a command and invokes it when needed. And then we have client, which creates a concrete command and association it with a receiver. Now let's understand this with this example, right? So first one what we have is command interface, declares an interface for executing operations. Now in our case we have this interface which is command interface, and we have these methods execute and undo. Then we have concrete command which implements the command interface and defines the binding between a receiver and an action. Now we have this concrete class, right? And this is also a concrete class. Basically this is the concrete class because it is implementing this interface. What it is doing, it is overriding these methods execute. So it says light turn on, light turn off, because here I have used the light on command. I mean this class is light on command. A similar way we can create another class which is light off command, implementing this command only, and there we can execute this method light dot turn off, right? Likewise we already have, and in undo we can put turn on. Okay, then we have an invoker class, the object that holds a command and invokes it when needed. So this is our invoker class. What it does, it has two methods, basically pressing the button on the remote or press undo, right? We want to go back. Now we have created this object of command, right, which is of interface type, and what we are doing, we are just invoking the method of these. For example, if when we want to execute this press button, we want to execute this this method, execute method, which in turn will go to the implementation class, which is for example light on command or light off command, right? So this is how we can implement this pattern. Let's see the advantages of this type of pattern. Decoupling, the invoker and the receiver are decoupled, allowing for flexible command execution. Commands can be restored and executed later, enabling undo redo functionality. And these commands can be queued and executed later on, which is useful in asynchronous processing. Let's see the use case. GUI applications, menu items, buttons often use commands pattern to handle actions, implementing operations that can be rolled back, for example, transactional systems, job scheduling, queuing commands to be executed at a later time. Interpreter pattern. The interpreter pattern is a behavioral design pattern that defines a representation for a language grammar and provides an interpreter to evaluate sentences in that language. This pattern is particularly useful for designing languages, expression parsing, and implementing simple scripting language. Let's see the key components of this pattern. So we have abstract expression, declares an interface for interpreting context. Then we have terminal expression, implements the abstract expression interface for terminal symbols in the grammar. Then we have non-terminal expression, implements the abstract expression interface for non-terminal symbols in the grammar. And finally we have the context, which contains information that is global to the interpreter and can be passed between expressions. Let's see the advantages and disadvantages. It is easy to extend. New expressions can be added easily without modifying existing code, and it simplifies the grammar, makes it easier to define and interpret the languages of grammar. Disadvantages are it is complex. For complex grammars, the number of classes can become large and harder to manage, and it might have a performance impact. Interpreting expressions can be slower than direct execution, especially for complex grammars. Let's see the use case of this pattern. Scripting languages, parsing and interpreting simple languages or these domestic specific languages, and expression evaluation, evaluating mathematical expressions or queries. Iterator pattern. The iterator pattern is a behavioral design pattern that provides a way to access the elements of a collection sequentially without exposing its underlying representation. This pattern allows for a standardized way to traverse different data structures while keeping the traversal logic separate from the collection itself. Let's see the key components of this pattern. Iterator interface. It defines the methods for accessing elements in the collection. For example, next, has next. Basically, next is to go to the next item. Has next to check if there is any item or not. Concrete iterator implements the iterator interface and keeps track of the current position in the traversal. Then we have aggregate interface, which defines a method for creating an iterator. And then we have concrete aggregator and aggregate, which implements the aggregate interface and returns an instance of a concrete iterator. Let's see the advantages and disadvantages of this type of pattern. Advantages are, of course, the decoupling. It separates the iteration logic from the collection, allowing for easier maintenance and changes. Multiple iterators. You can have multiple iterators for the same collection, enabling concurrent traversal. So, you can create multiple iterators, and you can one iterator you are doing for some purpose, another iterator you are using for some another purpose. Disadvantages of complexity is one disadvantage. Adding iterators can increase the complexity of the code base, especially for simple collections. And of course, the memory overhead. Each iterator may require additional memory for maintaining its state. Let's see the example use case. Yes, collection framework is a very popular one. Libraries and frameworks often implement the iterator pattern to allow for traversal of their collections. Custom data structures. Any data structure that require iteration, such as trees, graphs, or custom lists. Mediator pattern. The mediator pattern is a behavioral design pattern that defines an object that encapsulates how a set of objects interact. This pattern promotes loose coupling by preventing direct interaction between objects and instead allowing them to communicate through a mediator. This can help manage complex interactions between multiple components, making the system easier to maintain and extend. Let's see the key components of this pattern. So we have mediator interface, which declares a method for communication between components. Then we have concrete mediator, which implements the mediator interface and coordinates the interaction between components. And then we have colleague classes. These are the components that communicate with each other through the mediator. Let's see the advantages and disadvantages of this pattern. Advantages are of course loose coupling, because it reduces the dependencies between components, making it easier to change or replace them. Centralized control, all communication is managed by the mediator, simplifying the control flow of interactions. Disadvantage is one of them is complexity. The mediator can become a complex and bulky class if it manages many components, and single point of failure, because the mediator itself can become a bottleneck if not designed carefully, if it fails somewhere. First, let's see the example use case. In graphical user interface, different UI elements often communicate through a mediator. For example, a dialog or panel or a web interface. Users can interact with each other through a mediator like a chat server. Observer pattern. The observer pattern is a behavioral design pattern that establishes a one-to-many relationship between objects, allowing one object, the subject, to notify multiple dependent objects, observer, of any state changes. This pattern is particularly useful for implementing event handling systems or maintaining consistency across multiple views of the same data. Let's see the key components of this pattern. So we have a subject, observer, concrete subject, and concrete observer. Subject is the object that maintains a list of observers and provides methods to add, remove, and notify them. Observer is an interface or abstract class defining the methods that will be called when the subject state is changing. And concrete subject is implementing the subject interface, maintaining the state and notifying observer, whereas the concrete observer will implement the observer interface, responding to updates from the subject. What are the advantages and disadvantages? Loose coupling. Observers can be added or removed without modifying the subject. Observers can subscribe or unsubscribe at runtime, enabling flexible interactions. And disadvantages would be, if observers are not properly managed, they may continue to receive updates even after they are no longer needed, so memory leaks issue. Managing multiple observers can lead to a more complex system, especially if the relationships are intricate, so complexity. Let's see the example use cases. Event handling. In GUI frameworks, UI components can observe changes in model data. Then notification systems. Systems that notify users of changes such as news feeds or stock price updates. State pattern. The state pattern is a behavioral design pattern that allows an object to alter its behavior when its internal state changes. State changing and something should happen, that's why it's state pattern. This pattern is particularly useful for managing state-based behavior in an object, enabling it to appear to change its class. Let's see the key components of this pattern. Context, state interface, concrete states. Context is the object that maintains a reference to a state object. It delegates state-specific behavior to the current state. State interface is an interface that defines methods for handling state-specific behavior. And concrete states are the implementations of the state interface that define specific behavior for each state. Let's see the advantages and disadvantages. Advantages would be clean separation of states. State-specific behaviors are encapsulated in their respective classes, making the code more organized and easier to maintain. Dynamic behavior changes. The context can change its behavior at runtime by switching state objects. And disadvantages would be, if there are many states and transitions, the number of classes can grow significantly, which may complicate the system. and managing complex state transitions can become challenging as well. Let's see the example use cases. Game development. Managing different state of a character, idle, running, jumping, where it was earlier. Workflow systems. Managing states in a business process, for example, order processing states. Strategy pattern. The strategy pattern is a behavioral design pattern that enables an algorithm's behavior to be selected at runtime. What strategy we need to select at runtime? This pattern defines a family of algorithms, encapsulates each one, and makes them interchangeable. The client can choose which algorithm to use without modifying the code that uses it. Let's see the key components. Strategy interface. It defines a common interface for all strategies. Concrete strategies implement the strategy interface with specific algorithms. So basically we have everything in this interface which should be implemented, and then we have concrete classes, subclasses which will implement that interface. Context maintains a reference to a strategy object and can switch strategies at runtime. Let's see the advantages and disadvantages. Advantages would be, of course, flexibility, because we can switch algorithms or strategies easily without changing the code. Single responsibility. Each strategy encapsulates its algorithm, adhering to the single responsibility principle that we have learned in solid principles. Open closed principle. New strategies can be added without modifying existing code. That is another solid principle. Disadvantages would be increased complexity. More classes are introduced, which can lead to a more complex code structure, and the client must be aware of the different strategies and how to select them. Let's see the example use cases. Sorting algorithms. Different sorting algorithms can be encapsulated as strategies. Payment processing. Different payment methods, credit card, PayPal, etc., can be implemented as strategies. Template method pattern. The template method pattern is a behavioral design pattern that defines the skeleton of an algorithm in a method, allowing subclasses to refine specific steps of the algorithm without changing its overall structure. This pattern promotes code reuse and helps to enforce a consistent algorithmic flow while allowing flexibility in specific implementations. Let's see the key components of this pattern. Abstract class contains the template method which defines the overall structure of the algorithm. It may also contain default implementation for some steps, and concrete classes, subclasses that implement or override specific steps of the algorithm defined in the abstract class. Let's see the advantages and disadvantages. Code reusability. Common algorithmic structure can be reused across different subclasses. Consistency. Enforces a consistent algorithm structure across subclasses, reducing errors. Allows subclasses to define their specific behavior while maintaining the overall algorithm. And if too many steps are defined in the base class, it can limit the subclasses' flexibility in changing the algorithm structure and can lead to a complex inheritance structure if overused. Let's see the example use cases. Defining a game loop where certain steps are common, initialization, running, cleanup, etc. And data processing, a framework for processing data where the steps are common but specific actions differ. Visitor pattern. The visitor pattern is a behavioral design pattern that allows you to separate an algorithm from the object structure on which it operates. This pattern lets you add new operations to existing object structures without modifying the structures themselves, which is especially useful in systems with complex object hierarchies. Key components are visitor interface, concrete visitor, element interface, and concrete elements. Visitor interface declares a visit method for each type of element in the object structure, and concrete visitor implements that visitor interface and defines the specific operations to be performed on each element. Element interface defines an accept method that takes a visitor as an argument, and concrete elements implements the element interface and provides the specific behavior for the accept method. Let's see the advantages and disadvantages of this pattern. Advantages are separation of concern, extensibility, single responsibility principle. It separates the algorithm from the object structure, promoting a clean design. New operations can be added easily without modifying existing classes, and elements do not need to know about operations. So it's a solid principle. Disadvantages are, of course, it is a complex, can add complexity to the code base, especially if the number of elements and visitors grow, and difficult to maintain if changing the object structure can require changes in all visitors, which may be cumbersome effort. Let's see the example use cases. Compilers, implementing operations or different type of syntax trees, and performing operations on elements of various types in data structures like trees or graphs. So we have learned architecture styles and patterns. Let's see the difference between them, those on various aspects. So architectural styles and design patterns. Architectural styles on high level solution defining overall system structure, whereas design pattern granular solutions addressing specific design problems. Purpose wise, architectural styles focus on organization and interaction of components, whereas design pattern aim to solve recurring problem within components or process. And we will understand with this aspect, which is scope. Architectural styles affects the entire system architecture, whereas design pattern typically applied within a specific context, often independently of architecture. Examples are, we have already seen these architectures. Impact wise, architecture styles influences multiple components and their relationships, whereas design pattern enhances functionality and maintainability of individual components. Let's understand this key term, quality attributes or non-functional requirements, or NFR, in software engineering. When we get any opportunity, we work for any project, we almost do this type of activity also. We talk to stakeholders, understand what is the requirement, which is the main functional requirement which we need to accomplish. But there are non-functional requirements also which are not specifically told, but still we need to consider. Now let's understand what are those. Quality attributes are the non-functional requirements of a software system that define its overall quality and performance characteristics. They help to assess how well a system meets the needs of its stakeholders beyond just functional correctness. Let's see the key quality attributes. Performance, scalability, reliability, availability, maintainability, and there are more. Performance is the measure of how quickly a system responds to a request, often assessed in terms of latency, throughput, page time load, etc., resource utilization. You are accessing a website, how much time this website, a particular page is taking. You are submitting a form, how much time this form submission is taking, right? So these all things come under performance. Scalability, the ability of a system to handle increased load by adding resources, right? So for example, today there are 100 users accessing your website, tomorrow more users are coming, so how you need to add more resources to your system, so that comes under scalability. Reliability, the probability that a system will function correctly and consistently over a specified period, including its ability to recover from failure. So for example, because of some XYZ reason, maybe because of natural disaster, one server goes down, but still the application is functioning, means it's more reliable. More availability, the propagation of a time a system is operational and accessible, typically expressed as percentage, for example 99.9% uptime. So it is coming in availability. Reliability is more reliability if there is any failure, but still it can recover itself, right? For example, we create replicas of system, replicas of database, etc. If one database is down, still from the replica we are using the system, the application is up, working fine. Maintainability, the ease with which a system can be modified to fix defects, improve performance, or adapt to a change environment, right? We have seen that agility, in agile development we get the feedback from the business, we fix it during the maintenance phase, right? Then we have security, the ability of a system to protect against unauthorized access, attacks and data breaches, ensuring confidentiality, integrity and availability. Then extensibility, the ability of a system to accommodate future growth or changes without significant work, allowing for the addition of a new feature or components. And reusability is the degree to which components or modules can be reused in different applications or context. Now you see, these are the different quality attributes or the non-functional requirements which we consider. Not we should, but we always consider while we develop or we implement any of the project. Let's understand the importance of these quality attributes. System design, guiding architectural and design decisions to ensure the system meets stakeholder needs. Stakeholder satisfaction, it ensures that the system delivers a positive experience to users and meets business goals. So for example, we have been given this requirement that we need to design a form, a page where we have a form, maybe you consider it's a registration form. Now we have developed this registration form, user is able to fill the form and finally click on submit button. But the problem is, the non-functional requirement says performance is one of the aspects. The page load time, the submission time, right? It should be fast. There should not be any latency. But we have not considered that. And when we are submitting the form, it is taking indefinite time, right? So, is it a satisfactory solution which we have given to business? No, right? So, stakeholder satisfaction, risk management, identifying and mitigating potential issues that could affect system performance and reliability. Long-term viability, ensuring the system can adapt to changing requirements and technological landscapes. Next key terminology is technology stack. Whenever we do the architecture of any of the solution, we always discuss what is the technology stack, on which technology we are going to build this solution when it will go for implementation. Though architecture is independent of the technology, but it is discussed because once the architecture is complete, it goes for implementation, and there it is already decided for which technology, using which technology we are going to build this solution. So technology stack is also a very important step to understand what we are going to discuss, what we consider here. A technology stack is a combination of technologies used to build and run an application or project. It includes the programming languages, frameworks, libraries, databases, tools, platforms, etc. that developers are going to use to create that software. Let's see the common layers of a technology stack. Mainly we will find that we will always have a front end, which is client side. We will have a back end, which is server side. We will have databases. We will have some DevOps team, hosting, etc. We will create a DNS of server, etc. Some website URL will be there, right? Someone will deploy the content, code, etc. And then cloud services. The user front end will be the user interface layer that handles how user interact with the application. Backend server will be the server layer responsible for processing request, business logic and data management, and which data we are going to use will come under the database. And finally, the layer that focuses on deployment, version control, maintaining an application infrastructure will come under the DevOps activity. And these are the examples of technology stacks. So for example, the popular ones, the mean stack, MERN stack. Mean stands for M for MongoDB, E for Express.js, A for Angular, N for Node.js, whereas for again here is MongoDB, Express, React, Node.js, right? So this is the technology stack. Another technology stack could be, for example, within Adobe Experience Manager is one of the CMS, so it could be AEM is front end, and then in back end we have OSGI layer, etc. Right? So there can be multiple technology stack for different type of technologies. Another concept in the software engineering is behavior. In the context of software design and systems, behavior typically refers to how a system or component responds to various inputs, events, or conditions. This includes the actions taken by the system, the order in which they occur, and how they interact with other components. Let's see the key aspects of behavior. Response to inputs, how the system reacts to user actions, such as clicks, form submissions, or API requests. State changes the way the system transitions from one state to another based on events or conditions often represented in the state machines or state diagrams. Then we have interactions, the communication and collaboration between different components or services, including method calls, message passing or API interactions. Then business logic, the rules and algorithms that govern how data is processed and how decisions are made within the system. Error handling, how the system responds to unexpected conditions or failure, including logging, user notification and recovery actions. Concurrency, the ability of system to handle multiple tasks simultaneously, which affects behavior in multi-threaded or distributed environments. So these are the aspects of behavior. Now the examples would be, for example, user interface behavior, state management, service behavior, right? The way a web application responds to a user input, such as opening a model dialog when a button is clicked, or maybe if some issue is coming, some error is there, so we are just showing that error maybe with red font, right? Or in a React application, how the application's UI updates based on changes in the component state. So these all are behavior. Some events are happening and we are taking some action on the screen. What is stakeholder need? Stakeholder needs refer to the requirements and expectations of individuals or group that have an interest in the outcome of a project or system. Identifying and understanding these needs is crucial for successful project delivery. Unless we know what is the requirement, what is the need of from different stakeholders, we will never be able to accomplish this project successfully. Let's see the common stakeholder needs. So for example, related to functionality, the system must meet specific functional requirements that allow users to perform desired tasks. Usability, in terms of the application should be easy to use within an intuitive interface that enhances user experience and minimizes training time. Performance, stakeholders expect the system to perform efficiently with fast response time and minimal downtime. And security, protection of sensitive data and user information is critical. Stakeholders need assurance that the system is secure from threats and breaches. Scalable solution, the ability to grow and handle increased loads without a drop in performance is important for future proofing the system. So these are needs of the stakeholders. Few more, for example, reliability, stakeholders require that the system operates consistently and accurately with minimal errors and the ability to recover from failures. The system should be easy to update and maintain, allowing the quick fixes and enhancements without significant downtime. It should adhere to the relevant regulations and standard whatever is necessary. For example, if the industry is related to finance, healthcare, life science, etc., or maybe something related to the geography where this website or the platform is going to be launched. For example, if it is in Europe, so Europe related regulations, GDPR, etc. Cost effectiveness, stakeholders are concerned about the overall cost of the project, including development, maintenance and operational expenses, and the ability to work with existing systems, vendors, tools is often a key need, allowing for seamless data exchange and interoperability. Why it is so important to understand stakeholder needs? One is, of course, it guides into development, because if we it is clearly defined what is the need from the stakeholders, we will never be able to complete the project. It will improve the satisfaction, because once this project is complete and then it is according to what they were looking for, they will provide a positive feedback which will improve their satisfaction and we will get more opportunity from the business. It reduces risks, because identifying potential issues early helps mitigate risks and prevent costly changes later in the project. And it facilitates communication, understanding needs, promote better communication and collaboration among team members and stakeholders. So we have gone through all those steps related to software architecture in software engineering, whether that is software architecture is style, design pattern, different various aspects of software development phases, right? SDLC models, solid principles, etc. Now let's see the importance of software architecture. Software architecture is a crucial aspect of software development that lays the foundation for the system structure, design, and functionality. And this is lays down few of the importance aspect we should always consider while we do the solutioning or we do the architecture of any of the given opportunity. First thing is, of course, it is going to be a blueprint for the development team. It facilitates communication, all the quality attributes, the non-functional requirements we need to address, we need to prioritize them, because on basis of that only the functionality, the application, the digital platform is going to work. It supports decision making. It aids in choosing technologies and design pattern effectively. It reduces risk. It enhances flexibility. It improves maintainability of the product. And of course, it guides in testing because it provides a framework for effective testing and validation of the system. And that's it in this course. Thank you so much for watching. I really appreciate you take this time to explore the world of software architecture, including solid principles, design patterns, and a lot of. Your support means a lot to me. If you found this video helpful, please like, share, and subscribe to this channel, Tech Talk with Ritesh, for more insightful content on technology and software development. If you have any question or topic I would like to hear, please leave a comment below. Until next time, keep learning, stay inspired. Thank you so much for watching.